Hello world, my name is David Malan, and this is CS50's Introduction to Cybersecurity for technical and non-technical audiences alike. In this course, you'll learn how to secure your accounts, data, systems, and software against today's threats, and how to recognize and evaluate tomorrow's as well, both at home and at work. You'll learn how to preserve your own privacy. You'll learn how to view cybersecurity not in absolute terms, but relative, a function of risks and rewards for an adversary and costs and benefits for you. And you'll learn to recognize cybersecurity as a trade-off with usability itself. In the world of cybersecurity, I dare say you and I have to be perfect. All of our doors, all of our windows, virtually speaking, have to be locked. But an adversary has to find just one mistake that we've made, a single door or window ajar. So perhaps we should be focused not only on prevention, but on detection especially, through auditing, through monitoring, so that even if an adversary gets in, we can at least detect as much quickly and minimize the downsides for us and, in turn, the upsides for them. Perhaps nowadays tools like artificial intelligence or AI can even help with that, detecting patterns in potential adversaries' behavior that we might not even notice ourselves. And perhaps if we raise the bar high enough for the adversary, increasing their cost, their risk, decreasing their potential reward, they'll simply lose interest in us as a target. Of course, if they have more resources than us, they might very well win anyway, but will they be even interested in us? Which of these threats should we actually worry about? Throughout this course, we'll present both high-level and low-level examples of threats and provide you with all you need know technically to understand both, even if you're not a programmer or computer person yourself. Through those examples, we'll introduce you to certain first principles, how computers themselves work, so that you can understand and deduce, even after the course ends, how other threats that the world might not have even seen yet actually work. This is CS50's Introduction to Cybersecurity. All right, this is CS50's Introduction to Cybersecurity. My name is David Malan, and this week let's focus on securing accounts. You and I have so many accounts nowadays, be it for websites or apps or the like, and we'll focus today on exactly what the threats are to all of those accounts, but more importantly, what some of the defenses are so that you can keep those accounts secure. But let's first consider what we mean by security in the physical world, for instance. Whether you live in a home, an apartment, a dormitory, or the like, odds are you have a key that lets you into that building. Now that key, of course, lets you in through that locked door, and then you have access to the entire habitat. But the catch is that if someone else gets that key, of course, they too can let themselves into that system or into that same building. So let's consider now in the digital world, though, what some of the building blocks are of security so that we can focus exactly what those threats and what those defenses are. So first, allow me to propose that we think about the security of our accounts in terms of authentication. So authentication refers to this process digitally of proving who you are, that I, for instance, am David. But that alone isn't necessarily enough to keep a system secure, because just because I'm David doesn't necessarily mean I should have access to your entire home. Perhaps I should not have access at all. Perhaps I should just have access to the entryway or some narrower form of access. And so there's this related topic when it comes to the security of locations or systems known as authorization. So authorization speaks to whether or not you should have access to something once you have proven that you are you, that I am David, and that I should in fact have access to the door that I just walked through. Now, when it comes to our accounts in the digital world, we of course don't use physical keys, but very frequently nowadays we use usernames, which of course can be public. It might be a username like David, it might be a username like Malan, or it might be more commonly even an entire email address that presumably uniquely identifies you in the world. But even though that's public, the thing that you and I ideally keep private is, of course, our password. And nowadays, you and I must have dozens, maybe even hundreds of passwords that are hopefully distinct and not reused across all of those different websites, but more on that in a moment. And so it's really this password that ultimately allows you to authenticate yourself, demonstrate who you are, because presumably I am the only one in the world that knows not only my username or email address, which all of us can know, but presumably I'm the only one in the world that knows my username and this here password. And so the presumption is if I type in both of those values to some app or some website, that I must in fact be David Malan in that case. Of course, it's not good enough to just have a password. You need to have a good password. Now, what do we mean by good password? Well, ideally, this password is not going to be in a dictionary, like literally a dictionary of English words or whatever your human language might be. Why? Well, there's this threat known as a dictionary attack. And by this, I mean an adversary, a hacker that wants to get into your account. They could just start typing randomly to try to figure out what your password is. But they're a little smarter. They'll actually use a dictionary attack. That is, they'll open a physical book of words, or more likely, they'll open a file on their computer containing a whole lot of actual English words or in some other human language, and then just one at a time, try this word as your password, this word as your password, this word as your password, and so forth. Because if you and I have chosen a pretty guessable password, one that is an actual word in a dictionary, they're going to get into your account much faster. But even if you and I are clever, and odds are by this point in life, you know that you shouldn't just choose a simple English or some other language word, but rather you should probably have some numbers, some letters, some punctuation or the like. You're still vulnerable, as am I, to what we'd call a brute force attack. Brute force sort of evokes the memories of yesteryear where where someone might have had a branch of a tree using as a battering ram, trying to get into the castles from past times. But brute force attacks in the digital world mean something analogously, whereby you're using software to digitally try all possible passwords. And so here too are you vulnerable, because if your password is too short, even if it's random with letters, numbers, and symbols, odds are an adversary or a hacker that has enough time and enough technical savvy, they can just try every possible password in the world, and eventually they might very well get into your system. So how do we go about defending against these kinds of attacks? Well, we use these passwords, but these passwords, of course, come in different forms. And it's kind of a low bar that is set by default on a lot of devices still nowadays. For instance, on your phone, if you'd like to chime in here in the chat, how many characters or digits in particular are typically required of systems? Well, I would conjecture that very often when I set up a phone, I'm only asked for a passcode, a numeric password, of 4 digits alone. Now, if you have a 4-digit passcode, or password more generally, how secure is that? And how do we even go about thinking about how secure that password is? Well, I would propose that we could start to measure, not even using fancy math, but just some basic heuristics. We could measure the security of a password that has just 4 digits by considering, well, how many possible 4-digit passcodes are there? So perhaps if you'd like to chime in here in the chat, how many possible passwords are there if they're all digits, 0 through 9, decimal digits, and if you only have 4 of them? How many possibilities are there? I'm seeing 1,000, I'm seeing 10,000, I'm seeing 9,999, and I'm seeing a whole range. And I think a lot of you have the answer spot on. It's 10,000. It's 10,000. Why? Well, if we just think about this numerically, if I've got 4 decimal digits, 0 through 9, well, the smallest password I could come up with, so to speak, would be 0000, and the largest password I could come up with would be 9999. Now, you might think, OK, well, that's obviously 9,999 possibilities, but not quite, because if you include 0000, that's the 10,000th possibility. So indeed, there's 10,000 possible passwords if we're using 4 digits specifically. So how do we actually think about that more generally, especially so that we can now figure out the math for larger passwords as well? Well, if you've got 0 through 9 as the first possible digit, and 0 through 9 is the next, and 0 through 9 is the third, and 0 through 9 as the fourth, you have 10 possibilities times 10 possibilities times 10 times 10. This, of course, if we do it out more mathematically, is 10 to the 4th power, the exponent being 4. And that, of course, gives us 10,000 as well. So that might be the more mathematical way of approaching it versus just the more intuitive, that 0000 can go all the way up to 9999. Now, again, a question for the group. How long do you think it might take for an adversary or a hacker to get into my device, for instance, my phone, if I do have a 4-digit password? If I've got a 4-digit password, this means they might have to try as many as 10,000 possibilities, because in the easiest case, sure, they get lucky and my password is still the default 0000. But in the worst case, I chose 9999 and they don't get to that until the very end of their attempts. Or maybe I choose something there in between. I'm seeing 10 seconds, less than a second, milliseconds, 10 seconds a day, 4 hours. OK, so the responses are all over the place. So how could we go about actually measuring this or estimating this? Well, let me propose this. I'm going to go over to my computer here. And even if you've never written any code before, let's go ahead and write some code together here. I'm going to go ahead and open a program called VS Code, Visual Studio Code, which is a free program that we use in CS50 more generally that allows me to write code on my Mac or PC or in really any internet-based device. And I can actually write code and not only write it, but run it. And I'm going to write code in this case in a language called Python. And this is just a very popular language, but I could use any of a dozen or more different programming languages. And the goal here is not to learn Python. For that, we have whole other classes. But to just demonstrate what an adversary, what a hacker need do if they want to get into, for instance, your iPhone or Android device or anything that has just a 4-digit password. Now, my presumption here for demonstration's sake is that I'm going to go ahead and write code that just prints all possible passwords on the screen. But you could imagine if I had a USB cable or maybe a lightning cable, I could connect this phone to this laptop, especially if it's your phone that I just swiped from a table, could quickly plug it into my computer here, run the code that I'm about to write, and maybe automatically send all 10,000 possibilities to your device before you even realize the phone is gone. Now, here's how I'm going to do this. I'm going to go ahead and in a text file called crack.py, where crack is actually a term of art. It just means to figure out what a password is, to brute force your way in. I'm going to go ahead and from a library called string, I'm going to go ahead and import digits. Now, this is a very easy way of just giving me access to the numbers 0 through 9. I could obviously type them all out on my keyboard. This is a little faster because this gives me like a list of the numbers I care about. Now, there's a bunch of different ways I can write this code, but what I really want to do intuitively is try all possible digits for the first value, try all possible digits for the second, then for the third, then for the fourth. So one way of doing this might be as follows. I'm going to use a keyword in Python called for, which just means do something for as long as I want you to. And then I'm going to give myself a variable, like in math, just so I can use something to keep track of each number. And I'm going to use a default value of I for integer. And then I'm going to go ahead and say that for each value I in those 10 digits, I want to go ahead and do the following. Well, for each of those I digits, for the first value, I want to do for j in digits as well. And then for each value for my third placeholder, I might do something like for k in digits. And then lastly, I might do for l in digits. So this is admittedly not the best design. And those of you who have programmed before are probably cringing that I have this indentation, indentation, indentation. But it's a simple way of demonstrating, especially for those unfamiliar with programming, how we can try all possible first digits, all possible second, all possible third, all possible fourth. And all I'm going to do, very inside of this code now, is print out the value of I, j, k, and l. So that iteratively, we should see on the screen 0, 0, 0, 0, and then all the way up to 9999. So if you assume that I've connected my phone to this laptop, ideally then we'll have an estimation of how long it might take until we actually have cracked into the device. So let's go ahead and do this. I'm going to open up a separate window on my screen here. It's called a terminal window. And I'm going to go ahead and run Python of crack.py. So in just a moment, we're going to see, is it going to take a few minutes, a few milliseconds, a day, 4 hours, or here we go. 1, 2, 3, go. OK. So those of you who estimated just a few milliseconds were spot on. So what's the takeaway here? Well, apparently using a 4-digit password is not very secure at all, because look how quickly I, the adversary, the hacker in the story, was able to get into your phone. And in fact, I could probably unplug it at that point because I've gotten whatever data I care about off your phone, and you might not be none the wiser. So how can we go about improving upon this system? Well, let me propose that instead of using a 4-digit passcode, let's use 4 letters instead. And we'll use English because that's what I speak well. And in English, we have 26 letters of the alphabet, A through Z. But you know what? That might give us initially 26 possibilities for the first position, times 26, times 26, times 26 for the second through fourth. But let me propose that we actually use lowercase and uppercase letters. So that gives me not 26, but 52 possibilities for each location. So if I do 52 possibilities, that's 52 to the 4th power. And does anyone want to estimate how many possible passwords there are if I'm using 4 English letters now, uppercase or lowercase? I'm seeing 26 to the 4th power, but that's not right if we're using uppercase and lowercase. It's indeed 52 to the 4th power, and I'm seeing a lot. But here we have estimates along the lines of indeed 7 million as well. So with 7 million possibilities, you might think, OK, surely that's going to be a lot better, and it's going to take the adversary a lot longer to hack into this phone. But let's try that. Let me go back to my terminal window here. Let me reopen now my code file, and let's go ahead and use not digits, but let's go ahead and use ASCII letters. For those unfamiliar, ASCII letters are simply the letters A through Z in both uppercase and lowercase. Now, here I have to go ahead and change this from digits to ASCII letters, from digits to ASCII letters, from digits to ASCII letters, and lastly, from digits to ASCII letters. Again, there's an easier way I could implement this code to be more succinct and less duplicative, but it involves some features that we'll introduce in another class altogether. But now I have all possible ASCII letters from my first placeholder to the last. Let's go ahead and open up that same terminal window. Let's run Python of crack.py, and here now is the answer to how long might it take an adversary to get into your phone if you're using 4 letters of the English alphabet for your password instead. OK, so this time I have enough time to walk all the way over to the screen here, and you can see that we're going in alphabetical order, first lowercase, now uppercase, but in just a moment we are done. And we're down all the way to Z, 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 Z. So that was a few seconds, which is indeed slower, but that really wasn't that much effort at all. So presumably then even 4 letters of the alphabet might not be enough to keep us secure. So let me go ahead and do what we all are told to do anyway, which is to go into your phone or whatever device in question and actually use 4 characters perhaps instead. So not just letters, not just digits, but let's toss in some punctuation as well. And in the world of punctuation, at least on a US English keyboard, there's typically as many as 94 possibilities for letters, numbers, and punctuation because we have 26 lowercase letters, 26 uppercase letters, 10 decimal digits, 0 through 9, and another 32 punctuation symbols that we can add into the mix as well. So that gives me 94 possible keys that I can hit here, or 94 to the 4th power. And does anyone want to estimate what this is? We've gone from 10,000 to 7 million to, I'm seeing it indeed in the chat, roughly 78 million possibilities. So in some sense, 10 times more secure. Let's go back to my terminal window, open up my code here, and import not only ASCII letters, but also the digits from before, and also this time some punctuation as well. Now let's go ahead and change just the ASCII letters alone to ASCII letters plus those digits, plus that punctuation. And just to save some time, I'm going to highlight and copy what I just typed, and I'm going to change the 2nd position, the 3rd position, and the 4th position as well to use that combination of 94 possibilities. I'm going to open up my terminal window again. I'm going to run Python of crack.py, and this time, because we have 10 times as many possibilities, I kind of had 10 times the amount of time to walk over to the screen, because indeed we're still in the lowercase e's, f's, g's, h's, and now it looks a bit like a Hollywood movie maybe. You can perhaps see, even though it's going across the screen fast, that there's a lot of cryptic output here because we're running through all of the letters, the digits, and the punctuation, so it looks a little fancy at that. Now, you might recall, too, from Hollywood movies, too, that they tend to be very dramatic. And so instead of just doing this, which is iterating from left to right very slowly, the movies and TV shows tend to very dramatically get like the 3rd character right, then the 1st character right, then the 4th character right, and then just in time, you get the 2nd one as well. Like, that's not really how brute force works. You tend to do things methodically, not jumping around from symbol to symbol. But this is clearly taking a long time, and I'm not even going to finish waiting for this to go because we still have to get through all the punctuation. So this is to say ultimately that 78 million possibilities is actually getting up there pretty fast. But honestly, if we come back in like a minute or so, I bet that will be finished nonetheless. And none of us, hopefully, has a password that's only 4 characters nowadays. Letters, numbers, and punctuation. Odds are it's at least a conventional 8 characters. And indeed, most websites and apps require as much of you as well. Now, the math here is pretty straightforward, too. If you have 94 possibilities, but you have 8 characters in total now that's 94 to the 8th power. And does anyone want to ballpark just how many passwords are possible if it's only 8 characters, which isn't even that long? But you have 8 of them total. Too many. It comes back one answer. too much to count. OK, I see that we've given up here. But oh, I did see one in the chat. It's roughly this many possible passwords, which is actually a little hard to figure out. So this is, let's see, millions, billions, trillions, quadrillion. So this is 6 quadrillion possibilities. So now we're talking. Now the adversary is probably going to run out of time, run out of energy, run out of money, run out of lifetime if it's going to take this much time to try to crack, so to speak, your particular password. And so here's one of our first takeaways when it comes to cybersecurity and securing our accounts. It really is this game of relativity and resources. What we're really doing here is not something fundamentally different by adding in digits and numbers, digits and letters and punctuation. It's sort of still the same formula, the same approach to our passwords. But as we add complexity and as we make it longer and longer, we're raising the bar to the adversary. Why? Well, so long as you and I don't do something dumb like still choose 0, 0, 0, 0, 0, 0, 0, 0, so long as we're choosing something that's pretty random in that range of 6 quadrillion possibilities, it's going to take the adversary way more time than it would otherwise to brute force their way into that password. And so by the time they finally get into the account, you might have changed the password already. You might not be using the account anymore, or you or the adversary might not even be on this planet anymore. And that's indeed the goal. But there is a downside, of course. The longer your password gets and the more complicated it gets, the more likely you and I are to not even be able to remember what that password is. And so here is that sort of balancing act, trying to figure out this balance between the usability of the account, just how user-friendly it is to access, versus the security of that account. And finding that inflection point is somewhat personal or somewhat corporate in policy typically. Well, let me pause here and see if there are any questions now on securing our accounts via passwords alone.
I was wondering, a couple of years ago, there were devices, USB devices with fingerprint recognition. How come that's not more frequently used? Were they too expensive, or?
A really good question, and we'll come to this topic in a little bit on biometrics more generally, but your intuition is pretty much right. It's expensive to have another device, and most consumers are not going to bother wasting money on something just for them. Some companies might, but if they have a lot of employees, that could get very costly. But you might be glad to know that one of the topics we'll end on today is a new technology called passkeys that actually leverages a device you most likely already have, a phone that might use your fingerprint or might use your face or some other form of biometrics. That's becoming more common nowadays, or soon will, even for your laptop and desktop, which will talk to that phone in some form. How about one more question here on securing accounts?
My question is why if 4 digits password is so unsafe, why some program still is using this password, not a website like program?
Oh, really good question. Why are some programmers using this? So it's a trade-off between usability and security. If you are the programmer designing the system, you presumably want users to use the system and to come back and to keep using it. But if you make it too hard for them to access that account, if you increase the probability that they're going to constantly forget their password, lose their password, they might just stop using your system or your app or your website altogether. And so that's probably not a good thing. Other reasons might include just unawareness, or not having taken a class on cybersecurity, or not having really thought through the implications of having such short passcodes. So nowadays is industry starting to nudge us in better and better directions. But we'll see today in the rest of this class that there are still going to be a lot of trade-offs, again, between usability and security. So what can we do to defend ourselves against these brute force attacks? Well, at least here in the US, there's an organization called the National Institute of Standards and Technology, otherwise known as NIST, that actually issues recommendations for how we as consumers or companies, or more generally humans, can go about securing their accounts more effectively. And we thought we'd share just some of these recommendations so that it informs not only your own behavior as an individual citizen or consumer, but perhaps if you're in a place of business where you can influence your own company's policies here are generally what are considered best practices nowadays. So a quote from their recommendations: memorized secrets shall be at least 8 characters in length. So that at least corroborates the quick math and the test that we ourselves just ran, that only once we got up to like 6 quadrillion possibilities did it feel like it was going to take a very long time to actually hack into someone's device. So consider that for your own accounts. Even on your phones, you might have to go through a few menu options to upgrade from just 4 digits to something more, but odds are you'll benefit from this additional layer of security. This one's more of a mouthful, but helpful as well. Verifiers, so the website or app that's verifying your input when you authenticate with your username and password, verifiers should permit subscriber-chosen memorized secrets of at least 64 characters in length. All printing ASCII characters as well as the space characters should be acceptable in memorized secrets. Unicode characters should be accepted as well. Now, if you're not yourself a computer person, there's a bit of jargon within this. But first of all, the takeaways are that websites and applications should let you and me come up with passwords that are actually as long as 64 characters. Now, that's pretty long, but that's exactly the point, particularly as it's gotten more difficult for you and I to remember all of our passwords, to come up with very complex passwords. The reality is you and I might very well be better off on the whole by just choosing an easier to remember but much longer password. For instance, a sentence, a quote, a phrase that you can more easily keep in your human mind, but that doesn't necessarily have a crazy amount of punctuation or digits or letters, but at least is 64 characters in length. So even if an adversary tries a dictionary attack, trying all possible English words or some other language, even if they try a brute force attack, it's going to take them way too long. Unless, of course, you do something foolish like choose a 64-character passcode that's 000 or so forth. So you still want to be original within that space. Now, more technically, this recommendation is referring to ASCII. ASCII generally refers to US English symbols on a US English keyboard, as was the origin of this code system. So that includes A through Z, 0 through 9, and the punctuation I alluded to earlier. But websites and apps nowadays should also support Unicode, including things like emoji and other accented characters or symbols that you might have in languages beyond English. Unfortunately, this is not really common practice, I dare say. Just yesterday, I created an account on a new website for the first time, and it made me jump through hoops, so to speak, figuring out the right number of uppercase letters, lowercase letters, punctuation, and even then, it told me I could only use certain punctuation, so I had to think about now which symbols I'm using. That is a lot of friction. That is not good for usability, and it's of questionable value for the security of the system if I can't even remember the thing afterward. So keep this in mind in general, that your password should not only be 8 characters minimally, but most apps and websites you maybe yourself develop moving forward should allow much longer passwords as well. And you as the human can use longer passwords if systems allow them as well. Now here's another set of recommendations from NIST. Verifiers, the website or the apps that we're using, shall compare the prospective secrets, the passwords you're choosing, against a list that contains values known to be commonly used, expected, or compromised. So that is to say, when you type in a password, if it's already been a commonly used password, if it's very easily guessable, the website or app should probably say, pick a better password than that, just to decrease the probability that an adversary is going to get into that account. Specifically, NIST recommends that passwords obtained from previous breach corpuses, which is a fancy way of saying if some website, some database has been hacked, and that database contains usernames and passwords, and those passwords have now been uploaded to the internet for adversaries or anyone to download and browse, well, then you should not be allowed to pick a password from that list, because it's essentially an alternative dictionary. It essentially is a list of passwords that a smart adversary should just start with before they even bother resorting to brute force, which we've seen would take much more time. 2, dictionary words. So this we've already stipulated would be a good thing to avoid, because it's just much too easy for an adversary to go through a big list of English words or some other language and try those first. 3, repetitive or sequential characters. AAA, or slightly more creatively, but not good enough, 1, 2, 3, 4, ABCD. I would also add 0, 0, 0, 0, and so forth into that category as well. It's just too easy for the adversary to guess that maybe you're doing something repetitive like that too. And then lastly, context-specific words, such as the name of the service, the username, and derivatives thereof. This is to say, if you sign up for a Gmail account for the first time, you should not be allowed by Google to choose a password like Gmail password, quote unquote. If you sign up for an Amazon account, you should not be allowed by Amazon to have your password be Amazon password or some such variant thereof, because smart adversaries are going to try those same heuristics. And that's the catch too. If you can think of it, even if you think you're being clever, odds are a just as clever adversary can think of that heuristic as well and prioritize those tricks before they resort to brute force like I did on my own laptop. A few other recommendations as well. Memorized secret verifiers shall not permit the subscriber to store a hint that is inaccessible to an unauthenticated claimant. Verifiers shall not prompt subscribers to use specific types of information. For instance, what was the name of your first pet, when choosing memorized secrets. So there are a lot of companies, a lot of websites, a lot of applications that violate this recommendation nowadays. And in fact, I bet you can think of one or more accounts that you have where you've had to tell them, for instance, what was the name of your first pet or your first car or your mother or father's name or the like. That's not good to collect either, nor is a hint a good thing, because frankly, you and I are all too often in the habit of maybe typing into that hint field, if it's available, a question that's meant to help you remember what your password was. But if your hint is something like, my password is the name of my first pet, well, you're now just leaking information to the world, and anyone who can go online and figure out that information can now get into your account as well. And so that's really the threat in this case. If you start using personally identifiable information in this age of social media and websites like LinkedIn and the like, there's just so much information out there about us that can be discovered. You don't want to fill all of these databases, all of these systems with each of these tidbits about you, because a smart adversary with enough time and enough focus on you can probably figure out all of those same values. So what more? Verifiers shall not require memorized secrets to be changed arbitrarily, for instance, periodically. So this one, too, is something that a lot of companies violate as a recommendation still. If you're in a corporate workplace in particular, and you're being required by the system administrators to change your password every month, maybe every 3 months, 6 months, every year, perhaps, that's not generally recommended anymore, even though not too long ago it did sound like a best practice. But why is this not recommended anymore? To have you forcibly change your password periodically, like every few months?
Because the password will be easily forgotten and be more vulnerable to brute force attacks.
Why would it be more vulnerable?
Because the hackers can get access to all password and get hints about the new password.
Okay. So yes, one danger of forcing you and me to change our password too frequently is that you and I do not tend to exert much effort when we're required to do so. For instance, if my password today is, for instance, password 1, well, you know what my password might be in 3 months? Password 2. Or in another 3 months, password 3. You and I might exert the minimal amount of energy to change the password so that we meet the company's requirements, but so that it's not too hard for you and me to remember what the new password is. And so indeed, if information about my past passwords leaks out and some adversary sees, oh, well, wait a minute, your password was password 2 last month, I'm just going to guess heuristically that this month it's password 3, we might indeed be leaking information. What's another reason that you might not want to require humans to change their passwords arbitrarily on some schedule like this?
Okay, we keep forgetting our passwords if we change it too frequently. So that is not a good practice for a website.
Exactly. If you make me change my password too frequently, honestly, I'm probably going to forget what my next password is, because I'm going to get confused with last month's or the previous month's or the like. And so there's these sociological effects on us humans, just being human, not being very good at remembering not only the first password you made me choose that's very complex, but the second and the third as well. And so generally, you should not come up with such a scheme anymore because of these adverse side effects. And how about one more recommendation here? Verifiers shall implement a rate limiting limiting mechanism that effectively limits the number of failed authentication attempts that can be made on the subscriber's account. Now, what do we mean by this? Well, odds are this is something you yourselves might have experienced if, for instance, you forgot your password or you kept typing it slightly wrong. Maybe your phone's screen was wet, so it wasn't registering your fingertips properly. It turns out you can lock yourself out of your own phone, and you might have, in fact, seen something like this on iPhone. Android has a similar screen if, for instance, you type in the wrong passcode 10 times in a row. The presumption by Apple and Google and others is that if after 10 times you still haven't inputted your password correctly, it's probably a higher probability that you are not David, that you are not you, but rather it's someone else who has taken your phone, stolen your phone, and is trying to get into it. Now, that's not always the case. You can imagine situations where you just were being absent-minded, you were half asleep, maybe you weren't really focusing on it, and you locked yourself out. And so there, too, is, again, a trade-off between usability and security. But the higher probability event after 10 wrong attempts probably tends to be that it's an adversary trying to get in and not you. But what's the point of this? Beyond annoying the adversary, and maybe more significantly, really annoying you when it happens by accident, what this effectively does is it slows the adversary down. In other words, it increases the cost of this attack to the adversary. Why? Well, we saw a moment ago that a smart adversary who knows a little bit of Python code and steals your phone can try 10,000 possible passwords in just less than a second. However, if you now slow them down by having this feature on your iPhone or Android device that pumps the brakes, so to speak, that lets the adversary try no more than 10 at a time, that significantly slows them down. Now they might have to spend at least 10 seconds, 20 seconds, an hour, a day, or longer, especially since what Android and iPhone also do is they tend to increase this time limit. The first time you mess up, it's 1 minute. If you mess up another 10 times, it's now 2 minutes, maybe 5 minutes, maybe 10 minutes. Maybe the phone even deletes itself, wipes itself, if that too is a feature that you or your company has enabled. So again, the right way to think about this beyond the usability trade-off is that we're just trying to raise the bar to the adversary. We're trying to make it more expensive, more costly, maybe more risky to the adversary by slowing them down. And by more risky, I mean if this is like a Hollywood moment and someone's just stolen the phone from your table at Starbucks or a coffee shop, they've plugged it into their laptop, they're trying desperately to crack into it before you come back to the table, well, by slowing them down, it's going to significantly increase the risk, too, that they are caught in the act while doing it. And hopefully, too, the goal is to just get them to lose interest in your phone, lose interest in your account, and have them move on to, ideally, no one else's, but at least, barring that, someone else's instead of yours. So, what are other defenses against these kinds of brute force attacks or even these dictionary attacks? Well, this is a system that you and I are increasingly being able to turn on, but also increasingly are being required to turn on as well, which is in general probably a good thing. Two-factor authentication, or 2FA, more generally known as multi-factor authentication, is a technology whereby in addition to having one factor that you use to log in, like your password, as is tradition, you also have a second or maybe more factors that you additionally have to use in order to log in. But these factors don't just generally mean one password, two passwords, three passwords, or the like. They're fundamentally different types of factors. And in general, they're broken down into these three categories. One is a knowledge category. A knowledge factor is just something that you know, something like your password that ideally you keep secret, no one else knows, and that's why it enables you to authenticate yourself. Prove that you are you because you and only you hopefully have that knowledge. But a second type of factor would be a possession factor, something that you physically have. So you might be in the habit at work of carrying around one of those little key fobs that has a little code on it that changes. Now those things can be expensive, so increasingly the world is just using our own phones, your own Android phone, your own iPhone that maybe has SMS support on it, text messaging, or maybe a specific app that displays a short code that you type in. The presumption is that you challenge the user not only for a knowledge factor like their password, but a second factor like something they possess, you significantly decrease the probability that an adversary is going to be able to get into that account, because whereas anyone on the internet, millions of people, can be a threat threat to you by just figuring out or finding your password, a possession factor really narrows the scope of the threat to only the other customers in Starbucks or the coffee shop, only the other people physically near you, because they would have to physically obtain that second possession factor. And then a third type of factor nowadays might be an inherence, something that is unique to you specifically, more generally described as biometrics. So maybe it's your fingerprints, maybe it is your face nowadays. Something that's inherent to you can be a third factor nowadays, because the presumption is that only you, ideally in the world, have exactly that factor as well. Now, this is a little different from what some companies, some websites, some apps describe as two-step authentication, where 2 steps might actually just be 2 passwords of some sort. But two-factor more technically refers to 2 or more of these types of fundamentally different factors, that being the most common in our case here. Now, when it comes to those possession factors, those key fobs or the apps or the codes that you receive, specifically what you're receiving in those models is generally known as a one-time password, or OTP. The idea being that this is not a password that you know and keep remembering and keep using again and again. It's literally one time, because it's texted to you, or it's sent via an app, via push notification, or it's actually sent to something on your keychain, like this here key fob, for instance. Nowadays, your company can buy these, and what happens is on the screen here, this one-time password constantly changes every few seconds, and it's synchronized somehow with the server, so that the presumption is if I am carrying around this device and I type in when prompted this particular code, and that code matches the synchronized code that's on the server, I should be allowed into the account, because the presumption is that it's indeed David carrying this around and not necessarily some adversary. It might also be possible to plug it in as via USB or some other technology, thereby removing the human from the formula so that the device itself can just authenticate using special software on the system instead. Nowadays, though, you can download special apps, whether it's one from Google or other companies, that allow you to manage all in one place all of these one-time passwords that you might automatically see updating on the screen, and you can type any or all of them in when you're actually prompted by a website or app. But even in this space of one-time passwords and possession factors, it's worth keeping in mind that some of these technologies are more secure than others. Now, it's very common for websites or apps nowadays to want to send you one of these one-time passwords via text message, for instance. And you receive it via SMS, and then you can type in that 6-digit code, as is often the case. More secure, though, would be something like an actual app that you install from the App Store or the Google Play Store that actually talks directly to some server and does not just go over the cellular phone network. Why is that? Well, as you might know, in your phone is typically a SIM card, either a physical card, a little chip, or nowadays it might actually be built into the phone as well. But that SIM card has a unique identifier. And when you sign up for phone service, typically with a company, they need to know what the unique identifier is of your SIM card, be it something physical or something wired, hardwired into your device. Why? Because that's how they associate your phone number with that specific device. The catch is that it's all too possible, and in some cases all too easy, to trick even the phone companies into swapping your SIM. Not necessarily doing it physically per se, but convincing the mobile phone carriers to update their system to say, oh, David now has this SIM card and not that original one. That is to say, if I'm an adversary and I just have any old phone with any old SIM card and I figure out what the unique ID is, and maybe I call up David's mobile phone provider and I somehow convince them that I am David by tricking them into believing it's me, as by telling them all of that personal information about myself, I might be able to convince them to swap my SIM card, the adversaries, with what is already on file. The implication of that is that when David subsequently gets text messages, they don't actually go to me, the real David. They go to the adversary's phone as well, because they're tied to that SIM card. So in general nowadays, if you have a choice using some website or app to use SMS or text-based messaging versus a native application that you install onto your phone or other device, you should generally prefer the latter. Some first-class piece of software that actually uses push notifications or your data plan and does not rely on SMS text messaging because of this potential threat. So, What are still other threats when it comes to these systems? Well, it turns out that it's very possible, unfortunately, for adversaries to somehow get software, malicious software, otherwise known as malware, onto your Mac, onto your PC, perhaps even onto your phone. This might be because you installed a piece of software that you shouldn't have trusted. This might be because your phone or your device is infected with something like a virus or a worm. But in general, you might be vulnerable to malware, including software that logs all of your keystrokes. Key logging refers to exactly that. Some piece of software that most likely maliciously is literally recording everything you type or everything you tap into that device. And what does this software do with those keystrokes? Very often it will upload them, if there's an internet connection, maybe to a server that the adversary controls. Now, what's the implication of this key logging threat? Well, if you're typing in your username, that's not such a big deal because those are generally public. But if you're typing in your password and that's being automatically uploaded to the adversary server, now they know your username and your password. Worse, if the adversary also sees you typing in that 6-digit code, your one-time password that you might have received even from your phone or some other device, if they are fast enough and smart enough and figure out how to log what you're typing, send it to the server, perhaps even before you yourself hit enter, maybe they can use not only your username and your password, but even that one-time password by pretending to be you on their own phone or their own laptop or desktop, typing in, or more realistically, automatically through software, typing in those same values and accessing your account even before you had a chance to do so as well. Now, what are the defenses against that particular threat? Really just to be generally paranoid about what computers you yourself use. For instance, nowadays, I will rarely, if ever, actually use like an internet cafe's computer or even a lab computer here at Harvard's campus, or frankly, even a friend's computer, because I don't know just how safe they are when it comes to best practices using their device on the internet. I will, in general, only log into websites and apps on my own personal devices, which isn't to say that I too am perfect, but rather at least I'm reducing the probability that I lose control over my data by using some other device that I myself don't oversee by that person, that owner, not themselves adhering to best practices. Now, even then, I will admit that using key logging and getting it up to an adversary server and inputting it faster than you might is a pretty sophisticated and difficult threat, but it's worth keeping in mind and realizing that these are certainly theoretical attacks, and if you yourself are targeted for some reason, these are absolutely things you should be mindful of. So in general, if you have the luxury of only using your own device and not some shared device, that too tends to be best practice, I would say. All right, any questions on these here attacks?
Regarding using long passwords, do you recommend using like Google passwords or Apple passwords for the system to remember the passwords for us?
A really good question. Short answer, yes, but we'll come to that in more detail in just a few minutes. So what are other attacks that we should be mindful of? So this one has kind of a funny name, but there's this attack known as credential stuffing. And we've come across reference to this already in this discussion thus far. Credential stuffing, a credential is something like a username and password, refers to the process of an adversary having found a whole bunch of usernames and passwords, maybe online, maybe in some database that they or someone else attacked and posted for the whole world to download. Credential stuffing means not using dictionaries, not using brute force, but just literally using a list of already known usernames and passwords, maybe from some other application or website, to try to stuff them into a different website to see if, well, maybe if David's using this username and password over here, with high probability, he's probably using the same username and password over here. So credential stuffing is the threat that I dare say many of you are vulnerable to. Now, you don't need to raise your hands and admit to this right now, but if you are using the same username and the same password on 2 websites, 3 websites, 30 websites, all websites, you are today vulnerable to this attack. To be clear, if any one of those websites or apps is compromised by some adversary and they figure out all of the usernames and passwords on that system, what a smart adversary is going to do now is to try that same username and password they found for you on Amazon, on Gmail, on any other website or app that you, with high probability, might be using just because those services are popular. So what's the takeaway? Ideally, if you want to be immune to this kind of credential stuffing attack, where someone takes your credentials over here and tries to stuff them into these other services over here, you have to use different credentials on each and every website, on each and every app. You cannot, should not be reusing the same password on multiple websites or apps. Username, yes, especially if it's your email address, but passwords, no. Now, this is admittedly easier said than done, so we'll see soon how we can try to achieve this, avoiding credential stuffing by having unique passwords, by at least having some help when it comes to managing the same. But there's another attack, too, that's come up indirectly here already, known as social engineering. Social engineering isn't a technical attack per se, but rather a social one, an attack among humans. For instance, let me go ahead and suggest the following. If you have a piece of paper near you and a pen or pencil, go ahead and write down, if you could, on that piece of paper, one of your passwords. Any of them is fine. Just go ahead on this piece of paper in front of you and write down one of your passwords, including any letters or digits or punctuation. Now, I'm seeing in the chat some resistance. I'm seeing some heads down, though, and some scribbling, which is exactly the point. Why would you take my suggestion and write down your password on a piece of paper? Even though I'm presumably someone you should trust in a cybersecurity class, those of you who reached for a pen or pencil, just wrote down one of your passwords on a sheet of paper, were just socially engineered because a circumstance was created where you believed or trusted the person that was asking or telling you to do something, and you took at face value that you should do that thing. Moving forward, if any teacher ever asks you to write down a password on a piece of paper, one takeaway for today is just don't do it. That would be social engineering. And in general, if someone calls you on the phone, sends you an email, and tries to get information from you, even if it seems and sounds legitimate, moving forward after today especially, you should always have a healthy skepticism, if not just enough paranoia to be healthy in the interest of protecting your account. Moving forward, if you had someone ask you something like that, or even a little more nefarious, trying to figure out what your first pet was, or something, should kind of perk your ears up. Your spidey senses should go up, so to speak, in the context of Spider-Man, and you should wonder, wait a minute, why do they need that information? Let me see how this plays out before I share anything about myself. And indeed, if you were, bless your hearts, but if you did jot down your password with a pen or pencil, remember that feeling of being duped, because you do not want that to happen when it actually matters. Now, after this, now I know you'll believe nothing I say, but go shred or tear up or flush whatever piece of paper has that password on it. The point is not to share it with anyone, just to prove that particular point. Now, beyond social engineering, there's another threat that's a variant of that, but is more technical in nature, and that is phishing. And most of you probably have heard about phishing in this context, and you can think about it sort of physically like going fishing, but trying to hook a sucker, someone like me or you, who is duped into providing information that they shouldn't. And this very often happens via emails. Odds are, if you go through your spam folder sometime, you will see emails that seem to be coming from PayPal.com, or seem to be coming from Google, or maybe a politician or the like. And very often those emails are encouraging you to click a link and maybe make a donation. Click a link, maybe change your password. Click a link and verify your information. Phishing is all about trying to use social engineering, in this case in a technical way, to try to convince you through very convincing looking emails and even websites that it is a legitimate email from PayPal.com, or it is a legitimate email from a politician, or it is a legitimate email or request from a teacher here at Harvard. But it's not. What they're trying to do, the adversaries in this case, are prey on your trust for those certain companies or persons. They're trying to prey on your comfort with familiar user interfaces, things that you've seen before. But unfortunately, it's all too easy for an adversary to make a very official looking email, to make a very legitimate looking website, even one that looks identical to PayPal.com, identical to Gmail or other services. And frankly, if you take some of CS50's other courses, kind of boils down to copy and paste in the simplest of scenarios, just copying and pasting some legitimate website and pretending that you own it too. So how might phishing manifest itself in the real world? Well, consider one of those social media posts online that tend to invite you to comment with your favorite song from childhood. Sometimes those posts have like 1 million responses from people you know and don't even know. But more than being interested in what your childhood favorite song was, those posts are very often phishing for personal information. Because suppose that you, or at least someone among those comments, is actually using their favorite childhood song as their answer to some website or app secret question. Now the author of that post, not to mention everyone else, knows the answer to the same. So how else might phishing manifest itself in the real world? If you were to visit a screen later today that looks a little something like this, well, this looks like Gmail's login page, at least here in the US when using English. And frankly, I've seen this so many times that I might be inclined to just blindly type into the form my email address, and then after that, probably my password. But it's important to begin to develop an intuition for, a suspicion for, when these sites might not be legitimate. How might you do that? Well, you should minimally be looking at the URL bar and making sure that it is gmail.com or probably google.com or whatever google.country code, depending on where you live in the world. Making sure that it looks legitimate and that you've actually been there before. When you hover over links, you can very commonly in your browser look at the bottom left-hand corner or some corner of your screen, and you can see what URL a link will actually take you to. Even though the words on the screen might say something, the actual link might take you somewhere else. Now, even then, it's hard sometimes to discern these kinds of things, but these are just best practices. You don't need to be so worried that you don't go anywhere on the internet, but you should learn to keep an eye out for these kinds of things. And in general, with phishing, rather than trust any link in an email that you receive, especially when it's something private, like a bank account, something medical, something personal, well, that's fine. Open a new tab and manually go to paypal.com, enter, or manually go to gmail.com, enter. Don't just blindly trust these links. Now, here again, we see a trade-off between usability and security. It's a little annoying if I can't just click on a link and go to the place I want to go. You have to manually open the page, type it in manually, and so forth. But again, it depends on what's now more important to you, the usability of that service or the security of your account therein. This is even worse when this is even more worrisome when it comes to two-step verification. And Google takes some liberties with the wording here. This is usually best described as two-factor authentication. But again, the most sophisticated of adversaries, theoretically, if they sent you a phishing email, tricked you into visiting a website that looks like Gmail but is not Gmail, they could theoretically even prompt you for a two-factor code like this. And then if they're smart and savvy enough with code, they could automatically now send your username, your password, and a two-factor code maybe to the real gmail.com, log into your account, change your password before you even get up and running therein. It's a more sophisticated threat, and it's not something you need to worry about as much, but it's this principle of not just trusting screens and requests that are presented in front of you. You should have this healthy skepticism and at least some technical savvy to know how you can decide for yourself, yes, I am comfortable with proceeding with this step. Now, there's another type of attack, too, that's more sophisticated and not one you need to worry about as frequently as some of the earlier ones, but they're generally known as a machine-in-the-middle attack, whereby if you're on the internet, there are, suffice it to say, many other machines on the internet, very often between you and whatever website or app you are visiting. Often those machines might be things like routers, servers that internet service providers, companies, universities, maybe even your own home owns and controls, but all of your data is passing through those machines in the middle, so to speak. If any of them are malicious and are maybe storing your data, looking at your data, it's possible that you might not be having secure communications with the other end unless you are using certain defenses. And in our focus in this class on data, we'll talk about cryptography and encryption and building blocks via which we can mitigate attacks like these. But it's worth knowing about this general idea that even though it feels like it's only you and Amazon.com, it's only you and PayPal.com, it's only you and WhatsApp, there are many other machines in the middle. And if you're not using the best practices, and if you're not keeping an eye out for those things suspicious, those machines in the middle might actually be there to attack you, to take your data, to change your, to access your accounts, or something more as well. So there's a lot of attacks out there, and at this point you might be feeling a bit defeated, but hopefully we've presented at least enough defenses thus far, and there are still a few more to come. But let's consider now kind of the source of a lot of these problems. Unfortunately, it's you and it's me. Like, the whole story here today started with you and I are not very good at choosing passwords, and we generally meet the minimal requirements, not necessarily the best practices. But again, there's these sociological side effects of certain corporate policies or technical policies that do induce this trade-off between security and usability. And it's one thing for me to preach here, so to speak, and say, yes, you should use long, complicated passwords that are really hard to guess with letters and digits and punctuation still, maybe even 64 characters if you want to be really secure, even if it's a longer phrase. But honestly, there are also these pressures on me not doing that. It's annoying to type in 64 characters. It's annoying to type in 8 characters if a lot of them require uppercase, lowercase, punctuation, and the like. And honestly, I have dozens, I have hundreds, maybe thousands of accounts nowadays on the internet that have accumulated over time. What am I going to do if it just gets difficult to remember these things? Well, like someone you yourself might know in your company, you might walk by their desk and see on their monitor the familiar yellow Post-it note with one or more of their passwords actually on it. Maybe worse, you open their desk drawer and there's a whole printout of all of their username and passwords. Or even beyond that, maybe they actually have a text file or an Excel file, a CSV file on their computer, thinking, well, at least it's all digital, but it's just sitting there on their desktop. And worse, maybe it's called passwords.txt or the like. But that's a very real side effect of having policies and technical constraints that make it harder to use systems. So what are some other defenses that either you can use or maybe companies can use or offer to make things better? Well, a solution to some of these problems might be this: single sign-on, or SSO. So single sign-on refers to an ability to sign up for, to log into one's website using an account that you already have on another website. And very often the account that you use is one of the big ones, one of the popular websites or applications out there. So for instance, if you log into this representative website here, what you might see is, yes, a form field via which you can type in your own email address and your password to log in. Or if you prefer, you can just log in with Google, or you can just log in with Facebook, or you can just log in with any number of other services if this website or application supports it. Now, what's the motivation here? Well, one, it's still backwards compatible, so to speak, with the very familiar approach of just let me register with my own email address, let me come up with my own password and be done with it, especially if I don't use Google or Facebook as a customer. But the upside of offering these solutions, especially for popular websites like Google and Facebook and others, is that if I already have an account with Google or Facebook, and hopefully I already have a good password for both of those, because those are important to me, and better yet, I ideally have two-factor authentication enabled on one or both of those, because again, they're important accounts to me, wouldn't it be nice for this new website to let me, one, just log in with my existing account so that I don't have to waste time signing up for yet another internet account. Two, I don't have to remember a new password that's going to be difficult to remember and so forth. And so it decreases friction. It increases usability of the system, and ideally, it increases the security of the system in this case as well. Why? Because if you're doing a good job protecting at least these most important personal accounts, then this website stands to benefit from those same best practices on your part. Now, what is actually happening here? When you click login with Google, login with Facebook, you should see the Google login screen or the Facebook login screen respectively. You should literally be redirected in your browser to google.com or facebook.com or one of their international domain names instead. There, you'll type in your same username and password as usual for Google or Facebook, but that password is not given to this new website or this third-party website you're visiting. Rather, using a technique known as cryptography and encryption and some fancy math, essentially, the username with which you log in is sent back to this third-party website, but not your password. Just a confirmation that, yes, David successfully logged into Google or David successfully logged into Facebook. Therefore, you can trust that his username is malan@harvard.edu or whatever it is I typed in to log in there. So using single sign-on benefits not only you potentially, but also the website or application by making it easier for you to register and or log in subsequently as well. Now, where does this leave us ultimately? Some of you might already be thinking, well, what about using a password manager? And some of you might be thinking, what is a password manager? So let's emphasize this one perhaps the most. Increasingly, best practice is to use a piece of software that manages your passwords for you. Thankfully, there's going to be an even better solution than this on the horizon. But for now, minimally, if you're not using a password manager, you probably should be. If you're using the same password on multiple sites or applications, and thus you're vulnerable to credential stuffing, you should probably be using a password manager instead so that you can change all of those accounts to have unique passwords. But this piece of software known as a password manager can remember those passwords for you. If you are in the habit of choosing very easy passwords, because it's just better for you to remember, you should probably start using a password manager, because beyond remembering your passwords, these password managers also make it easy to generate new passwords. You click a button and essentially it will generate a password that's however short or long that you want, with some uppercase, lowercase, symbols, numbers, whatever it is a website requires, it will just generate it for you. And better yet, it will then save that generated password for you, so you, the human, do not need to memorize it, and you, the human, certainly don't need to write it down on a Post-it note or any other file somewhere else. So password managers literally do just that, and they have even more features than that. Generally, if you're using a password manager and you go visit a website for the second time or the third time, you can typically hit an automatic keystroke that will just automatically log you in. It will fill in your username and your password, but better yet, it will only do so if you're on the real gmail.com or the real facebook.com or the real paypal.com. These password managers also remember the URL at which you created or last used that username and password, so that if you are somehow subject to a phishing attack, you've been tricked into clicking a link and going to a website that looks like Google, looks like Facebook, but actually isn't, the password manager will ignore your keystrokes and not actually log you in, pasting into that form your actual username and password, because it doesn't recognize that same URL. So there are a lot of upsides of these password managers. The one catch is that the onus is on you to remember one primary password that protects your password manager itself. That is to say, if this is a piece of software that stores all of the dozens, hundreds, thousands of usernames and passwords that you have, you are putting proverbially all of your eggs in one basket, so to speak. That is, you want to protect this password manager with probably the best password you've ever come up with. This should probably be long. It should have some complexity. It should be a little annoying perhaps to type in, because you don't want an adversary to get in and get access to everything else, but it's just one password that we're really asking you to pick really well and reasonably long, so that you're protecting everything else. Now, these password managers are a little different than what you're probably familiar with in your own browser. It's been common for years for browsers to remember your username and password by just showing you like bullets, like ... in the form field, so you can just hit enter. That's fine, but that information is often associated only with that one browser. It doesn't propagate to your phone or another device that you're logged into. It's not easy to share it with someone else if you have a family account, for instance, or something like that. So password managers often offer additional features features beyond that and really protect all of the things that you're using and also help you generate those same passwords. Fortunately, thankfully nowadays, these are increasingly standard. There are third-party options that you can find online or even purchase, but they're increasingly built into our own operating systems, which if I had to choose, especially for a less technical audience, using what comes with your computer from the major manufacturers is probably a good thing, as opposed to going third-party, unless third parties offer you additional features that might be especially beneficial in companies and families or the like. So Apple has what they call their iCloud keychain, via which you can not only save passwords on one device, they can propagate securely to your other device, like your phone. Google has its password manager, Microsoft has its credential manager, and there's certainly other options as well. The takeaway for today, though, should be that if you're not using a password manager, it's probably time to start doing so, at least for your most important accounts. Maybe things that are particularly personal, medical, financial, anything where you or your family would really be upset if that account were somehow compromised. At least figure out how to start migrating those kinds of accounts to a password manager, and also enable some of our other best practices like two-factor authentication. Better yet, don't just enable two-factor authentication. Don't use SMS if you can. Instead, use like a native application on your phone or even a physical key fob, just to decrease the probability of those threats. And I would encourage you too, because it's one thing to sit in on a class like this and be like, oh yeah, I should do that. But then it just feels like so much work to go and change all hundreds or thousands of my accounts. Again, take baby steps. Bite off the easiest, most important accounts first. And over time, the next time you log into that other website, OK, go ahead and change the password to something better, put it in the password manager, and be done with it. The next time you go to another website, do it that one. You can do these things incrementally because, again, with this advice, I'm just trying to help you personally strike this balance between usability and security. Because if your takeaway is, I have to go change 1,000 passwords tonight, you might not realistically do it. So better would be to change a few of them and chip away at this problem over time. Let me pause here and see if there are any questions.
If a password manager and 2FA is so helpful, so why we are using antivirus for websites?
Oh, so you should certainly be using antivirus for other reasons that we'll talk about in another class. Viruses, worms, and malware can do any number of bad things, including encrypting your data, deleting your data, sending spam from your computer. There's many reasons you want to run it instead. However, if you have malware, like a virus on your computer, and it's logging all of your keystrokes, theoretically, you could still be vulnerable to attack if they are also logging your two-factor code, maybe because you get distracted, you don't hit enter fast enough, and they can use that too. It's a lower probability threat. It's a theoretical one, but also in the interest of best practices, you don't want any software on your computer that could be doing bad things anyway. You just want to raise the bar as much as you can to these adversaries without making your own accounts unusable. Another question.
Oh, yeah. I had a question about social engineering, if that's fine. And we know that the rise of the AI technology, now AI can record your voice and sample it. And that could be a real threat in social engineering, because now someone can mimic your boss and call you, or someone can mimic your voice and call your bank. So is there a way to combat this, or is there any technology to prevent this from happening?
That's a really good question, and another piece of advice I should reflect back. If on any of your accounts, particularly bank accounts, you are using voice recognition technology, whereby when you set up the account, you were prompted to say a phrase into the phone, for instance, to evoke an old movie called Sneakers, "My voice is my password," you should disable those features and stop using them, assuming there's an alternative like two-factor authentication, whereby they send you a push notification to an app or the like. The reason being exactly that. As you've probably seen in this age of AI, there are technologies called deepfakes, whereby you can generate video, but also audio of people. This is very commonly done for celebrities, for politicians, and voices that you see a lot on the internet. But it would not be that hard if someone has access to voice recordings of you to use some software or some app to generate you saying, "My voice is my password," even though you might not have said that since the time you set up the account. And so your accounts too might be compromised. So my own advice there would be, don't use voice-based recognition anymore if there's a better alternative available. Other questions?
Doesn't having one password manager? So figuratively, keeping all your keys in one safe defeat the purpose of having different passwords? Because if you lose that one key to your key safe, all is gone.
It's a really good intuition, and that's exactly the trade-off to think about. I would consider in deciding for yourself, if you want to take that advice, what the alternative is. Because if you're using pretty easy to guess passwords everywhere, like this is probably a net positive to move to a password manager instead. If you're reusing the same password on a lot of websites and apps, this is probably a net positive to switch to a password manager instead. If, however, though, you've actually been a very good internet citizen and you've been choosing hard to guess, unique passwords for all different sites, they're not written down on a Post-it or easily accessible, then this might be a net negative for you to put all of those eggs, so to speak, in one basket, thereby making them more vulnerable. From experience and from sort of the head nods and admissions that we get from students over the years, I guess that most of us in this room would benefit as a net positive from a password manager. But there, too, you should decide for yourself. And again, one of our lessons for today is don't just believe something some guy on the internet told you. Decide for yourself based on these trade-offs, these upsides and downsides. Now, password managers are not all upside. Indeed, if you lose or forget that primary password, you might lose access to all of your other accounts. Fortunately, there is an alternative that's increasingly available on websites and apps known as passkeys. And what's nice about passkeys is that moving forward, it will be your Mac, your PC, or your phone that generates a passkey for a new website or app for which you're registering. You yourself don't have to remember what that passkey is, and indeed, it isn't even just one value. Rather, it's a pair of values, a private value and a public value that have a mathematical relationship between the two. And those two values are used the next time you try to access that website or application. Your Mac, your PC, or your phone will use those values to automatically authenticate you thereafter. And better yet, those values are synchronized as needed across your devices so that you can use your Mac and your PC and your phone or any other such devices to authenticate. But to better understand these passkeys, we'll need to know a little something about the world of cryptography. And so for that, we'll wait for our discussion of securing your data. So more on that next time. All right, this is CS50's Introduction to Cybersecurity. My name is David Malan, and this week we'll focus on securing data. Last week, recall, we focused on accounts, and particularly one of the mechanisms via we protect our accounts is generally by way of these things called passwords. But we focused last time really on our having the responsibility to keep these things secure. And yet there's another party involved whenever you have an account with a username and a password, and that's the server or app that is actually storing that password in some form long term so that you can actually authenticate yourself, that is, prove to this application or website that you are who you claim to be. Well, in the simplest form, perhaps these servers that are storing our usernames and passwords for which we have registered are maybe doing something very simple like this. For instance, if a website or app has two users at the moment, at least, Alice and Bob, and suppose for simplicity that Alice's password is Apple and Bob's password is banana. You could imagine that website or that app simply storing in like a very simple text file these key value pairs: username, colon, password, new line. Username, colon, password, new line. And in fact, that's actually very commonly how passwords are stored on systems, at least certain operating systems like Linux. Not necessarily as simply as this. They often have a little more information off to the right there. But in essence, it's the username and password. But this wouldn't be a good thing to store the passwords exactly like this. Why? Well, suppose that this website or this app and its database are somehow hacked by an adversary. That is, someone gains access to that file containing these usernames and passwords. Well, at that point, they literally have everyone's username and password. And we talked last time about attacks like credential stuffing, whereby an adversary, once they know your username and password on one system, they can try stuffing that username and password into other systems, other websites, other apps, just in hopes that you are unfortunately using the same username and password elsewhere as well. So this is generally not a good thing if an adversary gets access to everyone's usernames and passwords. And even though, of course, in an ideal world, that would never happen, we should probably, as the administrators, as the creators of this website or app, we should probably do everything we can to at least minimize the fallout, the downsides, the damages that might result if, and dare say when, our database or this text file here are somehow compromised. So how might we go about doing that here? Rather than just storing apple and banana in clear text, so to speak, literally in the English words themselves, why don't we go ahead and employ a technique known as hashing. Now, if you've studied computer science before, you might actually know this phrase in the context of hash tables and data structures. Well, it turns out the idea in this world of securing data is very similar, and in fact, this is a technique that's incredibly common for solving all sorts of problems. Well, what do we mean by hashing in this context? Hashing is the process of taking a password as input and somehow converting it to a so-called hash, or hash value. Now, these hash values don't look like English. They're typically strings of text that might have letters, might have numbers, but they're generally of some fixed length, typically. And in this case here, when we go about taking our password as input, converting it somehow via an algorithm or some code that we wrote, we want to convert it into this hash value and then store that hash value in that database of passwords instead. So here's a proverbial black box, and let's stipulate for the moment that I have no idea how hashing works, but I do know that this box can do it. So how do I think about this process? Well, generally speaking, there's going to be some input to this box. Ultimately, I want to get some output from that box, and what this box really represents is, in fact, a hash function. You can think of this as a device, like some kind of machine. You can think of it like a program, some piece of software, or you can even think about it as a mathematical function that operates simply on numbers coming in as input. In fact, if you're mathematically inclined, though we won't use this syntax often, you can think of that hash function as being represented by f. You can think of the input as being represented by x, and you can think of the output of this process as being so-called f of x. If not familiar with that notation, that's fine, but this is directly connected hashing to basic mathematics as well that you might encounter before long. But what we care about is passing into this black box a password and getting out a hash, and then storing that hash and not the password in our database or text file of usernames and passwords. So how might we go about doing this? Well, if I were to provide apple as an input to this hash function, let's think about the simplest hash function possible that doesn't output apple, but some representation of apple that I can eventually store in that database. So I'm going to propose very simply that maybe the simplest hash function we can come up with, and indeed, if you've studied computer science or taken CS50 itself, you might recall that we can hash our inputs on like specific letters therein. So apple starts with A. So you know what? A is the first letter of the English alphabet. So I'm going to create a hash function here pictorially that outputs 1 whenever the input happens to start with an A, as does apple. Meanwhile, if we pass in banana, I'm going to have this hash function output 2 because B is the second letter of the English alphabet. And ... we might get to cherry or other passwords as well that might output 3 and beyond. And you could imagine doing this for all letters of the English alphabet. Now, unfortunately, this isn't the best hash function because it's fairly simplistic. And in fact, I can quickly think of some other fruits like avocados that also start with A and that would give me the same hash value. And that's actually a characteristic we'll come back to whereby when you hash values, there can actually be ambiguities potentially, whereby two inputs might actually have the same output. And we'll consider eventually what the implications of that might be. But for now, I dare say that's a little too simplistic. And what might be better than outputting 1 or 2 or 3 is a little something more cryptic, because that's just too helpful. That's too much of a hint. If I see that your hash value is 1, I at least know that your password now clearly starts with an A, which means at best I can do 1/26th the amount of work to figure out what it actually is. So we want these hashes generally to be a little weird looking and really unguessable and not leak any information. So for instance, a very common older hash function for Apple might actually output this, ... EKWXA83DHIA with some mixed uppercase and lowercase letters therein. Now it looks weird. You probably can't and shouldn't see any kind of pattern in there. There is a fancy math formula that took as input Apple and outputted as its hash value that string of text there. But in and of itself, it doesn't really leak any information like the number 1 or 2 or 3 would. So we've already made an improvement. Banana, meanwhile, would look like this. And cherry, meanwhile, would look like that. So notice that these values are indeed quite different. So using this better hash function, I claim, that doesn't just look at the first letter of the alphabet, but looks at maybe all of the letters in the input, C, H, E, R, R, Y. In this case, we can probably come up with something more interesting, more cryptic looking, if you will, like the values we've just seen. So let me propose now that what we should do in our database of passwords is not store Alice, Apple, Bob, banana, but let's instead store the hashes of Apple and banana respectively. So instead in this password database, I'm going to store this instead. The exact same values that we just saw coming as outputs from that black box. But in this case now, I'm storing in my database of passwords usernames and hash values. Now, why is this perhaps a good thing? Well, one, if someone now attacks this server and somehow gains access to all of these usernames and hashes, what they don't have is an entire list of passwords. So they can't quite as easily go about credential stuffing and figuring out maybe if this database will give me access to my accounts somewhere else. I'm at least creating some work for the adversary. But at the same time, I feel like I've kind of broken the whole system because previously, presumably, when you log into a website or app and you type in your username and then you type in your password, what does the website or app probably do? Well, once that username and password are sent over the internet, typically to that server, well, the server probably compares what you typed in against the username in their database or their text file, and the server compares what you typed in as your password against whatever password is in their database. But now we have a problem. We have you typing the username, and we do have the username still in the database. Case in point, Alice and Bob are still here. But what we don't have is Apple and banana. We've replaced those all together with hashes. So even if you type in, or Alice types in Apple, well, we don't want to compare APPLE to this because it obviously doesn't match. And Bob's banana, we don't want to compare against this because it's not going to match, and so forth. So what can we do? Well, the way authentication typically works on the server side when using hashing is as follows. When you first create an account or register for this website or app, you type in, if you're Alice, Alice, enter, and then Apple, for instance, enter. That username, Alice, that password, Apple, are sent to the server. But what the server does before saving the username and password is it runs that hash function on Alice's password, which is Apple, converts it thereafter to this value, and stores Alice's username and the hash of Alice's password only, and throws away Apple. It deletes it, it forgets it in memory. What then happens next? Well, the next time Alice tries to log into this website, maybe the next day, a week from then, a year from then, for the second or third or more time, what happens? Well, Alice types in Alice as her username, hopefully Apple as her password, hits enter. Those get sent to the server as usual, and obviously the server can't just compare username against username and password against password because it doesn't have the password in its database. So what can the server do? The server can repeat the very same process, taking Alice's password as inputted, APPLE, run it through the exact same hash function a day, a week, a year later, and then compare that resulting hash value to whatever is stored in this text file or database. And now, admittedly, we're creating a whole lot more work for ourselves, but it's not that big a deal because this is just a math function, or if you know how to program, it's just a few lines of code that you've written in software that converts passwords to hash values. And honestly, nowadays, you wouldn't even be rewriting most of this code yourself. You'd be using a library, third-party code that someone else smarter than you maybe has written and gotten it just right, no bugs or mistakes. So you're just relying on someone else's code anyway to achieve this goal. But the upside now, to be clear, is if this file is compromised somehow, the server's hacked into and this data is leaked, at least they only know the usernames on your system, not the actual passwords. Now, let me pause here and see if there's any questions on this technique of hashing for passwords specifically.
you said yourself, we are using libraries more often than write the hash functions ourselves, if we are not taking the course on CS50. So then it's easy to hack these hashes, right? Because we can go through 10, 50, I don't know, hash functions that are available in the libraries. And then you can reverse the hash results. Is that right?
Almost. You can do exactly what you described first, whereby you use the same library, the same code, to create hash values, to then compare those against what's in the database. But generally, these hashes are not reversible per se. You can compare them, but you can't reverse the process for reasons we'll come back to. But your intuition is right. And so really the takeaway here is that we haven't made our system absolutely secure. We've made it relatively more secure. Why? Because we've increased the cost to the adversary, to the hacker. They now have to do more work to figure out what the actual passwords are if they want to benefit from this hack. So again, it just raises the bar. It does not keep the adversary necessarily out or even stop them from figuring out one person's password, but it might take them a lot more time. It might take them a lot more resources like server or cloud costs or money, or it might even heighten the risk before they actually are successful. How about one other question here on hashing?
If the password is intercepted before after the website is hacked and the password is intercepted before it's encrypted, so wouldn't that pose a problem?
Yes, absolutely. Then all bets are off. Everything we just discussed is not useful at all if the adversary has actually intercepted the password before it has even been hashed. Now, thankfully, there's going to be solutions to that problem too, and we'll come to them today. But for now, focusing only on hashes, it solves one problem, but not all. In fact, it turns out that those attacks we talked about last time with respect to our accounts are still possible. You can still use a dictionary, for instance, of English words, or better yet, a dictionary of English fruits, and you could, one fruit at a time, run each of those values as input into the same hash function, the library or code that you're using to achieve this, and then that's going to give you one hash value after another, and you could compare each of those hash values against whatever is in the database or the file of passwords that you, the hacker in this story, might have actually stolen somehow. You have to do more work, though, because it's no longer as simple as just comparing apple against apple and banana against banana. You actually have to do some work. You have to do some computational work. And if the file is only a few values, of course, not a big deal. If it's thousands or millions of rows, it might actually take a lot more time, energy, and effort. So again, we're just raising the bar, but not keeping the adversary out altogether. And even if you don't have a dictionary available, and even if the passwords are not all fruits in English, well, you can still, as the adversary, resort to brute force attacks. And you can try even the simplest of passwords like 0000, or maybe 8 zeros instead, and you can hash that and see what the resulting hash value is and compare that against what's in the database. Then you could try 0000, 0001, hash that, compare that against what's in the database, and then move on to the next and the next, doing this not just for numbers, but for letters as well. A, hash that and compare. Eventually, apple will be on that list. Eventually, banana will be on that list. But there, too, the brute force attack is still going to take some amount of time. So it's just increasing the cost or the complexity for the adversary in this particular case. But there's yet another threat that's possible in the context now of the hashes, which is worth knowing about. There's a term of art known as a rainbow table, which is a very beautiful way of saying that adversaries in advance might have already hashed all possible English words in a dictionary. Adversaries might have already hashed all possible passwords of length 4 or 5 or 6 or 7 or 8 or something else. And maybe if they have a big enough hard drive, they are storing a big table, like an Excel file or a CSV file of all of the words that they've tried, all of the passwords they've tried, and all of the hash values they've already computed. Then it's even easier. Then they don't even need to do a brute force attack per se, hashing and hashing and hashing and hashing. Then they can just compare. Because indeed, a rainbow table simply contains all of the passwords they've tried, all of the hash values they've generated, and so they just compare left to right whatever the user typed in against the hash value they've already computed. Now, for certain hash functions, This threat of a rainbow table is just not feasible. You might need terabytes or petabytes of data, which means a lot of hard drives and a lot of money. So there are potential downward pressures on this kind of an attack, but it can certainly speed things up. Certainly if you're pre-computing, that is pre-calculating some of the hashes for at least words in an English dictionary, and certainly some short list like all of the fruits in the world. But there's another problem that we might encounter on the server with regard to our passwords. Alice might have a password of apple, Bob might have a password of banana, but suppose that both Carol and Charlie have a password of cherry. And just by coincidence, they both chose the same password and are in this same database. Now, we've already concluded, I think, that we definitely don't want to store the plain text passwords. We don't want to store literally in the clear apple, banana, cherry, and cherry, because it's just too easy for the adversary to do bad things with it. So we at least want to hash this, but here's where hashing can kind of leak information, so to speak. If I go ahead and use the same function I've been using to hash apple and banana and now cherry, what do you notice about Carol's and Charlie's hash values? Curiously, but maybe not surprisingly, they're exactly the same. That's, after all, how functions typically work, be it in math or in software, in code. If you pass the exact same input, unless there's some randomness going on, you're going to get the same output again and again. Now, why is this a big deal? Well, if some adversary attacks this database and gains access to all of these usernames and hashes, we have leaked information in the sense that the adversary, just by glancing at this file, knows that, okay, I don't know what Carol's password is or what Charlie's password is, but I know it's the same password. And that alone might be enough information to figure out with higher probability what it is. Maybe Carol and Charlie are related. So maybe you focus on words or numbers that are common to both of them. Maybe there's some information that's implied by this if they both are in that, they both like the same TV shows. They both like the same movies. You can try to find in your mind maybe the intersection of information that might lead you with higher probability to figure out, without brute force even, what Carol's password is and Charlie's password is. So this is a common problem, and we only have 4 users in this database. You can imagine having many more. Odds are some of us are going to have the same username, not the same username, some of us are going to have the same passwords. In fact, without raising your hands or admitting to this for the whole world to see, do any of you have a password of 1, 2, 3, 4? In some website or app? Maybe a little harder. 1, 2, 3, 4, 5, 6, 7, 8. You know, something very simple like this. Maybe it's an account you don't really care about. Well, that's a perfect example of where, if you have an account on the same system as someone else here in the classroom, you're going to have, in that database presumably, the same hash values. And that might be alone enough information to leak and increase the probability that you, and not Alice or Bob, are actually compromised with respect to your account. So how can we fix this? Well, it turns out there's another technique in the world of data that we can use to perturb this process. And you can think of it metaphorically as like sprinkling a little bit of salt on the hash function so as to change what its output is. It's not random per se, but you are perturbing the output so that it's much less likely that 2 people with the same passwords are going to have the same hash value. So how does this work? In this case before, when we passed in cherry as our input, we got the same hash again and again. But let me propose that we modify our hash function to take 2 inputs now. Not just a password, but also a salt value, so to speak. A little bit of a sprinkling of, in this case, just 2 characters, 2 numbers, 2 letters, or a combination thereof. Now this hash function that I'm describing is still going to output a hash value, but notice it's different from the one before. And even if you don't quite remember what it was before, it was not this. But worth noting is that in the output of this hash function now is the salt itself. So the salt isn't something that's meant to be private or secret or secure. It's just sprinkled in there to make sure that whatever hash value comes out of this black box is a little bit different than if you had put a different salt value instead. So for instance, suppose that for Carol and for Charlie, we use different salts. And that's the idea. Different users should have different salt values just in case they choose the same passwords. So instead of 50 in cherry, suppose that Charlie uses a salt value of, say, 49. 49 is not a number that Charlie or you or me have to pick. This is all done by the server automatically, picking a random 2 characters like 49 or 50. But notice what just happened. If I rewind to Cherry with a salt of 5, this was the hash value, the first 2 characters of which are the salt. If, though, I change the salt from 50 to 49, the hash changes completely. And it prefixes it with now 49 instead of 50. This ensures that even if Carol and Charlie have the exact same password, there's no way I, the adversary, am going to know by looking at it. Because indeed, what ends up in the file now are these 2 values. One is prefixed with 50, one is prefixed with 49. The rest of the hash values clearly are completely different. So again, the upside is this approach, where the hash function takes 2 inputs, the password and a salt, and then outputs 1 hash value, means that we're not leaking information except there is a corner case if by chance, by bad luck, the system chooses the same salt for both Carol and Charlie. Yes, there might still be information leaked. And honestly, that may very well happen if you've got thousands, millions of users. Then you're going to run out of 2-character possibilities. You're going to have to reuse salts. But the idea is that we're just trying to put downward pressure on the probability of being attacked successfully. We're trying to equivalently raise the bar to the adversary so that they are not as likely to gain access to my data or, in turn, my account. Questions now on salting or hashing itself.
Oh, I'm curious, where do we store the salt?
So where do you store the salt? The salt is actually stored in the hash value itself, according to this algorithm, in the first 2 characters. And the value of storing the salt in the first 2 characters of the hash is as follows. The next time Carol logs in, she types in her username Carol and hits enter. The server now knows, OK, I'm expecting a password from Carol. Let's see what she types in. Suppose that she types in correctly Cherry. Now, the system is not storing Cherry, so it's not going to compare literally what Carol typed in, but it is going to hash Cherry. But first, the system's going to check what is Carol's salt. And it's going to infer as much by looking at Carol's hash value and looking only at the first 2 characters by convention. Then what the server's going to do, it's going to take whatever Carol typed in, Cherry, C-H-E-R-R-Y, it's going to pass in 50, and then hopefully it's going to get back this same value here, this whole string in yellow. And if those are correct, then the Carol will be considered authenticated. By contrast, if the username happens to be Charlie and Charlie hits enter, then what the server is going to do is look at Charlie's hash value, grab the first 2 characters for Charlie's salt, use that salt and Cherry as the input to the hash function, and hope that the result is Charlie's value, not Carol's. Really good question. Other questions on salting or hashing?
Is there any sense in rehashing a password? So hashing it first a first time to get string, then rehashing it for a second string, or it's just impractical?
No, you could certainly hash the value multiple times, but a good hash function should not require that of you. Especially now, more recent modern hashes, one of which we'll look at in a moment, they should have sufficiently calculated and proven characteristics that allow you to hash it just once, and you will get a seemingly random string that represents whatever that input is. And here, too, is where I should emphasize that when it comes to this world of hashing and salting and today's other topics ultimately, these are not wheels that you or I should be reinventing unless you are the researcher or the company that's actually developing the algorithm, stress testing them, analyzing them theoretically and practically. So often in industry or the real world, when people like you and me invent our own systems for storing information, we just haven't spent nearly as much time, or we're just not nearly as sharp as some of the security researchers out there who have really given this some thought. So when it comes to all things security, let me get on my soapbox here and say you and I should not be solving these problems unless it is your full-time job or calling in life. There's just too many corner cases unless you're collaborating with a smart team. All right, with that said, Here is what hashes generally look like nowadays in practice. For the sake of discussion, I deliberately chose a fairly simple hash function that was using a fairly short salt, just 2 characters, and a fairly short hash value as output. Here, in a smaller font no less, is how Alice's and Bob's and Carol's and Charlie's passwords would probably be stored nowadays using a more recent modern hash function that, notice by the sheer length of the text on the screen, outputs a much larger value. If you're familiar from computer science with the notion of bits, zeros and ones that are used to store information in systems, these hash values use many more bits, many more zeros and ones. You and I, as humans, are seeing them as alphabetical letters and as numbers. But underneath the hood, these are just more and more zeros and ones that the computer is storing, which means it's much, much less likely that someone who steals this kind of file is going to be able to figure out efficiently what those original passwords were. And you can see, too, that for both Carol and Charlie, even though their passwords are still cherry, these 2 strings along the bottom look completely different. Except in one location here, it turns out that the scheme a lot of systems have adopted is that if you look between $ at the beginning of what seems to be the hash value, you'll see a code like Y or Y or Y or Y or other numbers or letters as well. That's a little cheat sheet that tells the system exactly what hash function was used to generate the rest of it. And that's in the documentation that you can read online for any number of hash functions. So this is to say, when you create an account on some new website or app, if they are doing things well in a manner consistent with best practices and they are being mindful of your security, they are probably in a file or in a database or some other mechanism storing values that look quite like these based on whatever password you actually typed in. In fact, just to give you a sense of how easy or difficult it might be to crack passwords, that is, figure out what they are based only on these hashes, in the case of our first hash function, whereby we had a fairly short hash value being outputted with or without the salt, turns out there's 18 quintillion possible hash values. Now, that's a lot. That's bigger than last time's quadrillion value. But with enough time, enough money, enough cloud computing, those early hash functions can be broken. That is, with enough time and energy, you can probably figure out what someone's password is. If you fast forward to the other strings that I showed you on the screen, the much longer ones that use more bits, so to speak, then you have this many possible hash values nowadays. And I actually did look up how to pronounce this, but based on reading it on my screen, I wasn't actually sure how to say the word, since this is a really big number that my mathematician colleagues could do a better job pronouncing. But given how many digits are on the screen, given how many commas are on the screen here, this is a really big number such that you and I probably don't need to worry about an adversary using brute force figuring out and still being able to figure out by the end of time what the corresponding password might be, unless there are other weaknesses in the system. Now, speaking of weaknesses, has anyone ever forgotten your password? Yes, of course. But have you ever gone to a website or app, clicked that link that says forgot password, ? In hopes of getting an email of some sort so that you can reset the password? I mean, odds are almost everyone here has experienced that. But has anyone ever clicked on that link, gotten back an email that actually contains your password so that you're just immediately reminded what it is? I'm seeing a few nods of the head. You can copy paste it then into the website. Do not use that website anymore. That is evidence of, that is a symptom of a website or application not practicing best practices. Why? Well, if it is the case that the website can email you your password, that means they can see and they know what your password is. That means this database, this text file we've been talking about, is probably vulnerable to some hacker eventually getting into it and stealing all of those usernames and passwords in the clear, no less. Because recall what these hashes are. They're generally meant to be irreversible. When you take as input apple, banana, and cherry, the output looks completely different with no obvious relationship to what those original passwords actually were. And so if that's what's being stored in the database, the company who made that website, the person who made that website or app, they should not be able to reverse that process either. Otherwise, surely the adversary can. So it is the case, and I've experienced this myself, often from sort of smaller shops or companies that maybe haven't really invested a lot of time or care into their website. If they are able to email you your original password, it is by definition not secure. And it's certainly not up to today's standards. It's just too easy for it to be compromised. So maybe minimally stop using that service and make sure you're not using that password anywhere else. Maximally, maybe send them a note explaining your concern and maybe linking them to some reference online, maybe this video, in which you explain why you have that concern. Questions then on forgetting passwords or hashing or salting?
So as you said, some companies may not be practicing these hashes and maybe practicing something very bad. So if I were, let's say, a company and I, because of my practices, I had a leak of passwords and all the data, do I as a company have any obligations or responsibility for what happened? Since I have all the customers' data and all their passwords, do I have any obligations or responsibilities?
It's a really good, a really noble question. The answer to that ethically is probably yes, you should, quite simply. However, the more nuanced answer is that it's probably going to depend on the industry that you're in, the country that you're in, any regulatory requirements that your company faces, which might oblige you to report out in that way. So I would read up on the context that's specific to you yourself. And I will say, unfortunately, it is not that common in the world, I dare say, that companies document and detail publicly when there have been security exploits. They might announce that something indeed has happened, but it is rare that companies will go into any amount of detail. Now, this is understandable because, one, they're already embarrassed, or if not in legal trouble or financial trouble because that has happened already. But they probably, typically, don't want to provide other adversaries, other future attackers, with more information about their systems and the weaknesses that those systems have. The downside, of course, societally, is that if each of us is sort of secretly getting attacked in ways we didn't expect, learning things that would be ideal to share with others in the world, this itself is actually a big question in the world of cybersecurity, just how much and how often to share, especially when you discover a bug or a mistake in someone's system. Do you tell them privately? Do you tell the world publicly? These are ethical questions that we'll touch on indeed in the coming days as well. Well, allow me to propose that separate from these concerns here, we can come back to some of those recommendations that we started the class with from NIST, the National Institute for Standards and Technology. Notice that this was one other quote we did not share last time. A recommendation from NIST is that verifiers shall store memorized secrets in the form that is resistant to offline attacks. Memorized secrets shall be salted and hashed using a suitable one-way key derivation function. Their purpose is to make each password guessing trial by an attacker who has obtained a password hash file expensive, and therefore the cost of a guessing attack high or prohibitive. So when I refer to best practices, I'm really referring to actual documentation like this, either from the United States, from other countries, from other companies. There are indeed these best practices, and among our goals for this class is to expose you to some of those, both on the consumer side, you and me as individual computer users, but also on the corporate or the academic side as well, as to what you should be doing when you are in a position of being responsible for someone else's data as well. Now, as for the actual hash functions to use nowadays, these are just some of them that are generally recommended nowadays that can be categorized as SHA-2 and SHA-3. These refer to fairly sophisticated mathematical functions that take as input typically a password or some input more generally, and then output a hash value thereof. There are other algorithms too that can even be used to verify the authenticity and integrity of messages as well. In fact, today we'll also focus on how we can use primitives like these to ensure that data was not actually changed in transit when you sent it over the internet from one person to another. But ultimately, what we've been focusing on and what you've seen on this list here are what are generally known as one-way hash functions. That is, these are mathematical functions, or, in the context of programming, these are functions written in code, languages like Python or otherwise, that take as input a string of arbitrary length. That is a password that's this long, maybe this long, maybe this long. But what's key to these cryptographic functions is they output a hash value of fixed length. That is always this many bytes or characters, or this many bytes or characters. That is, doesn't matter how short or how long the password is, these one-way hash functions are one way in the sense that they take a potentially infinite domain, if you know this term from mathematics, and condense it into a finite range. That is a huge number of values, all possible passwords in the world, to just a finite list of possible hash values. It might be a long list of possible hash values, but indeed, no matter how long a string of text is, if it's of some fixed length, 16 characters, 32 characters, something else, there's only a finite number of those values. Now, there's an implication of this. When you take a really large input space or domain mathematically and map it to a smaller finite range, so to speak, mathematically, it turns out that if you do try to reverse the process, there will be multiple inputs that yield the same output. Think about it this way. If you've got 100 possible passwords in the world, but you only have 10 possible hash values, so 100 passwords, 10 hash values, you have to figure out how to put all of those passwords into 10 buckets, so to speak. So surely some of those passwords are going to be in the same bucket. Think about it in terms of the English alphabet. If we stuck with that original hash function where A was 1, B was 2, C was 3, presumably Z was 26, there's more than one fruit that starts with A, apple, avocado, and so forth. So there too, you were going to have multiple fruits mapping to the same finite range of values, hash values 1 through 26. What that means is that if an adversary, or even you, the owner of the system, look at that hash value and see the number 1, you don't know if the password was apple or avocado or some other word that started with A. And so that's what we mean by one-way hash functions. You cannot reliably reverse the process by any means and know definitively what the original input is. Now, there is a catch. That technically means on some systems, it might be possible to log in with apple or avocado, or more generally, your actual password and some other seemingly random password that might make no sense to you, but just because mathematically it has the same hash value, that password too might let you into the system. But the idea is, especially as we're using really large numbers of bits, really long hash values, the probability of you or me figuring out, or an adversary even guessing what that other hash value or what those other inputs, passwords might be, is just so small that we tend not to worry about it as well. The algorithms we've looked at on the board here are also known as cryptographic hash functions, which means they have utility in the world of cryptography, where the world of cryptography is all about the practice and the study of securing data while in transit from one point to another, or while at rest on your own system. Let's go ahead here and take a 5-minute break, and when we come back, we'll explore precisely that world of cryptography with respect to our data. All right, we're back. And indeed, cryptography is all about the practice and study of securing our data, particularly when we want to transmit it from one person to another. So cryptography can be broken down into a couple of different categories, one of which are codes. And codes are not the type of code that you might write in Python or the like. It has nothing to do with software, but rather a mapping between what we'll call code words and the actual message or true reading that those words represent. Here, for instance, is an actual book from over 100 years ago that was used to map these code words in the left column to these indeed messages or true readings on the right. The idea is that if that one party wanted to send a secure message to another party, they wouldn't just write it out in plain English. Why? Because if that message written on a piece of paper or parchment were intercepted by another human, that other human, assuming they too know English, could just read the actual message, the so-called plain text. In a code, though, you can convert the words that you want to say to code words that make no sense necessarily to someone who's intercepted the message in and of itself unless they too have this book. Now, you can imagine this being a fairly time-consuming process because when the recipient receives that message, unless they've memorized all of these pages, these code words and the meanings thereof, they have to do quite a bit of work flipping through their copy of the book in order to figure out what that message is. But the fact that they have a copy of the book too is a potential threat, because if one party or another had their code book stolen, then any of the messages they've sent can now be decoded, so to speak, by looking them up retrospectively. And any future messages, if the owners of the book don't realize that code book has been taken, so too could those messages be translated. Not to mention the fact it's fairly cumbersome. This alone is page 187, and so that's quite a bit of codes and quite a bit of work just to achieve this layer of indirection. But there are some terms of art here that are worth knowing, and you might actually use in everyday context, but not necessarily for the same purpose. So in code, what do we mean by that? It means taking a plain text message, be it in English or any human language, and taking that as input and producing as output code text. So the code text might be a short, succinct sequence of words that might actually be English words, but they're not meant to mean what they normally mean. They're meant to be looked up in the code book to figure out what the message is actually trying to say. Meanwhile, decode, as you might expect, is the opposite. You take as input the code text that you have received as the recipient. You use that same code book to look up the code words and figure out what the actual message is in order to get the original plain text, be it in English or any other human language that the code book is designed for. But there's an alternative to codes, if only because those code books can get very cumbersome indeed. They can be taken and compromised and the like. So it's not necessarily the best system in that you need to physically keep something like that secure, let alone do so efficiently when converting. So there are also what we'll call ciphers. And ciphers are more algorithmic in nature. So if you have taken a computer science or a programming course, you already have the predisposition to thinking algorithmically and taking a big problem and breaking it down into smaller pieces and then applying some kind of logic, sometimes again and again, in order to solve some problem. So ciphers focus on exactly that. They don't focus on maybe words or phrases. They might focus on individual letters instead, or even bits if it's in the context nowadays of computers. So in the world of ciphers, you might have actually seen them in popular culture. So here, for instance, is just one frame from a famous film known as A Christmas Story. At least here in the US, it plays like every day, all day long on a couple of TV channels around Christmas time. But this here is Ralphie, one of the main characters in the movie, and in his hands here is this secret decoder pin that he tried so hard to get through the mail. And this secret decoder pin was from little orphan Annie herself. And what it does is implement mechanically a cipher, converting one letter to a number and back. But the thing twists left and right so that you can actually figure out what the mapping might be. So this is more of a cipher because it's operating at a lower level, not on entire words or phrases, but one letter at a time. And it's a repeatable process that Ralphie, in this case, can apply again and again to all of the letters of the secret message. In World War II, the Germans, for instance, had the Enigma machine that you might have read about or seen depicted in films, and this was a mechanical implementation of this same idea of a cipher. But instead of using mathematics or gears turning just this way and that, it was much more mechanical, was with rotors and lights and the like, but it too was implementing a cipher and could be configured with different inputs in order to influence exactly what the output would be. But that too was a physical device, and we'll focus here for the most part, though, on things more digital, things that you can ultimately, for instance, nowadays implement much more readily and much more scalably in software. But the words we'll use are pretty much the same. To encipher a message means to take that message in English or any other language, our so-called plain text, and convert it, not surprisingly, to ciphertext as output. Meanwhile, the reverse of, or rather an equivalent term here that you might know as well, is to encrypt. Same idea, synonyms for our purposes, plain text to ciphertext. To encipher or to encrypt. Nowadays, encrypt is probably the more common of those terms. Meanwhile, decipher would be the opposite of that. To actually take the ciphertext that someone else has sent to you, run it through an algorithm or cipher, and get back the plain text. Meanwhile, decrypt would be a synonym for that phrase, which refers to exactly the same process of taking ciphertext as input and outputting plain text as output. So how do we configure these ciphers so that you and I can use the same algorithm but customize them not only with our own messages but also with our own settings, so that just because you and I might want to send the same plain text doesn't mean that the ciphertext has to actually be identical. And indeed, in the world of cryptography, it's quite recommended that you and I use public and well-documented, well-tried and tested algorithms publicly, but we do keep one piece of information secret so that our use of that cipher, that algorithm, is specific to us. And this customization, this configuration, are generally known as keys. Now, keys, much like a physical key to a lock on an actual door to your home, a key is what sort of unlocks the capabilities of this cipher, but it's a key that needs to be known and used not only by you typically, but also by the recipient, so that by having copies of the same key, you can not only encrypt messages or encipher them, but you can also decrypt or decipher those messages too. Now, what are these keys in practice? They're not physical objects in the virtual world, but really just really big numbers. And often there's some mathematical significance of these numbers, and sometimes those numbers don't even look like numbers. They might be presented on your phone or your laptop or desktop actually as letters of an alphabet, and maybe even with some punctuation too. But at the end of the day, they're really just numbers, or of course, if you know a bit of computer science already, they're really just zeros and ones. But it's perhaps helpful to think about them metaphorically as akin to these physical keys. Now, how are these keys actually used? Well, within the world of cryptography, there are different types of encryption. And the first we'll look at is known as secret key cryptography. The presumption is that the security of your data relies on the secrecy of some key. So if A wants to send a message to B, then A and B must keep secret whatever key they are using to configure their choice of algorithms. So what do we mean by that? Well, secret key cryptography, specifically in the context of encryption and scrambling data, is also known as symmetric key encryption for the reason that both A and B in this story are going to use the exact same key. And we'll contrast this in just a bit with asymmetric key encryption, which solves other problems as well. So let's consider the process of encryption, much like the process of hashing, as being this black box. Somehow or other, this black box is going to encrypt information for me, taking as input my plain text and hopefully outputting as output my ciphertext that I can actually send over the internet or some other channel to a recipient as well. So in the context then of secret key encryption, the picture looks a little something like this. Not only do you pass as input to the algorithm your plain text message in English or any other human language, you also pass a key. And for now, just think of that key as a number that you and the other person have somehow agreed upon in advance. That algorithm then will ultimately output the ciphertext. And to be clear, the motivation for that key is to ensure that if I and you and you and you and you are all using the exact same encryption algorithm, it's not going to be obvious if and when we're sending the exact same messages, because that too, per our discussion of passwords, would leak information. Maybe you don't care about the information being leaked, but it's probably not a good thing if just because someone else is sending some message, that makes it more likely that an adversary can infer what it is you sent because the ciphertext just so happens to look the same. We want our ciphertext to be unique to each of our transmissions. So let's consider a simple example. Suppose that the message I want to send is just as short as the capital letter A, and suppose that the key that I want to use is as simple as the number 1. These are not good best practices, but we'll use them for the sake of discussion. Let me propose that the simplest algorithm I can perhaps think of is actually one that would take A as input and 1 as input and output B. And you can perhaps infer where this is going. If I instead provide B as input and 1 as input for the plain text and key respectively, then the output is C. So believe it or not, in yesteryear, Julius Caesar was known to use an algorithm like this by lore, whereby this algorithm, Caesar cipher, is what's generally known as a rotational cipher, because you're sort of rotating the letters of the English alphabet. A becomes B, B becomes C, and I bet if we continue this logic, we can go around from Z becoming A as well. Now, this, of course, is being applied at the moment to very short messages that are not that useful. Sending A or B or C is not particularly useful in general, but it's demonstrating how we can encipher or encrypt our plain text into our ciphertext. However, when someone receives this message, they need to know not only what algorithm I used to encrypt it, in this case, Caesar cipher or a rotational cipher more generally, but they also need to know what the key is. And the key might not be as simple as 1. Here, for instance, is an example of 13. If your key is 13 and your plain text is A, then your ciphertext should be N, because that is 13 places away from A. And so now the algorithm seems a little less obvious. 13 is also representative of something that's long been known on the internet as ROT13, for ROT13, rotate 13 places. It's a very popular way of scrambling information, but not in a way that you intend to be secure. Historically, it was often used for like movie spoilers online. If you want to make something a spoiler before there was CSS and blurring effects on websites and whatnot, you could just scramble it so it looks completely encrypted, but it's very easy for someone else with a click of a button even to just decrypt it. However, I would recommend that you not use a key of 26 because why? Well, at least in English, there's only 26 letters of the alphabet, capital A through capital Z in this case. So a key of 26 is going to output for your ciphertext the exact same thing as your plain text. So there's another joke on the internet whereby, ROT26 is twice as secure as ROT13, because 13 times 2 is 26. And obviously, that's not the case deductively here. Now, of course, this particular algorithm and keys of this small size, 1 through 26, not at all secure. Why? Well, honestly, I don't even need a computer to crack this cipher. I can probably take out a piece of paper and pencil and just try all possible numbers from 1 to 25. I don't need to even waste my time with 26, and just figure out via brute force what key someone might have used to send a message using this algorithm. Not on even single letters, but maybe it operates on every individual letter of their message. Wouldn't take me that long to probably figure this out by brute force by hand. And with code, my gosh, I could write some Python code probably that does it even faster than that. So here on the screen is some ciphertext that I created in advance. And I'll stipulate that this ciphertext was enciphered using that same rotational cipher. But I'm not going to tell you just yet what key I actually used. It was originally an English message in all capital letters, so the task at hand now is to decrypt this, I dare say. Whether you are the intended recipient of the message, or maybe maliciously you've intercepted my transmission with this message in it, and now you're trying to brute force your way through by trying, and by the looks of some heads going down and some scribbling, 1 or 2 or 3. I bet we could also brute force our way through this algorithm. But how? Well, how does the decrypting process work? It's really just the same thing in reverse. If this now is our picture and you have ciphertext as your input, you should be able to pass the same key as input, 1 for instance, or 13, or with no good reason, 26, and get back out the plain text. But of course, the decryption algorithm is indeed the opposite, because you don't want to just add 1 position or add 2 positions or 3 positions. You want to subtract 1 or 2 or 3 or 13. You want to go in reverse, so to speak. And so if I were to pass in B as the ciphertext and 1 as the key, well, the plain text decrypted should, of course, be A. And that holds now for all of the other letters of the alphabet, assuming I'm reversing this process in order to decrypt. And now I'll let you glance at the screen here for just a moment and see if you yourselves can't figure out what this ciphertext is trying to say. And if you like the idea of figuring this out, if you want to get better at this particular skill, you are an aspiring cryptanalyst, I dare say, focusing on this world of cryptanalysis. And this, too, itself is a job, I dare say, particularly with governments trying to decrypt messages that might very well have been encrypted. Now, hopefully, the world is using more secure algorithms than these simple rotational ciphers. And what do I mean by secure? Hopefully, they're using keys that are much bigger than small numbers like 1 through 25. Hopefully, they're using much, much, much larger numbers, many more bits, if only so that it takes you and me, when we try to apply cryptanalysis to ciphertext, it takes us way, way longer than this particular algorithm alone. Now, I don't want to keep you in suspense, but I also don't want to spoil this if you'd like to try your hand at this. So go ahead and close your eyes if you don't want to see the answer to this, or I suppose you can just look away from your screen. But in 5 seconds, I'll reveal what the plain text actually is. And some of you, if you've seen that movie I mentioned, will know immediately why this is the way it is. But otherwise, you might just see this as an advertisement of sorts. So here we go. Your chance to close your eyes in 5, 4, 3, 2, 1. From some faces, some of you have seen this movie around the holidays, but now I've taken it off the screen, and we'll move on now with some actual algorithms. So if you'd like to come back on replay and actually see what the answer is, we'll, of course, leave it on demand. So what are some of the actual algorithms used nowadays for encryption that are best practices? This rotational cipher that I described earlier, Caesar's simple one, is not to be recommended. It's wonderful for demonstration's sake and discussion's sake, but it's not something you should be using in practice unless, for instance, you're in, say, middle school trying to send a message on a piece of paper through your classroom of classmates and worried that the teacher might intercept it, and the teacher probably doesn't have the instinct to or the care to actually brute force their way through it and figure out what the key is. But that's the level of security you're getting with something like that rotational cipher. But in the real world, with our phones and desktops and laptops today, generally used are AES or triple DES, both of which are popular algorithms that have been vetted by the world and are very commonly used as secret key encryption ciphers or symmetric key encryption ciphers, which, to be clear, require that both the sender and the receiver know and use the exact same key. And for our purposes today, let me just stipulate that the mathematics of these two and other algorithms much more sophisticated and documented in textbooks, but therefore it makes it much harder for the adversary to figure out, as by trying 25 different keys, what the actual key in use might be. Questions now about secret key cryptography or any of the primitives we've just discussed.
So is it possible that if someone hacks the gets to know about the hash value, the hash function of a company that it is using, he might be able to use the hash values and find a reverse function and then get the passwords for that?
A good question. I wouldn't worry mathematically about someone reversing the hash functions, if only because with all of the ones that are in popular use today in modern systems, there are a lot of smart mathematicians, computer scientists, professionals who have kind of vetted, if not proven mathematically, that these things work as expected. However, if the passwords that have been hashed are relatively easy to guess, or if the adversary just gets lucky with whatever technique they are using, it is absolutely possible to find at least a password, a input, that maps to that hash value, but often not without significant effort. And so generally, a company does not want to, should not try to keep proprietary or secret what hash function they're using, what encryption algorithm they're using. If anything, I dare say, it should be reassuring to the public if and when companies are using best practices and de facto standards. All of these algorithms are designed to keep secret, not the algorithm itself, which literally can be found in university textbooks nowadays and on Wikipedia and beyond, but rather to keep secret the thing that's designed to be secret, which is the key. And now, if you're using too small of a key, like I did originally, well, then you're just using the algorithm poorly, perhaps. But so long as you're adhering to best practices and picking a really big recommended size key, then things mathematically should be trustworthy.
For an attacker, rather than basically cracking a hash or cracking an algorithm, wouldn't it be easier to just try and access the basically server database and access the hash function like generator code? So rather access how the specific algorithm works. That way, they can basically just reverse engineer it.
Everything you described is possible. However, I would push back on this assumption that the company should try to keep its hash algorithm secure or hidden, you should trust in the mathematics of what we're discussing today, both in the context of hashes and in the context of encryption. And I've pulled back up on the screen here the number of possible hashes that exist when using one of the most modern standards for hashing passwords. This is such a big number. I dare say, I don't remember how many atoms are in the universe, but I'm going to guess it's fewer than this, maybe. The idea is intuitively that if the search space of possible hash values or the search space of possible keys is so darn big, both you and I, not to speak darkly, are going to be dead before the attacker actually figures out what that password or that hash actually is. So that's generally the presumption. Most of what we do today in terms of security all boils down to probabilities and trying to drive the probability of being exploited way, way, way down, even though if your password is still 000000000, doesn't matter if there's this many or more possibilities if the adversary tries that one first. So keeping algorithms secret, keeping ciphers secret is generally not best practice. You should be trusting that the math and the probabilities will protect your data if you are using these algorithms correctly. And how about one more question before we resume?
How cipher work with word, not number, like with words? How it work? How we can cipher cryptograph letter, our letters with words, not a number. How it can be work?
OK, so if your key is a word and not a number, let me first say that generally when it comes to encryption, the keys are not words. These are not passwords. They're not meant to be used in quite the same way. These keys are generally generated by the computer for you. And so as such, they're just random numbers for the most part. With that said, even if it is a word like Apple, there are ways, and you would learn this in a class like CS50 itself, to convert a word to the underlying numeric representation. There's a system called ASCII or Unicode. So capital A is actually the number 65 in most systems. Capital B is the number 66. But we can go one level deeper. There's actually a pattern of zeros and ones that represent A's and B's and C's and so forth. So we can convert everything in the world of computers to numbers. And for that, let me encourage you to take CS50X Online. So that then is secret key cryptography or symmetric key cryptography, but it doesn't solve all of our problems because I've kind of taken for granted throughout this whole discussion that the sender and the receiver have a shared secret between them, whether it's a simple key like 1 or 2 or 13, hopefully not 26, or hopefully some much bigger value. But there's kind of a chicken and the egg problem there, so to speak, in English, whereby how do you actually establish a shared secret between parties A and B if A and B have never talked before? In fact. So for instance, if you're visiting Amazon.com for the first time, a popular e-commerce website, or gmail.com for your email, ideally, and you probably know this already from just living in the real world nowadays, ideally you want that connection to Amazon or Gmail to be encrypted, to be scrambled in some way. Why? Well, you don't want your password being stolen by someone. You don't want your credit card number being intercepted by someone. You don't want your personal emails being read by other people. So it stands to reason that encryption is generally a good thing. And you've seen this perhaps in the URL bar via something called HTTPS, where the S literally is meant to mean secure. But odds are you don't know anyone personally at Amazon.com, and you don't know anyone personally at Gmail.com. So what key are you going to use to communicate securely with these websites? Not to mention new websites that don't even exist today but might come online tomorrow. How do you establish a shared secret with someone else? So that's sort of a fundamental gotcha or caveat with symmetric key or secret key encryption, is that assumes that you have a shared secret between you and the other person. But the chicken and the egg scenario comes in whereby the only way to establish a shared secret would be to send it to the other person securely. But if you can't communicate securely, you can't even send them the secret you want to use. So you're sort of caught in this deadlock. Thankfully, thanks to math, there are ways that we can solve this too via not symmetric key cryptography, but public key cryptography, otherwise known as asymmetric key cryptography. And among the algorithms here might be these, something called Diffie-Hellman, MQV, RSA, and others as well. And I dare say on this list, maybe RSA is among the most well-known, is perhaps an acronym you've actually seen in the wild. Now, what do we mean by public key cryptography, or more specifically, public key encryption? Well, in the world of public key encryption, or asymmetric key encryption, the asymmetry is implying that you actually don't use one key between the two people, A and B. You actually use two keys. In the world of public key encryption, everyone in the world has both a public key and a private key. And these two are just really big numbers. There is a mathematical relationship between these numbers, the public key and the private key, but that's a relationship that your phone or your laptop or your desktop figures out when generating these values for you. So unlike our previous discussion of passwords, which you and I as humans do choose and memorize or store in our password managers, when it comes to keys, these are generally, in the world of public key cryptography, generated for you. And as the name suggests, the whole purpose of these keys is to tell the whole world, if you want, what your public key is. It is not in any way secret. You can literally email it out. You can put it in the signature of every email. You can post it on your website, on social media. The whole point of the public key is to make it indeed public. But suffice it to say, the private key should be kept secret by you, private by you on your own device. That should never be shared with anyone else. But the cool thing about public key cryptography and the mathematics underlying it is that if you share your public key with someone else on the internet, they can use that public key to encrypt a message and then send it to you over email or chat or any other technology. And if you had to guess, what is the only key in the world that can decrypt a message that has been encrypted with your public key? The only key in the world that can decrypt a message that has been encrypted with your public key is your private key. That's what the mathematical relationship ultimately does for you. So pictorially here, if this is our algorithm that implements this idea of public key encryption, let's see what the inputs and outputs should be. If the goal is to send a message to you and you have shared with the world your public key, whoever is sending you this message uses your public key, their plain text message, and out of that comes ciphertext. That then is how asymmetric key encryption works. Meanwhile, when you receive that message, you can use your own private key and the ciphertext you've just received to get back the plain text. And this is what we mean by asymmetric. Unlike secret key cryptography or symmetric key cryptography, where you're using the same key back and forth, +1 or -1 in the case of the rotational cipher, with asymmetric encryption, you are using one key for one process and another key for the decryption process. So that's what's fundamentally different. RSA is one of the most popular algorithms for this. The browsers you probably use every day are probably using some variant of RSA underneath the hood. We won't get into great detail about the mathematics, but one of the most important details about RSA is that it relies on really big prime numbers. In fact, in a nutshell, what happens with RSA is your computer or your phone chooses a really big prime number called P. It then chooses a really big other prime number called Q. Then it multiplies them together to get a new value. We'll call it N. And it uses that value N in the resulting mathematics that the algorithm's authors came up with, ... The presumption here is that when you take a really big prime number and multiply it against a really big other prime number, it is really hard to figure out from the product of those numbers what the original P and Q were. And if you're a little hazy on prime numbers, it's a number that can only be divided by itself and 1. And indeed, we can use those, coming up with two big ones, multiply it together in order to get this value n that is subsequently used in the rest of the mathematics. What are the rest of those mathematics? In essence, this. And this will be the scariest looking formulas you perhaps see over the course of this class. The value n I just described is used as to divide values ultimately. If you're unfamiliar with mod here, this means to, in this context, take the remainder of some value. So what are we doing? Here is a quick summary of how encryption and decryption works with RSA. If you have some message M that you want to send to another person, and you have come up with somehow, via the ... process earlier that I alluded to, you've come up with your own public key E there, well, then someone can take their message, encrypt it by raising that message to the power of E, the exponent of E, and then divide it by n, and figure out what the remainder is when dividing by n. That then gives you a value called C for ciphertext. When you then receive that message, C, you can use your private key, known here as D, and you raise the ciphertext, its numeric value, to the power of D, that is the exponent of D, and you divide by n in order to figure out that remainder, which will give you back the original message. Now, that is a significant oversimplification of what's going on, but that's the essence of the algorithm. It has to do with picking two very large prime numbers, multiplying them together to get that value n, and then using n as well as other values that ... are generated by the algorithm for you, E and D, in order to encrypt and decrypt messages ultimately. And this is what's generally known as modular arithmetic. It involves lots of division and division and division in order to come up with these remainders, but ultimately it is a very secure way to asymmetrically share information without having to agree on one shared key in advance, but rather using a public and a private key instead. Now, there are other techniques that come with this world of public key cryptography, and another technique is that of key exchange. So by contrast, if you do actually want to establish some kind of shared secret, there are alternative algorithms that different humans have invented over the years. So there are alternatives to one algorithm or another, and one of these alternatives is actually called Diffie-Hellman, named after another pair of authors here. So here is the essence of the mathematics for this algorithm, the goal of which is indeed key exchange, to figure out, using fancy mathematics, how both A and B can come up with the same value that they can then use as a shared secret, but without anyone who intercepts any of their messages being able to figure out what is that shared value, that shared secret. So what's the essence of the math here? Well, you first pick a value g, which is called a generator. It can be as simple as the number 2. And you pick a big prime number, call it p here, and those are agreed upon in advance. Meanwhile, person A, say Alice, picks her own private key A, which is another really big number. And then she does this math, g to the power of A mod p. And again, mod refers to taking the remainder of some value. Meanwhile, B, or Bob, still uses the same g, still uses the same p, picks his own private key called B, and raises g to the power of B modulo p, and that gives him back this value, capital B, whereas Alice had capital A. Then, turns out that Alice and Bob can send those values across the internet, A one way, B the other way, and thanks to some fancy modular arithmetic here too, Alice can take Bob's B value and raise it to the power of her A value, which effectively gives you g to the power of A times B mod p. Bob, meanwhile, can take Alice's A value that was sent to him, raise it to the power of his private key B, and then mod p. So calculate the remainder with respect to p. The end result, and it's totally fine if these mathematics are uncomfortable for you or whew, just know that thanks to some basic principles of mathematics, this results in both Alice and Bob having the exact same value. We'll call it S for shared secret, even though the value never went across the internet in its entirety. Alice sent part of it this way, Bob sent part of it this way, but because Alice and Bob held on to private values, the little a and the little b, they kept that to themselves, they are able to do these mathematics that ensure that they both came up with the same value, even though you or I, if we intercepted any one of those messages, we could not figure out what it is. And now that they have a shared secret S, they can use that using any of those other symmetric ciphers we talked about earlier. AES, I put on the board briefly. Triple DES, I put on the board briefly. Heck, we could even use this in a rotational cipher if we really wanted to, but not indeed best practice. So again, don't worry so much about focusing on the mathematics, but if you were to take a higher level class in theoretical computer science, these are intellectual rabbit holes that you could go down to better understand how the software works. And now to my comment earlier about not trying to invent your own cryptographic functions, like this is the kind of reason why. This is the degree of sophistication that you and I take for granted in our phones, our laptops, and desktops that have been vetted by industry and academics alike. Generally, best practice is to rely on standards that have been tried and tested rather than try to come up with your own creative crypto system, so to speak, that may very well have faults that you yourself do not know. And the icing on the cake is that this is ultimately, if curious as to the underlying mathematics, what value ultimately Alice and Bob are both calculating, g to the power a times b mod p. But more on that in a higher level mathematics course, if indeed of interest. How about one final building block that you get from this world of public key cryptography? And this is one that's going to be increasingly omnipresent, I do think, in our world, especially as we move away from very archaic paper pencil signatures that you might write with a pen on a paper, and rather moving to what we'll call digital signatures as well. It turns out that once you're comfortable with the idea of public key cryptography, generally involving a public key and a private key, the first of which is literally public, you can share it with the world, the second of which is meant to be private, kept only to you, and if you can take at face value my claim that through appropriate mathematics, there's a relationship possible between these two numbers that whereas one can encrypt data, the other can decrypt. Even if you don't care to get into the specifics of the mathematics, but you just agree that, okay, that sounds reasonable to me, that math can work, we can now use that building block of a public key and a private key to solve other problems as well. Not just encrypt messages from point A to point B and back, but rather to sign information, sign documents even, and say, yes, this was signed by David or someone else. So how does this work? In the world of digital signatures, here's a few more acronyms of algorithms that are commonly used, even though we'll continue to simplify them in our discussion. DSA, ECDSA, RSA, and others can be used to give you the ability to sign documents or other pieces of information digitally. So what does it mean to sign something digitally? It's not at all like this with a unique signature. It's all mathematics involved. So here then might be our algorithm for digitally signing some document or piece of information. And I claim that the input to this process is a message, a letter that you've written, a contract that you want to sign, something that you want to put your digital signature on. And the output of this message initially is going to be a hash. So we can use any number of hash functions we talked about earlier that take as input an arbitrary length input, like a message, a document, an essay, a contract, and produce as output a fixed length hash value. So we've seen that, and we've stipulated that that is indeed possible, similar in spirit to our password discussion earlier. You can even do it for larger inputs than passwords. You can do it for entire documents as well. Once you have that hash, here's how you digitally sign the document. You use your private key. You pass that as input, as well as the hash value you just computed a moment ago, into the digital signature algorithm. And the output of that process is a signature. So if you think about this intuitively, what are we doing? Well, we're taking an arbitrary sized document. Maybe it's a letter that you've written. Maybe it's a contract that you've written that you need to sign that might be short, or it might be really long. Here's where the value of cryptographic hash functions come in. Recall that a cryptographic hash function, by definition, takes an arbitrary size input and reduces it to a fixed size output. So it doesn't matter how big the original was. You can distill it into a distinct representation that's shorter. So per this diagram, if you take that hash value and you encrypt it with your private key, what we say is that the output of that process, which is just a really big number or some sequence of weird looking text, is your digital signature. Now this is a little weird because what we're doing now is the opposite of public key encryption. With public key encryption, remember, someone else used your public key to encrypt a message to you, and you used your private key to decrypt it. But in the case of digital signatures, the story gets flipped upside down. You use your private key and a hash of your message to digitally sign your document, and the output of that is a signature. Again, a number or some string of text. and you send that signature to the recipient saying, this is my digital signature. You can verify it now if you so choose. And they should. So that invites the question, well, how does the recipient verify your digital signature? How do they know that this weird looking sequence of characters or numbers actually was signed by you? Well, recall that you have not only a private key, but a public key as well. And that public key is accessible to everyone, including that recipient. And so what happens is this. When that recipient gets your document and your digital signature, so to speak, they probably want to and should verify the digital signature to confirm that, yes, you signed off on that document or contract. So what does that box look like? Well, they have received not only the document itself, the so-called message, they've also received your digital signature. So you've sent them two things. And the digital signature, you can think of it like a human signature, but it's, of course, a big number or a string of text. But they've sent you two things, the document and that signature. So what do? You take the document you've received and you run it through the exact same publicly available hash function, because the document might be long, so you want to collapse it into a short hash representation thereof, just like our use of passwords. So that you can just do easily, no private information involved. But then what do? You then take the public key of the person who signed this document, you take the signature that they claim is their signature, and you decrypt their signature with their public key. That should output the exact same hash that you just calculated. So to summarize, the message itself, the document in this story is public. It's not encrypted. It's not something you really worry about being private. What you really care about in this story is that it was signed by a specific person. So if that message, that document, is available to both the sender and the receiver, both of them do this first process of hashing the message, hashing the document, just to get some succinct representation thereof. So it's not this big, it's this big. Makes the math quicker and easier. However, what the recipient does is, upon receiving not only that message, which they just hashed, but also your claimed digital signature, they try to decrypt your signature using your public key. And here too, just as the private key can reverse the encryption done by a public key, so can the public key reverse the encryption done by a private key. So if the recipient mathematically gets the exact same hash after decrypting what you sent them, it must be the case mathematically that the only person in the world who could have signed this document is in fact you, because they have your public key. And maybe some third party, some registry, some company has said, yes, that is David Malan's public key. You can trust that. And so if David Malan's private key has not been compromised, you can trust that any signature that you can decrypt with my public key must have been encrypted with my private key. And it takes a while, I think, for these ideas and certainly the mathematics to sink in. But for now, if you just trust that there's two big numbers in the world, one public, one private, there's a mathematical relationship between them such that one can reverse the effects of the other in either direction, we humans can use this now not only to secure our messages per our discussion of encryption, we can also use it to authenticate messages and attest, yes, this came from David Malan or did not. And unlike a human signature on a piece of paper that can obviously just be photographed, duplicated, traced over, the secrecy of digital signatures relies on keeping your private key private. And that notion does not exist in the world of human signatures. And so in that sense, digital signatures are objectively better than our old form human ones. Questions now. And I know that's a lot, and it's okay if it didn't all go down at once. Questions on digital signatures, public key encryption or decryption, or anything prior?
Would these public and private keys be attributed to at your IP address?
A good question. To what are they attributed? Not to your IP address typically. They are typically stored in a registry, like a central registry that knows that this is Vlad's public key, this is David's public key, and so forth. And it relies on a system of trust and transitivity. So if you trust this third-party company that is storing all of our public keys, then you can trust whoever it is they are in turn trusting. Or it can be more distributed. Your public key can literally be distributed in the footer of your emails. It can be posted on your website. It can be on your LinkedIn profile or the like. And so long as other people in the world trust your emails or your website or LinkedIn, they can trust that that is, in fact, your public key. So different ways to implement that system of trust. Other questions?
Hashing uses a mathematical function, and encryption uses a mathematical function plus a key, like the Caesar cipher basically uses the simple function plus the key. Is that analogy correct?
Yes, that is correct. And if it helps you, this is an oversimplification, but it's generally helpful, I think, to think of hashing as one way. So you can only convert a value to a hash value, but not the opposite. But encryption is like two-way. It's reversible hashing, so to speak. The output still looks weird and random, but you can undo the process. And one way to think about this is in the world of hashing, because I claim that you can take like an infinite domain, like any possible message you want to send, and convert it to a finite range. For instance, all A words could be a hash value of 1. All B words could have a hash value of 2. That simple example already captures the reality that if you only have the hash values, 1, 2, I have no idea what the original input is. And it doesn't matter how hard I try, I'm never going to figure it out because it could be apple or avocado or something else that starts with A. So hashing in that sense, one-way hashing throws away information such that it's not recoverable. But encryption does the opposite. It would be pretty useless if encryption threw away information, because the whole point of encryption is to secure messages and information we want to send. So encryption is reversible. Hashing in general is not. And as you know, the key, no pun intended, to encryption is necessary so that you can reverse the process in a way that remains secret to other people. How about one more question, and then we'll take a short break, and then we'll come back and wrap up.
Is there any possibility to spoof the signatures?
Short answer, no. Like, so long as you are using a standard that we believe to be correct and not compromised, so long as your private key has not been stolen by someone or no one's taken it off of your phone or your computer, it should not be possible to forge it. The probability is so low, it should be the least of your concerns, is the idea. Now, it turns out there is yet one other application of this world of public key cryptography that solves a problem from last time. Recall that we ended our first class on a note of emphasizing that passwords and password managers can improve our security if used properly, but there's another technology that's becoming increasingly available, and it's colloquially called passkeys. Or more technically, it's an implementation of a standard called web authentication. And it turns out that these passkeys, which are available on certain platforms and certain websites, and ever more will be available soon, quite surely, they too rely on public and private keys as follows. And thankfully now, as fancy as the mathematics we're alluding to today sound, there really are only two ways to use these public and private keys: to either encrypt with one and decrypt with the other, or vice versa. So we have just a fairly basic building block that we can use in one direction or another. So how do passkeys work? In the near future, as you will find, when you go to certain websites or applications, you probably will not be prompted as frequently to type in a username and pick a password, which is to say, you don't have to generate a hard-to-guess password. You don't have to memorize a hard-to-guess password. You don't have to even store a hard-to-guess password in a password manager, because passkeys eliminate passwords. It moves us more toward a world of passwordless accounts. Now, how can that be? Because up until now, we've been using usernames and passwords to authenticate ourselves. Well, it turns out we humans have been getting really good at this math, even if it doesn't feel like it today. We've been getting really good at using mathematics to solve these problems as well. So imagine the following scenario. When you go to a website in the future or app, rather than being prompted to create a username and password, you'll just be prompted to create a passkey, What that means is your laptop or desktop or phone will probably prompt you with some form of factor. They'll ask you for your fingerprint, or they'll ask you for a scan of your face, or maybe a PIN code, a short number that you type in just to demonstrate with high probability that you are authorized to be using this device and creating this account. What then will your device and the website do? Your device will generate a public key and a private key just for that one website or app. Your device will send the public key to that new website, along with your user ID or username, some identifying information so that they know you're David or someone else. But you don't send a password. You only send to the website or app your public key. And you keep private within your browser or some other piece of software your corresponding private key. And to be clear, this public-private key pair is used only for this one website. You'll do this repeatedly, but automatically for every other website in the world in this model. So what happens when you not register for that website, which you've just done, but you want to log into it tomorrow, next week, or next year? Well, assuming you still have that same device, or you're using some kind of cloud service that synchronizes all of your pass keys, your public and private keys, across devices, so you haven't lost these pass keys, here's how you would log into the website tomorrow, next week, or next year. The website would send you, when you visit, a challenge. And a challenge is like some little message. It's like a number or a word or a phrase. It's some piece of randomly generated data that the website wants you to digitally sign. Well, how do you digitally sign information? I proposed earlier that you can use your private key and pass that key and that challenge, which is just a random input given to you by the website, into your digital signature algorithm, this black box. And the output of that, as before, is your signature. And what does your device do? It sends that signature for that challenge to the website. And if you followed along earlier well enough, you might now realize where we're going with this. How does the website now verify that that is, in fact, your signature? That this did come from David's device and not some adversary online. The website, because it stored yesterday, last week, last year, your public key, it will use your public key to decrypt your signature using the same algorithm to get back, hopefully, the same challenge value. And if the output of this verification process matches the challenge the website sent you a second before, it must be the case mathematically that you are, in fact, who you claim to be, because it was your device that registered for this website a day, a week, a year ago as well. So again, if we trust in the mathematics here, and we trust that these algorithms allow us to encrypt information and decrypt it using a public key and private key, or conversely, a private key and public key, we can, with very, very high confidence, probabilistically say, yes, this is David Malan. I'm going to allow him back into this account. So what's the implication of this passwordless world that uses pass keys, or web authentication more technically? It means that we're getting out of the business, potentially, as a society, of having to remember dozens or hundreds or thousands of different passwords for all of our accounts. It does require, though, that we don't lose the device or the devices that registered for these websites or apps. But again, increasingly is the world providing cloud services, whether it's with Apple or Microsoft or Google or others, that presumably can synchronize your passkeys across devices. And we'll conclude ultimately today by talking about how they can be synchronized securely, even without Google and Microsoft and Apple knowing what your own passkeys are, so long as they provide us with a certain technical guarantee. So the upside of this is we can move away from passwords, and you can even share these pass keys with other people if you so choose. The catch is right now, they're not omnipresently available on every website out there. It's probably going to take some time for the world to come on board, but I do dare say in the coming weeks, months, and years, you will see pass keys increasingly offered to you. And so indeed, the next time you visit a website that asks you, hey, do you want to register with your fingerprint or with your face or with a PIN code, and you're never even asked for a password, odds are it's using this pass key technology instead. Well, let's go ahead and take one more 5-minute break here, and when we come back, we'll talk about securing data as it's moving back and forth and sitting on our own systems. All right, so we're back, and allow me to claim that we now have a bunch of ways to hash data and also encrypt data and also now decrypt data. So how can we use these building blocks to solve some other perhaps familiar problems? Well, there's this notion of encryption in transit, which is a fancy way of saying that you and I probably prefer nowadays that our data be encrypted whenever it's traveling from point A to point B, whether that point B is Amazon.com, Gmail.com, WhatsApp, or any other service that we're communicating with. We ideally want no one in between us, some machine in the middle, so to speak, to be able to get at that same data. Because in particular, what you should be worried about is a scenario like this, where if Alice is trying to communicate with Bob, you might worry that there's some eavesdropper, so to speak, named Eve, between Alice and Bob. And maybe this is via wires nowadays on the internet. Maybe it's somehow wirelessly. Maybe Eve actually represents a company that Alice and Bob are communicating between, like Gmail or Outlook or the like. So encryption in transit, though, is important to distinguish from other forms of encryption. In particular here, Alice might very well have an encrypted connection, not to an eavesdropper per se, but just a third party like Gmail. So assume that Eve here is Gmail. And meanwhile, Bob, when checking his email account, has an encrypted connection to Eve as well, which in this story now is Gmail. So Alice has a secure connection to Gmail, and Bob has a secure connection to Gmail as well. But that does not mean necessarily that Alice has a secure connection to Bob. Security does not really work through transitivity, so to speak. This might very well mean that the data is only encrypted while in transit from A to E and from B to E. But that doesn't mean that Eve, or Gmail in this story, can't be reading all of Alice's and Bob's emails. And indeed, that is technically possible on Google's end. They, of course, run all of the servers that your Gmail accounts might be on. There's nothing technically probably stopping them from reading anything and everything. Now, hopefully they have policies. Hopefully very few humans actually have the privileges or the authorization to even do anything close to that. But technically speaking, just because Alice has a secure connection to Gmail and Bob has a secure connection to Gmail, that doesn't mean that their communications will be encrypted entirely between A and B. And there are lots of examples of this as well. Zoom, for instance, when it comes to video conferencing, you might have an encrypted connection to Zoom. I might have an encrypted connection to Zoom. That does not necessarily mean that Zoom couldn't be Eve in this story, listening and watching everything that we're saying while video conferencing as well. So encryption in transit is good in that it at least keeps random people out of the picture because they don't have access to these encrypted channels. But if there is this third party, this machine in the middle or company in the middle, even they might have access to data that we do not want them to have access to. So what then is a stronger alternative? Increasingly possible, increasingly available, and something you as a user should be looking for with greater frequency is what we would call end-to-end encryption. This is a stronger guarantee whereby you can trust that Alice's connection to Bob is in fact secure, even if, not pictured here, there are 1, 2, 3, 4 machines in the middle, companies in the middle, eavesdroppers in the middle. If you use encryption properly, end to end, you can ensure that the only thing Eve or Google or Zoom can see is just your ciphertext, the seemingly random strings of text or zeros and ones that represent your encrypted data, but without your key, they have no idea what that data actually is. So end-to-end encryption isn't necessarily in most companies' best interest. Why? Well, companies like Gmail tend to presumably mine our data, whether it's for advertising purposes or otherwise. And so it's sometimes in companies' interest to have access to your data to keep it secure on their servers, but still in a way that they have access to it. Now, that might be not comfortable for you. And so there are alternatives. For instance, iMessage for Apple users and WhatsApp internationally is known in particular for offering end-to-end encryption, which, if implemented truthfully and technically correctly, should guarantee that even though your messages might be going through WhatsApp servers, no employee at WhatsApp can actually see your messages because it's encrypted all the way from A to B, even though it's going through a potential eavesdropper. But that depends on exactly what form of encryption you're using. And if it's not end-to-end, it might only be encrypted in transit, such that that eavesdropper might indeed have access to the data. So as to how you can use end-to-end encryption, it's an option that a service must provide to you in this case, or you must choose services that offer it. It's not necessarily something that's always available, but it is increasingly available in different software. So let's now consider a fairly mundane operation, but one that has implications for these same technologies and solutions. That is deleting a file, be it on your Mac or your PC or your phone or some other device. Now, where is data stored in your devices? Well, generally, it might be in a device like this, a large, somewhat older, but large hard drive that can store lots and lots of files and folders, or perhaps something smaller known as a solid-state drive that might store information entirely digitally without any moving parts. And even smaller might be something like this that you carry around, like a USB stick, and they are even smaller nowadays too, that similarly stores some data digitally. Now, how do we go about deleting files from a computer or any of these devices? Well, you typically click it and drag it somewhere, or maybe you right-click it, or maybe you tap and drag it to some trash or the like. There's any number of user interface mechanisms for deleting files. But let's consider for our purposes what happens underneath the hood. So let me stipulate that your hard drive, your solid state drive, your USB stick just contains ultimately a whole bunch of zeros and ones. And those zeros and ones represent your files and folders. So when you go about deleting a file by dragging it to the recycle bin on Windows or dragging it to the trash can on Mac OS, what actually happens? Well, it turns out not anything at all, really. When you recycle a file on Windows or when you trash a file on Mac OS, it doesn't actually get deleted in the sense that you and I might expect. By deleted, I mean it's gone. I don't want to be able to find it anyway. OK, wait a minute, though. Of course, we all know by now, at least on computers, you at least have to empty the recycle bin or empty the trash can. So OK, maybe I missed that step. But even then, contrary to what you might expect, emptying the recycle bin, emptying the trash can also does not generally delete the data. And here's where I'd again emphasize, wait a minute, when I delete a file, I want it gone, removed from my computer altogether. But what Mac OS and Windows and operating systems in general tend to do instead, when you even empty the recycle bin or trash can, they don't actually get rid of the file per se. They just forget where it is. Somewhere in the computer's memory, there's like a spreadsheet of sorts, some kind of database or table with at least two columns, one of which has the name of your file or the location of your file, the other of which has some kind of reference to which zeros and ones on your actual computer implement that specific file. Maybe these zeros and ones are for one file, these zeros and ones are for another file, and so forth. So somewhere your computer is keeping track of what is where physically on your computer. But when you delete a file by emptying the trash or recycle bin, the computer just forgets where it is. And more importantly, it frees up the space so it can be used later. So what do I mean by that? Well, suppose I do go ahead and delete a file and empty the recycle bin or trash can, and suppose that these yellow zeros and ones represent the file that I no longer care about. Well, what's actually going to happen underneath the hood, so to speak, of the computer? Well, eventually, some of those yellow zeros and ones might just get reused for other files. In other words, these zeros and ones highlighted in yellow represent a file that used to be there but is not. That is equivalent to saying, some other file can now use those same zeros and ones. And so here's some random zeros and ones that maybe overwrite some of the file, but not all of it. Notice there's still a bunch of yellow zeros and ones here in my depiction of my computer. So it turns out that over time, yes, your file will probably get actually deleted. What do I mean by that? Eventually, those zeros and ones will be repurposed, changed from 1 to 0, changed from 0 to 1, such that your file, for all intents and purposes, is actually gone, because it's been repurposed, that space altogether. But notice, at least at this point in time, And shortly after you delete a file, even if you've created or downloaded new files, there might still be parts of your files around, which means that sensitive Word document or Excel file or images that you had on your computer, there might still be remnants of them, just a few lines from any of those. So you should realize that deleting a file doesn't really get rid of it in the way you might expect or hope. To do that, you need to be a little better with practices. Now, what do I mean by this? Secure deletion is another beast altogether. And typically when we delete files, they're not deleted securely. They're not deleted typically in a way that you would hope. So secure deletion does what you might really hope for, get rid of this file altogether. So if we go back to the original contents of my computer with all of these here zeros and ones, and suppose that I want to delete this file here at the top of the screen, you know, in an extreme ideal world, those zeros and ones would just be gone, right? Like that's pretty darn secure. Those bits, those zeros and ones, they don't even exist anymore. Now this is probably not the best way to securely delete information, because if I just got rid of those zeros and ones somehow, like my hard drive is getting like literally smaller and smaller in terms of how much stuff I can put on it if I don't have as many bits or zeros and ones available. So that's probably not the best long-term solution because it's expensive. It's like getting rid of some of my capacity. So we don't actually do that. But how might we securely delete a file? I don't think we want to just wait and hope that those zeros and ones eventually get reused by the system, because we might still be left with some remnants, which might not be ideal. So what we can do when securely deleting a file is something like this. Change all of the zeros and ones that we don't care about anymore or want, change them all to zeros. And this will effectively securely delete the file, because now the ones that were previously there that represented some piece of information are just completely gone. Or equivalently, I could change them all to ones. Or I could even change it to random zeros and ones. The point is, to securely delete a file, you should change all of the zeros and ones to at least some other pattern so that the file is effectively gone. Now, how can you use this to your benefit? Well, some operating systems nowadays support what's called full disk encryption. And this is good for a number of reasons. One, if you enable a feature called full disk encryption, which is actually a specific incarnation of an idea known as encryption at rest. Encryption in transit refers, of course, to your data going back and forth from point A to point B. Encryption at rest means it's just sitting there on your device, in your pocket or on your lap or on your desktop, sitting unused, maybe on or off. So when it comes to full disk encryption or encryption at rest, you ideally want all of your data somehow encrypted on your Mac, on your PC, on your phone. And only when you log in with your password or maybe your fingerprint or your face should that data be decrypted automatically. And this can happen pretty darn fast nowadays with modern hardware, should the data be unencrypted. So you can actually use it and interact with that device. So why is this advantageous? Well, one, if your device gets stolen, so long as you're not logged into it, so long as it's locked, so long as the lid is closed, so long as it's unplugged, or any other number of scenarios, at least if someone takes your laptop from the table in Starbucks or the cafe, well, hopefully, if you have a good password or good biometrics, they're not going to be able to get any of your data. They can maybe delete all of your data, and they can sell your computer, they can use your computer, but they probably, if you're practicing best practices, don't have access to the data that's on the system. Why? Because it's completely encrypted at rest. And they don't know your password, they don't have your fingerprint, they don't have your face. They should not be able to decrypt that data. So in other words, if this is my unencrypted data, the way I want it and need it when I'm using my computer, full disk encryption at rest would change my entire computer to look random. These are random zeros and ones now that I generated by using, for instance, my password or my fingerprint or my face. And this is what your hard drive or your solid state drive should look like when the lid is closed, when the power is off, when you are logged out of it. It should be random zeros and ones. And the upside of this now is that, again, if it's stolen while in this state, there's no data to be used by the adversary because it looks like random zeros and ones. Better yet, if you deliberately want to get rid of the device because you want to trade it in for resale value, because you want to donate it to someone else, because you want to sell it to someone online, when using full disk encryption, the upside is that so long as you had a really hard to guess password, your data is, for all intents and purposes, securely deleted already, because only if the new buyer figures out or knows your password or has your same fingerprint or has your same face, they're not going to be able to access any of your data anyway. And this is important nowadays because it turns out with modern hardware, even if you might want to change all of the zeros and ones to all zeros or all ones or all random data, it turns out that today's hardware can fail over time. So even little USB sticks or solid state drives over time can kind of wear out. But they're smart enough, thanks to software known as firmware inside of it, as soon as the device realizes, wait a minute, that those bits over there aren't working properly anymore, the device might not let you change them to all zeros or all ones or a random zeros and ones anymore. It might just leave them as is forever. Which is to say, it's even more important to start using full disk encryption, encryption at rest, when you first get a device, because that way you can trust that even if parts of the device degrade over time, all of the data that's there and has been there was at least encrypted with one of your passwords or one of your biometrics in the past. So this is the kind of feature, too, to look for in your Mac, your PC, or your phone to ensure that it is somehow enabled. Thankfully, once you log back in with your password, it goes back to the original data and you can use it. Of course, then, an implication of this best practice is that if you lose your laptop or your phone or your desktop's password or your fingerprints somehow change or your face sufficiently changes, you might be locked out of all of your data too. But again, that's just another example of this trade-off between usability and security as well. Now, a downside, an evil side to full disk encryption is ransomware, which is how adversaries are monetizing attacks. It's not uncommon nowadays for hackers, for adversaries, when they get into a system, whether it's your laptop or, for instance, a corporate network, or in some cases, hospital systems or cities' own computer networks, to not try to do any damage or just do something like spam or cryptocurrency mining, but to actually encrypt all of the data on these systems they somehow accessed online. Why? Well, if they encrypt all of the data, they can then ask for a ransom and say, listen, if you don't give me this many bitcoins, I'm not going to give you the key that I use to encrypt your data. And if you poke around online, there have been many examples of this, unfortunately, where hackers have gotten into systems that were not very well protected. All of the data therein was encrypted. And this is an opportunity for the adversaries to try to extort, say, financial gain from a situation by then only handing you the keys, if ever, once you've actually paid up. And there, too, there's the risk, as in any ransom scenario, where who even knows if they're going to give you the proper key in the end. But this is increasingly a concern for municipalities, for companies, for universities, and the like. So just as we have some upsides here, there, too, is this trade-off in what you can do. And lastly, we thought we'd end on a note about the future, because this is a topic that will come up and has come up over time, this topic of quantum computing. So for those less familiar, we've been talking a lot about bits, zeros and ones today. And at the end of the day, that's how today's computer systems are implemented. Patterns of zeros and ones to represent numbers and letters and colors and videos and sounds and everything we've been discussing today, data more generally. Now, typically in our world now, a bit, a binary digit, can either be a 0 or it can be a 1, as per the diagram we had on the screen in these examples. Either a 0 or a 1. In the world of quantum computing, thanks to some very fancy physics and quantum mechanics in particular, it is possible, it seems, physically, for us to implement the idea of bits a little bit differently, using quantum techniques. And there's this idea of not just a bit, but a quantum bit, or qubit, whose power derives from the reality that physically you can implement a qubit in such a way that it is representing both a 0 and a 1 at the exact same time. So it can be not in just one state, so to speak, one condition at once, but 2 states at once. And if you have 2 qubits, they can be in 4 states at once. If you have 3, they can be in 8 states at once. If you have 32 of them, they can be in 4 billion states at once. Now, what's the implication of this? Well, when we talk about cryptography, when we talk about hashing, when we talk about just very large numbers and trying to figure out via brute force or some other mechanism what some input to a function was, if you have exponentially more computing capabilities by not being able to do 1 or 2 things at a time with individual bits, but 2 or 4 or 8 or 4 billion things at once, it stands to reason that if adversaries have access to quantum computing before you and I do, then all of the security you and I now rely on and that we've talked about today could suddenly become insecure. Because we're trusting right now that it's just going to take the adversary a lot of time, maybe money, maybe resources, maybe risk to attack our accounts. But if they have exponentially more resources than you and me, then our data really is at risk. And all of the mathematics we've been trusting need to be hardened instead. Now, hopefully you and I will have access to quantum computing at the same time as, or ideally before, all of these adversaries. So hopefully our algorithms for securing information will continue to evolve along with these technologies. So this isn't necessarily something you need to worry about for now. Indeed, I think after today we have more than enough to worry about. So for today, that's all. We'll see you next time. All right, this is CS50's Introduction to Cybersecurity. My name is David Malan, and this week let's focus on securing systems, particularly those that are somehow networked or even internetworked as well. Now, recall from last time that we presented encryption is really the solution to a lot of our problems, and that's going to be a building block that we continue to use to solve a lot of our concerns around the security of not only our accounts, our data, but now also our systems. For instance, let's consider something that you yourself are perhaps using right now, which is Wi-Fi, somehow connected via wireless technology to the internet and beyond. So probably by now you realize that when you're on Wi-Fi, you have to first choose your network. And you might choose your network from a drop-down menu on your computer or the like, or it might auto-select it. But there's at least 2 types of networks. One that are unsecured, and then 2 which are secured in some way. And odds are you recognize, and you've already been taught through practice to recognize the little padlock icon on your phone or laptop or desktop as signifying that your Wi-Fi connection is indeed encrypted. Now, what does that actually mean? Well, in particular, in this context, it would mean that any of the traffic, any of the internet packets of information, so to speak, like envelopes of information going from your device off onto the internet, are somehow encrypted, at least encrypted until they reach whatever device your device is talking to wirelessly. So you have a encrypted connection between that wireless device, often called an access point. Now, what is the actual technology that's being used to secure Wi-Fi networks nowadays? Well, hopefully you're using among the latest versions of this, Wi-Fi Protected Access, or WPA. And this has evolved over the years, and there have been a few different versions. And so in general, whenever you configure a phone or whenever you configure a laptop or desktop, ideally you're connecting to a device nowadays that supports this technology and the latest version thereof. And in a nutshell, what that ensures is that indeed your traffic from your phone, laptop, or desktop is somehow scrambled between you and that other device. And that device, in turn, is probably connected to devices called routers, computers that route left, right, up, and down information on the internet, which might then connect to other routers until it finally reaches its destination. So for our purposes, though, Wi-Fi protected access and using a secure Wi-Fi network is only technically encrypting your traffic between you and whatever device is maybe on the wall, on the ceiling, nearby, the little thing with antennas perhaps, that you yourself are actually talking to. So why do we care about this? Why do you want even your Wi-Fi connection, for instance, to be encrypted? Well, it turns out a lot of what you and I do on the internet isn't necessarily encrypted already for us. Now, fortunately, this is decreasingly the case. The world has gotten better about using more and more encryption in various products and software and applications that you and I use, but not necessarily, because odds are even some of you are probably in the habit of typing http://www.example.com or whatever domain you're actually trying to visit. Now, maybe you don't type even that, but you're certainly familiar with this prefix, this acronym HTTP, which stands for Hypertext Transfer Protocol, which is a fancy way of saying that this is a protocol, a language that computers use when talking on the World Wide Web, or web for short. So what do we mean by that? Well, if you're sitting down at a browser on your phone or laptop or desktop, and you're visiting a URL that starts with HTTP, your device is about to communicate with some remote server using this protocol, this language, really a set of conventions for talking between each other. But the catch is, per last week when we focused on the security of our data, the information or the packets of information that we're sending from browser to server and back are vulnerable to eavesdropping potentially if you're only using HTTP. Well, why is that? Well, HTTP by definition is not encrypted. It's just text messages, often English-like in nature, but they're not at all scrambled, which means if Alice is sitting at her desktop or laptop or phone and trying to visit some website, here represented as our friend Bob, there could be some third party, Eve, who's eavesdropping in between, a machine in the middle, so to speak, that could be looking at every request Alice is making and every response that Bob is sending, if again, Alice is the user in the story and Bob is the web server in this story. So you're vulnerable if you're only using HTTP and certain other protocols or technologies to these machine-in-the-middle attacks. And the attack in this case might just be someone nosily trying to know what it is you are doing on the internet. But worse, they can even manipulate what you're sending or receiving if these systems are not using some form of encryption. So let's take a specific example. When you visit a website on the internet, you are downloading effectively a language called HTML, Hypertext Markup Language. If you take a course like CS50 itself or an introduction to web development, you'll actually learn a language that looks a little something like this. And I've shown only the highlights using ellipses here, ... to wave my hands at details that won't matter. But this is the kind of text or language that we get back from a server when you visit something like http://www.example.com. But notice that this doesn't seem to be scrambled. Even though it might look cryptic to you if you've never written or seen HTML before, it doesn't look like random zeros and ones, certainly. It looks pretty intelligible. And in fact, it looks somewhat English-like with words like body here. Well, the catch is, if this is the response coming back from a web server to a web browser, for instance, Alice's own, what could happen is that some eavesdropper, some machine in the middle, could actually inject additional HTML code into the web pages that you and I and Alice are downloading. Now, what is this representative of? Well, this is another feature you might learn in a course on website development, but let me highlight just one key phrase here because this is a common use case. It is possible, therefore, for a machine in the middle to inject something like advertisements, or worse, something actually malicious that tries to steal your data in some way. But a common scenario for this machine-in-the-middle attack is when your internet service provider, or the coffee shop whose Wi-Fi you're using, or the hotel whose Wi-Fi you're using, wants to inject advertisements into maybe each and every web page you are visiting, even if those web pages weren't even designed to have advertisements. These things might be prepended to the very top of the page, for instance. Now, the reason that machines in the middle are able to do this, though, is simply because if you're not using encryption and Alice and Bob are communicating insecurely in that sense, well, there's no telling what they could add to the responses that are coming back from this web server. Let me pause here before we move on to yet other threats to see if there are now any questions on this particular attack.
How to detect machine in the middle and get rid of it?
A really good question. So how can you detect a machine in the middle and get rid of it? That certainly should be a worthy goal. Short answer is you cannot necessarily detect it. It is possible that a machine in the middle can be doing all of this without your own knowledge. How do you get rid of it? Well, that too is going to be the focus of today. Namely, encryption is going to help us push back on exactly this threat. But first, let's consider some additional threats or concerns that we might have. And one of them technically is called packet sniffing. So again, a packet is a virtual envelope of sorts that you might use when sending data on the internet. And so in fact, here is a pretty standard envelope in which in the human world, I might put a letter and then write something on the outside and send it off to someone through the mail system. Well, you can think of packets in the context of computer systems as being analogous to this, whereby this is an envelope whose purpose in life is to get data from one point A to another point B, so from Alice to Bob. And inside of this packet is the actual message that Alice is sending to Bob, and Bob is hopefully sending back to Alice. So it might not all fit in one packet. So indeed, the internet tends to use multiple packets like these, but that's an appropriate metaphor to think about what it is we're doing here, otherwise digitally. So packet sniffing then is kind of like trying to get a sense of what's going on inside of these envelopes. And indeed, if the contents of these envelopes are not encrypted, scrambled securely in some way, well then any machine in the middle can technically take a quick glance inside of these envelopes, so to speak, see what's inside of them, even change what's inside of them as we've seen, and then pass it along. So what are the implications for what this makes possible, therefore, if you are vulnerable to packet sniffing by, again, not having your systems use encryption when they are talking to one another? Well, here, for instance, is one example of what could be inside, metaphorically, an envelope like that. This is the kind of message, written mostly in English, that represents a browser requesting a web page from a server. In particular, when you visit a search engine, for instance, and type into the search box what it is you're searching for, maybe you're searching for cats, what happens is your phone or your laptop or your desktop creates a virtual envelope like that, opens it up, puts inside of it a message that looks like this, closes the envelope, and then sends the envelope off onto the internet to a web server that conversely is going to open the envelope, read this message, and hopefully send you back a whole bunch of search results about cats. Now, most of this is arcane detail that we don't particularly care about, including where it is we're visiting for this story. I'm using example.com as just something generic, but you could imagine it being Google or Bing or the like. Here you have a command get, which means literally get me a web page. /search is implying that I'm searching for something, but here's the interesting part. What I'm searching for is a query for cats, where a query is a question or a search request of yours, and cats, of course, is what I'm searching for. So this is to say, inside of this envelope, whether you're searching for cats or dogs or anything else, there is some mention of that search query inside of the message inside of that envelope that's being sent from Alice to Bob, or from you to Google or Bing. Lastly, there's this mentioned here, which is referring to exactly the same protocol, HTTP, in this case, perhaps version 3, but ultimately, it's the yellow highlighted text here, that mention of cats, that's worrisome if some machine in the middle, some adversary, can sniff this packet and see what's going on inside. Now, there's other threats similar in spirit. When you request pages on the internet, you don't sometimes just search for information like cats, which I don't really care about if people know, since everyone else on the internet is searching for cats. But what if I'm trying to check out on some website like Amazon and buy something with a credit card? Well, then what is inside of this envelope is some text that looks fairly similar. We still have a host in this story of example.com. I'm still using HTTP. I'm not getting information per se. I'm posting information akin to uploading my credit card to the server. And in particular, down here is a representative of how my credit card might be stored inside of this virtual envelope. And if I highlight that, indeed, you'll see a credit card number that hopefully doesn't actually work, but it is the right length. If anyone sniffs this packet, they might actually be able to find my credit card and maybe my name and my address and the little code that you need and more with respect to whatever it is I'm checking out for. So it's that easy if the data is itself not encrypted. Let me pause here then too and see if there are any questions.
If someone is performing an attack right from a machine in the middle, does the person actually have to be like connected to the same Wi-Fi network as you? Or they could be on a whole other network?
A really good question. So in general, they would be connected to the same Wi-Fi network so that they are Generally, they would be connected to the same Wi-Fi network, but even that is not necessary, so long as they are within reasonable proximity to you, and their laptop or their device has an antenna that can receive all of the wireless packets that are around you. They don't necessarily have to have access to that same network, especially if it's unencrypted. And in fact, there exists software that can listen to all possible networks that are around you, and so that too is a potential threat. Other questions on this here?
Do people have to know your IP address in order to be able to see what you're doing or read what websites you're going to?
A really good question. For those unfamiliar, an IP address is a unique identifier that every computer on the internet has, much like you have a postal address to which humans can send mail. Short answer, Mehal, is no. Like someone does not need to know your IP address in advance for at least these wireless attacks, because they can simply, as per my other response, listen to all of the wireless traffic nearby, and they can actually see the IP addresses of senders and receivers flying by, so to speak, throughout the air. So what's another threat we should be mindful of? Well, it turns out that most anytime you visit a website nowadays, one or more cookies are installed in your computer. Now, what do I mean by that? When you actually visit a website for the first time, particularly one that you need to log into, and therefore that needs to remember you when you click on different pages, for instance, to access different emails, add different things to your shopping cart, what the server actually does is a little something like this. The server responds to your request, for instance, after logging in, with an HTTP response that first says 200, which is code for OK. It's a so-called status code, similar in spirit to the 404 you might have seen in the real world, but 200 means OK. And then it additionally sends this line of text inside of a virtual envelope that gets sent back to you. Set-cookie, and then this key value pair, so to speak, a word like session, then an equal sign, then a value. Now in practice, the value is actually pretty big and random with numbers and letters, but I picked something easier to pronounce for today's purposes, 1, 2, 3, 4, A, B, C, D. And what this is similar to, actually, is as though when you visit this website, your hand is being stamped. Right after you've logged in, the server is now sending you, browser, this piece of message to say the equivalent of, your hand has now been stamped. And so the next time you click on a link on that same website, it's as though you present this hand stamp again and again and again, instead of having to input your username and password again and again and again. This is a more seamless way, supported by HTTP, to just remind the server, I'm still David, I'm still David, I'm still David, by having virtually stamped my hand, and that's implemented by way of this cookie, so to speak. So the cookie is exactly what's in yellow here, and a session is just a concept that refers to the ability of a server to remember who you are. It's like your shopping session in the context of a website like Amazon.com, where you might have a shopping cart that you want to keep adding things to. The website wants to remember what's in your cart, therefore the website needs to remember who you are, therefore the website's going to check your hand stamp, much like an amusement park, a bar, or a club might once you've already shown them your ticket or your ID. Now, subsequently, when your browser visits the same website again and again, it of course doesn't have a hand to show like this, so rather it sends its own message via HTTP inside of its own virtual envelopes back to the server. Every time you click another link, add something to your cart, open a new email on the site into which you've logged in. So here I'm just getting the homepage of this server, and then I'm sending not set cookie, but cookie. This is the textual equivalent in HTTP of my presenting my hand with that stamp. I'm sending the exact same value as before, session equals 1, 2, 3, 4, A, B, C, D. That's how the server knows at this moment in time that this is me, David, and not you, for instance, even if you have logged in separately on your computer, because you on your computer would have a different value for this cookie. Now, this cookie might be generally stored in memory temporarily, or it might actually be installed longer term on your computer for a day, for a week, a year, depending on how the server's been configured. But the catch with these cookies, even though they do solve a very useful problem of retaining state, that is, remembering who you are, they make you vulnerable potentially to what's called session hijacking, at least if you're not using encryption That is HTTPS, because if you're using HTTP, all of the contents of those envelopes, including the set cookie line and the cookie line, are just being sent back and forth in the clear without any encryption at all. Now, what's the implication of that? Well, if an adversary is somehow listening in on your internet traffic, wirelessly or via wires, and they see your unencrypted HTTP traffic going back and forth, and they see in this traffic, inside this virtual envelope, oh, David's session cookie happens to be 1234 ABCD, there's nothing technically stopping an adversary now from sending its own request like this to that same server, but copying your cookie and essentially pretending that that cookie is the adversary's and not just mine. The implication, therefore, logically, is that when I visit that website, I might still be logged in, but when the adversary visits that website by using this technique, they might be logged in too, but as me. So here too, the solution really is just to ensure you're using encryption, namely HTTPS in this context, to ensure that not only are all of the contents of these messages encrypted that you care about going back and forth, so are these lower level details that you might not have even known about, namely these cookies that are going back and forth. Now, what is HTTPS doing for us? Well, it's ensuring that the connection between Alice and Bob is completely encrypted, that is scrambled, so that even if there are other machines in between Alice and Bob, as there would be on the internet, none of them should be able to see what is inside of those virtual envelopes going back and forth. In fact, that's a good way to think about it. Recall that as Alice sends one of these virtual envelopes to Bob, and Bob might send a virtual envelope back to Alice, there may very well be identifiable information on the outside, like the IP address of Bob or the IP address of Alice. But HTTPS ensures that what's inside of the envelope is indeed encrypted, so that even if some other machine in the middle intercepts one of these virtual envelopes, they can't understand what's inside of it. Now, how is that done? Well, it turns out that there's another protocol in the world that handles precisely that process of encrypting HTTP traffic, aka HTTPS. And the most recent version of this protocol is called TLS, which, funny enough, is perhaps an acronym that many people have still not heard of, but you might have heard of SSL, which is essentially an earlier version of it. But TLS is essentially the new and improved version of SSL and what modern browsers should now be using. What does this do to go about encrypting your traffic? Well, it turns out it relies on our focus from last time of public key cryptography. And this principle that if you give two parties, A and B, each their own public and private key, using that, you can solve that chicken and the egg problem and actually communicate securely, even if in advance you don't have a shared secret. So recall that asymmetric cryptography allows us to establish a secure connection, even if you've never visited some website or some app before now. So what does it mean for a browser to be using TLS and thus HTTPS to communicate securely with a web server? Well, the web server in this story now has what we'll call a certificate, a digital certificate. And you can think of this for now as really a public key that has been signed by someone else. So the website has a public key and a private key, and the private key, as always, stays private. But in this case, the web server has a public key that's also been digitally signed by some third party. And for now, let's assume that there are some big third parties out there, companies really, that we all, or at least the browser manufacturers, the Googles, the Microsofts, the Apples of the world, all trust on our behalf. And they are the ones signing off on the legitimacy of these so-called certificates. Well, these certificates technically are of a type called X.509 if you're curious about the type of protocol being used, but this is just the standard format in which these certificates live. But you can think of a certificate really as almost a printed piece of paper with some interesting information on it, like the name of the website and how long the certificate is valid for, and also the public key, which we said last time is really just a big number that has a mathematical relationship with that private key as well. Now, who are these big players, these big companies that are doing the signing of these website certificates? Well, you might have heard this phrase at some point if you set up your own website, perhaps. These are called certificate authorities, or CAs. And these are a These are a collection of companies and entities whose purpose in life is to digitally sign certificates, and the various browser manufacturers of the world, Apple, Microsoft, Google, Mozilla, and others, have gotten together and included in their browsers, like Edge and Firefox and Safari and Chrome, a list of certificate authorities that they trust. And if the idea is that if you trust Apple and you trust Google and Microsoft and Mozilla and other browser manufacturers, then by transitivity, you should trust any of the certificate authorities that they in turn trust. So what actually happens when your browser visits a website? Well, it first downloads the certificate from that website, assuming you're using HTTPS. Your browser then calculates a hash value for that certificate by looking at certain fields within it using a special hash function that produces a fixed length representation of the certificate. Now, why does it bother doing that? Well, the next step that your browser does is it does this. It takes a look at the signature on that certificate. It uses the certificate authority who signed that certificate's public key, and then it uses that CA's public key, the signature from that server certificate, runs it through this algorithm here, effectively decrypting the signature with the public key, and that should produce the exact same hash value. That is to say, if you visit a server and it's presenting you with a certificate, and it says that that certificate has been digitally signed by a certificate authority, your browser can use the certificate authority's public key to decrypt that signature, and by way of these hashes, confirm or deny that, yes, that server's certificate was indeed signed by the certificate authority. And again, if you trust Google, if you trust Microsoft, Apple, Mozilla, and that's another question all to itself, but if you trust them and they in turn trust these certificate authorities, the presumption is that you should trust your secure connection with this particular website. Now, with that said, does HTTPS and in turn TLS keep you secure? Mathematically, yes, but you and I as the humans are again the potential weakness here. Why? There's another attack called SSL stripping for historical reasons, but now it refers also to TLS. And what this attack involves is tricking the user into thinking they have a secure connection to a website when they might actually have not an encrypted connection to that website. And worse yet, they might actually have an encrypted connection to a third party, a machine in the middle's own website. So how might this work? Well, if you and I are in the habit of only typing still URLs as http://www.example.com, or maybe you are and are in the habit of just typing www.example.com, enter, into our browsers. Or maybe more likely, you and I are in the habit of just typing example.com, enter, in our browsers. Well, if you watch the URL bar, the address bar in your browser, you've probably noticed over time that even if you type the most succinct of those inputs, it eventually gets converted into a longer URL with the HTTP, maybe with the www, and perhaps even more characters as well. And that's because your browser is just trying to be helpful. Technically, to visit a website, you need to use a URL, and a URL in this case should start with http:// or maybe https://. But your browsers are trying to be helpful, so if you don't even type any of those, it might first try HTTP, and then it might try HTTPS even. But the catch is that if you start your interaction with a web server using HTTP, that alone might be enough of a window of opportunity for an adversary to do something malicious with the packet of information you're sending to the server, and then maybe send you back a response that tricks you into ending up at some other website altogether, or perhaps just the adversary's own website. And they might be super clever and make you think that you have a secure connection to the original website that you visited. So what do I mean by that? If inside of your browser's virtual envelope is an HTTP message like this, which is just saying, get me the home page of example.com. But suppose for the sake of discussion that you are not using HTTPS, you just typed HTTP or nothing at all, and you're trusting your browser to fill this in for you. What might come back from the server? Well, the server could respond with a message that says this, HTTP version 3.307, which is another status code which means redirect the browser to a different URL. This is the browser's way of saying, detour, go to this other URL instead. Well, what location is that URL at? Well, perhaps this one here. But the catch is that if you're using HTTP and therefore your request is unencrypted, and suppose for this story that there is a machine in the middle waiting there, listening to attack you, it could actually be that this response is coming from that machine in the middle and not the actual website that you intended to visit. Why? Because if Alice is trying to reach Bob, but Eve, the eavesdropper, is in the middle, it could actually be Eve in the middle that's responding with this request. So Bob doesn't even know what's going on in this story. But the catch is here, notice that this eavesdropper, this machine in the middle, is particularly clever because they're suggesting that you be redirected per this status code 307 to https://. And odds are you and I are probably in the habit of at least making sure that our browser says secure, or that at least you're at an HTTPS URL. So you might think, whew, good, everything is the way it should be. Now this is very, very subtle, but what if I draw your attention to the actual URL I'm being sent to here? At least on a US English keyboard using this particular font, this is no longer example.com, example.com. This is now indeed examp1e.com. So this is a particularly subtle attack whereby the adversary in this story seems to have bought a domain name that looks very similar to example.com with an L, but they instead use the number 1, which in some fonts and on some screens looks so close to an L that are you or I really going to even notice this difference? The implication, though, of this subtlety is that you might very well have a perfectly encrypted connection using HTTPS to a server, but it's not Bob's server in this story. It's now Eve's server in the middle. So SSL stripping in this case refers to an attack whereby you're sort of stripping out what would be an HTTPS redirection to the right place, and maybe you never even end up at HTTPS, and the eavesdropper in the middle always keeps it as HTTP. But an even more malicious adversary might take it one step further and actually redirect you to their own HTTPS site, at which point you might be vulnerable to the phishing attacks that we've discussed before, where you might provide information into a website that is not actually legitimate. So how can you mitigate this kind of attack? Well, one, if you're a user, a consumer, you could just get into the habit of always typing out HTTPS:/ and then the domain name that you want to visit. I will concede that that can get tedious quickly, but that is hands down the most paranoid solution to implement here, because you know you will end up at HTTPS. Hopefully the website actually supports HTTPS, but most websites nowadays certainly do. With that said, if you're on the flip side of the story and you're actually the designer of the website, the business owner running the website, or you have control over not the browser but the server, there's a few different things that you can do. And in fact, you can use a protocol called HSTS, which is to say you can actually configure your server to provide hints to browsers that, you know what, they should always use HTTPS when talking to the server, no matter what the human has decided. And HSTS here, for hypertext secure or strict transport security, has you, as the administrator of the server, just configure your server to send an additional HTTP header. That is to say, an additional line of text inside one of those virtual envelopes that just informs the server that we really want to be strict about our transport security. That is, we want to be using TLS. We want the user to be using HTTPS. And here, the server is telling the browser, assume that this is the case, that I want you to use strict security for at least 1 year. This is the number of seconds in a 365-day year, for instance. That's just a really long time telling the browser that, yes, I'm going to keep my security on for at least a year, which should be the case anyway. But you can further configure your server to not just output this response in every one of those virtual envelopes going back to browsers. You can even more protectively say, use strict security for subdomains as well. So even if my user is at example.com, also make sure that their browser uses HTTPS for something like www.example.com, where in that scenario, www you can think of as a subdomain because it's part of the example.com domain itself. And so what is this telling the browser specifically? Even though you might accidentally, conveniently visit a website for the very first time using http:// because you typed it or you let your browser automatically fill that for you, If the server responds with this message, the whole point of HSTS is that the second time, the third time, the 300th time, the 3000th time that your browser visits that exact same domain in the future, up until at least a year from now, it will automatically switch you to HTTPS. And it very protectively won't even let you visit the HTTP, even if that's what's in the URL bar. It's just going to say, nope, I've been told to use HTTPS instead. And that therefore decreases the window of opportunity for adversaries to just that very first request that you might make accidentally, conveniently, that's using HTTP. But every subsequent request from your browser, according to this model, will now be HTTPS instead. And you can go one step further too. If you're the administrator of a server, you can also include the keyword preload in this message that's inside of all of these virtual envelopes. And what that will further tell the world is that if the browser manufacturers would like to preload this information into Chrome, into other browsers that humans download, you can even eliminate that first window of opportunity, because you can have your domain name included essentially in the source code for browsers like Chrome, so that when people download Chrome itself, visit your website like example.com, your browser will already know that they should not use HTTP with this website. They should use HTTPS. Questions then on HTTP, on TLS, on HSTS? It's a lot of acronyms, but realize that some of these defenses are available to you as a user, and some of you, if more technical, these defenses are available to you as system administrator.
So you mentioned that there is such websites as exam1e.com, and they very similarly look to example.com. And I know that registrars fight against phishing websites like this, and whenever somebody tries to register a domain that's looking a little bit suspicious, it usually marks it as fraud and suspends it. So how do such domains still exist, and why is it so common?
That's a really good question, and that's great that registrars, who are the companies in the world that sell you or rent you domain names nowadays, are being more vigilant when it comes to your buying a domain that could be maliciously used in this way, because it's so similar to a brand name or an existing website. However, there's a lot of registrars out there, and I would conjecture that not all of them are as good as others at doing that detection. There are hundreds of top-level domains nowadays, TLDs, which means that you could even choose example.something else potentially, and that too might not be caught in this way. Now, eventually, maybe, especially when you use it maliciously, you would eventually get shut down. But maybe it's enough to attack one person or 2 or 10 or 100 before it's actually shut down. So these remain theoretical and actual attacks, but there are certainly ways to push back on this. A good question. Others from the group?
I would like to know that is HTTP is the best solution for cookies and super cookies to prevent from attack, or should I clear the cookies frequently?
A good question. Unfortunately, super cookies cannot be stopped at the browser level. Super cookies refer to a type of cookie that's embedded by your company, your university, your internet service provider, and you would have to opt out at that level. So for context, for Americans in the group, AT&T and Verizon started doing this a few years ago, where they were injecting cookies into cell phone customers' HTTP requests. You literally and stupidly and obnoxiously have to log into your Verizon.com or your AT&T.com account via the web or the app and opt out of this. So one thing to your question here, super cookies are actually super annoying, super difficult, super dangerous in that sense, because they can happen without your knowing. However, if you are using HTTPS, that should decrease the probability of this happening, because if your data is encrypted, your company, your university, your internet service provider can't insert the cookies into those encrypted messages unless, and we'll talk a bit about this more later, unless you have given permission to your company or university to install special software on your Mac or PC. So in short, simplest advice is always use HTTPS, and if you have a cell phone provider, Google around, find out if they might be doing this to you, and if so, figure out if you can opt out How about one more question here?
My question will be like from a macro perspective, will it be feasible in the same way that there are machine in the middle attacks, machine in the middle verifications? Like, you know, that a request from, let's say, my cell phone to the Zoom meeting right now needs to do so many hops to reach the server, right? Will it be appropriate if between each hop every packet will get like a stamp, like a passport to verify the integrity of the connection?
Potentially. The catch is, and if I'm understanding the question correctly, the catch is you, I, we don't control all of these machines in the middle when it comes to routers. So it's possible to do what you're doing, but there just isn't coordination at that level. And so per our discussion last week of end-to-end encryption, in general, it's best that the sender and receiver worry about doing the encryption, because that way you don't have to trust anyone in between you, any machines in the middle, so long as you are using a protocol that supports some form of encryption end-to-end. So how else can you keep your systems secure, particularly when they're communicating with others? Well, another technology with which you might already be familiar is this, a VPN, or a virtual private network. Now, whereas HTTPS only secures your web traffic between browser and server, a VPN is, dare say, a more powerful technology because it encrypts all of your internet traffic between you and whatever VPN server to which you're connecting. So how does this work? A VPN allows Alice and Bob to establish a encrypted channel that even if there are machines in the middle, routers or otherwise, that shouldn't matter because Alice and Bob are using cryptography to encrypt all of the information going in between points A and B. Now, how might you use this? Well, it's very common if you work for a company that itself has servers that you might need access to, whether it's email or files or anything else. You might, from your laptop, have to, by policy at that company, connect to your company's servers via VPN, virtual private network. That is to say, your Mac or PC or your phone have special software that you start up. You probably log into using minimally a username and a password, maybe using a two-factor code, maybe using a USB device that you have to connect to your computer. You have to somehow authenticate to that VPN. And once that software is up and running and authenticated against the VPN server run, in this case by your company, all of your internet traffic thereafter should be encrypted between you, point A, and the company, point B. The motivation for that is that this way the company can ensure that no matter what services you are accessing inside of the corporate network, be it email or files or maybe video conferencing or something else altogether, no matter what, by nature of that VPN, all of that traffic is encrypted. But you should realize, too, that VPNs have a few side effects, perhaps good, perhaps bad. When Alice connects to Bob, if Bob is the VPN server, she has this encrypted tunnel. This is what we mean by a virtual private network. She has this encrypted tunnel to Bob, which typically makes it appear as though Alice's IP address, her internet address, her unique identifier on the internet, is actually that of Bob and not her own. That is to say, if Alice connects to her company's VPN server, she then gets another IP address from her company's own VPN server effectively. So if Alice then visits gmail.com or amazon.com or any other website, those websites will actually think that Alice's IP address is that of Bob and not Alice. So this is very commonly used if you're in one country and you want to masquerade as though you're in another. And this might be because you need to in order to access company resources. Perhaps from a show of smiles, this might be because you want to access a streaming media service that you don't have access to when you're in one country or another. The point, though, is that you have this encrypted connection between points A and B, and thereafter you can visit any website, any service, as though you are physically at location B. Beyond that, there are other technologies that you can use to encrypt communications, and this one's a little more technical and used by programmers and system administrators alike. There's a protocol called SSH for Secure Shell, and this is a technology via which you don't necessarily encrypt all of your traffic between point A and B, although you can use SSH to create the equivalent of a virtual private network or VPN. But SSH is all about connecting to a remote server and executing commands on it. So not executing commands on your your own machine ultimately, but on some other machine that's maybe inside of your company, your university, or somewhere else in the world. So for instance, if curious as to how this works, you might recall that in a previous class I wrote some code on my computer, and then I opened up a terminal window that started with this prompt, a $sign. It doesn't mean currency. It's just a tradition that the $sign means type your commands here. But at the time, I was typing them on my laptop here on a local server, if you will. If I, though, want to use a computer to remotely connect to another and then remotely run a command, it might work like this. Here I am, let's pretend on my own computer, and suppose I type out one command like the date command. If not surprisingly, this will tell me what the current date is. So suppose that where I am on my own computer, it is Thursday, January 1st at midnight Eastern Time in the year 1970, for instance. If, though, the next command I run is not date again, but I use SSH, and I connect, for instance, to, how about our friends at Stanford University? So I'm going to SSH into stanford.edu's server. As soon as I'm at that server now, I get another prompt in this case. But if I now run the date command, what you'll see is that the date is now apparently slightly in the past, at least if I type this quick enough so that the seconds weren't off. Wednesday, December 31st, 9 p.m. Pacific time in the year still 1969. So this is to say SSH is actually a very common technology used in the world of software engineering, system administration, when you want to control one server from another. And what's powerful about it is that everything I just typed after that SSH command, even as innocuous as the date command is on Stanford server, would be encrypted. So no one between these points A and B would be able to know what I'm controlling or what commands I have typed. All right, let's go ahead and take a 5-minute break. And when we resume, we'll look at some other building blocks of systems that both solve problems but also create vulnerabilities for us as well. Back in a few. All right, so let's talk about now what's actually been on the outside of these virtual envelopes that's helping these envelopes get from their source to their destination. So it turns out that on the outside of these envelopes, minimally, is what we'll call a port number, which is literally just a unique number that the world has decided on that uniquely represents the type of service that that envelope is destined for. So for instance, if you at your browser were going to pull up a website like http://www.example.com, on the outside of that envelope would not only be some mention of www.example.com, but also a so-called port number, namely 80 by convention, which means that this envelope should be opened not by the other server's email server or chat server, but by its web server specifically. Now, if the web server were to respond to us by saying, we want you to use HTTPS instead, essentially redirecting the browser to a secure version of the website, my browser would then have to send a second request to the server, this time still mentioning www.example.com, but on the outside of that envelope, among other details, would be a different port number, namely 443. Now, these aren't the kinds of things you have to memorize, but the computers certainly know what they represent. And in fact, common numbers include 80 for HTTP, 443 for HTTPS, 22 for SSH, and hundreds, if not thousands, of other numbers as well that humans decided on, but the computers actually rely on to know what piece of software on a computer should actually expect and open up these virtual envelopes, these things we've called packets. So what's the problem or danger here? Well, it turns out that your computer can be listening for internet traffic on none of these ports, in which case it's completely disconnected from inbound connections. But very often computers, especially servers, are listening, so to speak, for envelopes destined for maybe port 22, maybe port 80, maybe port 443, maybe others as well. So you might think, well, that's not great, because if these numbers are standardized, then adversaries could maybe try to access my server via those port numbers because they too know what they are. So you might think, all right, well, let me run my web server on a number other than 80 or a number other than 443 and just choose a random number between like 0 and 65,000 or so, because the odds that the adversary is going to guess that are much lower. SSH, you might consider doing the same. But unfortunately, it's all too easy for adversaries to wage this kind of attack known as port scanning. And recall that we did our own brute force attack in classes past on our own passwords, for instance, trying to figure out all possible passwords that might be locking a phone. And it's not that hard to use code very much like that with a loop of some sort that just tries every possible port number between some range, roughly 0 to 65,000. So port scanning refers to the equivalent of knocking on the door of every possible port number on a server. Now, most of those doors might be closed and no one might be home. That is, they might not be expecting any traffic or visitors on those numbers. But by writing software that tries all of those port numbers, you can essentially discover services that are running on certain computers. Now, hopefully that in and of itself is not a problem, because most likely the purpose of these services is to be on the internet. But hopefully these services too are using encryption. Hopefully they're using authentication. But that's not always the case. So security through obscurity, so to speak, running services on random or arbitrary non-standard port numbers is not really a good practice unless you're additionally defending against all of these common attacks. Now, in the world of port scanning, though, it's a specific example of what we might call penetration testing more generally. Penetration testing, or pen testing, is actually a skill, a technique, a job even, whereby you are hopefully not an adversary, but hopefully a well-paid consultant whose purpose in life, or whose vocation in life, is to actually try to penetrate someone's network or penetrate someone's system. And what do I mean by that? Well, maybe quite simply, you try scanning all of the ports on their servers just to see if there are ports that are open, that is listening, that shouldn't be, because no sense in opening a door if no one's meant to go through it. Or you might try to penetrate their network or system in some other way. Maybe you might try to brute force your way through passwords. Maybe you might try to socially engineer the employees of that company or the like. So penetration testing is all about someone who, for good purposes, is trying to find possible weaknesses in your infrastructure so that hopefully you can pay them and thank them, but then fix those problems before actual adversaries try to exploit it for malicious purposes instead. So this might also be referred to as ethical hacking, where you get all of the cachet of being a hacker and really good with computers, but the upside of doing it ethically, which is to say that if you are in the business of trying to find faults with systems, you don't have to do it for illegal financial gain, but for very much legal financial gain instead. As in, someone will pay you to find faults in their system so long as you tell them and only them first, so that they can actually fix the same. And in fact, in this world, there's a gamification of it of sorts in certain companies where you might have a red team whose purpose in life in this game is to actually try to penetrate the network or find some faults, and then the blue team, so to speak, whose purpose in life in the story is to defend the systems against those attacks. And so that too has often yielded better results for some folks, given that it helps them find weaknesses before adversaries who don't work for them do. So how might you keep these attacks out? And how might you keep even penetration testing out in a good way to demonstrate that, you know what, we are actually pretty secure? Well, there's this technology with which you might be generally familiar by name, namely a firewall, which actually comes from the real world. Typically in buildings that might have multiple stores, there might literally be a firewall between two of the stores so that if there's a fire in one store, it doesn't somehow propagate next door to the other store. Now, in the virtual world, a firewall is essentially a piece of software between you and the outside world, or between you and some other network that keeps data in the network that you don't want to leave it, and it keeps out from the network data that you don't want coming in. So for instance, if you might within your company or university or home have some sort of local chat service or intercom system or the like, none of that traffic ideally should end up on the public internet. So you might want your firewall to block any intentional or accidental attempts to transmit that data outside the network. Conversely, if you have a private network that you only use for home computing and watching streaming media and the like, you are not yourself a server, and you certainly don't want random on the people trying to connect to your laptops or desktops or servers in your home. You might want your firewall to keep all internet traffic out. Now, with that said, there are some problems when you want to use services where you do need to talk to someone on the outside world, maybe like a Zoom call or the like, but there are technologies that help mitigate this, so these firewalls are not necessarily absolute. You can open them up or poke holes in them, so to speak, to allow certain services through. So how might these firewalls actually work? Well, they might simply block traffic, that is, internet packets, based on IP address. Because recall, on the outside of those virtual envelopes is not just port numbers, but also, and not quite the domain name like www.example.com, on the outside of those envelopes is actually the unique address of a server to which you're sending a packet, and the unique address of a client that is expecting some response there too. So an IP address is just a numeric, unique address for, let's say, every computer on the internet. It's a bit of a simplification, but it's very similar to the postal addresses that you and I use to send mail, old school style, or postcards throughout the postal system as well. So you could quite simply, if you as a parent, for instance, don't want your kids accessing social media within the home, you could just configure your home's firewall to prevent access to the IP addresses of known social media sites. And so if the kids are trying to use the laptops or desktops in the home to connect to those IP addresses, it would effectively be blocked and not allowed through, so long as the software in question, the firewall, knows or can figure out what those IP addresses are. Now, that said, it's not fail-proof. All it takes is for someone in the home to have some out-of-band device, like a cell phone, that uses the mobile phone network. And then, of course, you circumvent the firewall that might be based only on your home network. So you have to keep in mind exactly what it is you are firewalling and which networks they're in. Now, you might not want to block access to sites based solely on their IP address, but perhaps based on those port numbers. So for instance, if you wanted to block all internet traffic in or out of a network, you could just use your firewall to block all of those port numbers. But if, wait a minute, you realize that you still want to be able to remotely control a computer or server in that network, you could open up just one port number, for instance, 22, if you want to allow SSH back and forth, or whatever port number your preferred VPN software uses instead. So you can use firewalls to block traffic based on IP address, based on port number, or even more sophisticatedly via deep packet inspection, which is a big way of saying that even the most sophisticated of firewalls can actually open up, theoretically, these virtual envelopes and see what's actually inside them. And this way you can even more reliably block certain sites by their domain name, not just their IP address, but by their name. You could, for instance, via deep packet inspection, keep an eye out as to who is emailing whom. For instance, corporations that are very concerned about their intellectual property, ideas and products that they have internally, they might use deep packet inspection to make sure that you and I are not emailing the press about some new product under development, or emailing the competition or anyone in the outside world about some product, because via deep packet inspection, you can pretty much look at everything inside of this envelope, be it the sender, the receiver, the contents of the message. But you can also use this too, not just for confidentiality and the like, but also, for instance, to check for malware and malicious software. That is to say, maybe attachments that you don't want to allow through. And we'll consider exactly what those threats might be in just a moment as well. Now, how might a company, a university, or even a home implement this kind of firewalling, or more deeply, this deep packet inspection? Well, we're essentially describing a technology that you would call a proxy. And a proxy is very often a server, though it doesn't have to be an actual physical server. It can be a piece of software running in your network. A proxy is a device that essentially implements a potential machine in the middle attack. But it's not quite an attack in this way. It's by design. A proxy is a device, a server, or a piece of software that sits between two other points. So in this case, Alice might be someone on the inside of a network. Bob might be someone on the outside of a network. And Eve, in this case, is eavesdropping literally because her role in this story is to be that of a proxy. And the proxy takes data from one side and ideally maybe hands it out to the other. But this proxy might indeed be eavesdropping, might be a little nosy. And so as a packet comes in this way from Alice, might look in the packet and decide, we're not going to send this to Bob, and then it might just be dropped or effectively deleted. So companies, universities, even home networks can use proxies to decide yes or no whether or not to allow certain traffic through. So in that sense, they're very similar to a firewall. But sometimes proxies are something that have to be configured even for your own devices, because there might be only one path out of a company network, only one path out of a university. But the catch here is that literally all of that traffic by design now is going through this middle point. And here's where things can get troubling, especially if you do attend a university or you do work for a company where they may be issued your laptop or desktop or phone. So if your company or your school has given you a laptop or desktop or phone, that might be nice that this is one of the perks to have this hardware. But if they have pre-configured it with software, realize that there are implications of that. You might have your own username and password on that laptop or desktop or phone, but they might have installed administratively, with root access, so to speak, some kind of software that could actually be monitoring everything you're doing on that computer. And this is not uncommon in the corporate workplace. But they can also do things more technically. Like they could install their own certificate authority on your laptop or desktop or phone, essentially adding to the list of certificate authorities that Microsoft and Google and Apple and Mozilla have baked into their own browsers. The implication of this is that even if you think that you as Alice can securely communicate with Bob, and maybe Bob in this story is gmail.com or amazon.com or facebook.com. Even if you think that Alice and Bob Alice, can communicate securely with Bob and establish a connection between https://gmail.com. If your browser, that is your phone or laptop or desktop, has a certificate installed by your company or university that's acting as a CA, or certificate authority, essentially your computer could be tricked into thinking that you're connecting to the real gmail.com, but you're actually connecting to the company's proxy server. But because you have this additional certificate on your computer, even though the company is masquerading, pretending to be gmail.com, you're actually connected to their proxy server. And they might actually be forwarding your traffic somewhere else, but this is a definition of a machine in the middle attack, but it's facilitated by someone else having used our technologies that we talked about earlier to trick, really, your local device into thinking that this is the real gmail.com, whereas the math might actually be based on the company certificate, not on Gmail's own. So be mindful of that again whenever you're using a device that has left your control or has not always been under your control, that you do not necessarily know what is installed on it. So how else might a company, a university, be observing or keeping an eye out, either for good or evil purposes? Well, they actually might also be doing something that we might call URL rewriting. So if you have a company or school email address via which you receive mails from the outside world, you might notice that whenever an email contains a link, if you hover over the link and look in like the bottom corner of your browser, it might actually not go to the actual link destination that you think it does. It might actually go to a URL like this, maybe https://example.com URL equals something. And the implication of this here is that what companies and schools might do to combat malware, maybe malicious software that could be accidentally installed or sent your way via URLs, or to prevent you from accessing phishing websites that are trying to steal your or the company or the school's information, they might automatically, through some kind of proxy server, acting in this case on email, change every URL in an email you receive to be example.com, and then embed at the end of that example.com URL the actual URL so that you can still reach your destination. But the implication of this is that if you click on this link here, you're first going to visit example.com. That's going to include some data from that proxy server that has added URL equals something, where something might be gmail.com, amazon.com, whatever the actual URL is. But because the company or the school in the story controls example.com, they know what URL you're trying to visit. Now, one, they could minimally just log that information and know that, oh, David seems to be visiting Gmail again. Or they could actually check in their database, is gmail.com or whatever this URL is known to be malicious? Is it known to be a phishing website? And they can just prevent you from accessing it altogether. So this is another form of proxying that's actually very explicit because you're embedding the machine in the middle quite literally as example.com or whatever your university or your company's domain name is. But it's all toward an end of trying to help protect you from potentially malicious phishing type websites. But the implication too is that now the company, the school, the machine in the middle knows every link you're clicking on as well. Let me pause here and see if there are now any questions about these techniques of proxying.
I just want to know what's the difference between VPN and also Tor network in a higher level, like, just the difference. Because what I do know is that these two networks are used to encrypt or anonymize our activity or, the data that we're sending. The second question is that, let's say that I'm using a network at a university or a company, and they also have their own, CA, which means that they've got their own databases, like which websites I can get in and which websites I cannot get into. If I'm using VPN, does that mean that, the university or the company know what I'm doing?
Good question. So Tor is the anonymization software I was alluding to a moment ago in my previous answer, and we'll talk about that in our final lecture. Tor really is about privacy preserving. So it's about covering your tracks so that, kind of like the Hollywood movies, when you're here, your data is bouncing sort of across all of these different servers in the world, and it's sort of difficult to trace it back to its origins by design. So more on that in a couple of weeks' time. VPN is an encrypted connection just between one point A and another point B. So even though they can't see what you are doing, it is very obvious where your data is coming from thereafter. So legally, for instance, if the VPN server or company were to be subpoenaed, they might have to disclose information about you. And so it's not quite as privacy preserving. It secures your data, but it doesn't preserve your privacy in the same way. On your other question about what you're doing, especially when you're on a VPN, if someone has installed with administrative privileges software on your computer, like, all bets are off. You cannot trust the device. So if they've installed their own certificate on your computer or a CA to the list of trusted things, anytime you use that browser, for instance, like, you are vulnerable to a machine in the middle attack or at least a proxying type implication. Beyond that, but honestly, at that point, if they've installed special software on your computer, they could be monitoring everything you do on the internet anyway. So sort of all bets are off. So what is it we're trying to keep ultimately out of our systems? Well, I dare say malware is perhaps one of the biggest threats. So malware or malicious software is just software that someone has written that can do malicious things. And that's sort of the nature of software. If you've never programmed before, it turns out that it's not that hard to write a program that, if you run it, like, deletes all of the files on your computer, or maybe starts sending out spam, or maybe starts mining Bitcoin or anything else. Like, software can do anything, and whether it's malicious or not is really up to the human who wrote it or the person who's using it. Now, you might have heard of specific types of malware, for instance, a virus. A virus is a piece of software that attaches itself to a host, just like in the human physiological world. The catch with a virus in the digital world is that you, the human, usually have to do something to get infected. You have to open a file that's infected with the virus and start running it on your computer and loading it into your computer's memory and CPU or brain. You have to click on an attachment in an email that's perhaps infected. So viruses generally require human intervention and really human mistakes. You're exposing yourself unintentionally to a piece of software that can now do anything. And a virus can literally do anything that a piece of software can. So it can delete all the files on your hard drive. It can send spam. It can start Bitcoin mining. It can email all of your files to an adversary. Like, once you have a piece of software running on your computer, all bets are off. So you might wonder then, well, what's the line between a virus and, like, Microsoft Word or some Spotify or some other piece of software you install on your computer? I mean, really, it's ethics at the end of the day. We are trusting that Microsoft Word and Spotify and other software you might install on your Mac, your PC, or your phone just isn't doing bad things. Because very often, once you have a piece of software on your computer, it technically can do anything that the operating system, Windows or Mac OS or iOS or Android, make possible, thanks to those manufacturers. And it really is a code of ethics. It really is perhaps capitalistic pressures that ensure that companies aren't necessarily infecting us with software that's doing bad things. Why? Probably bad for business, if nothing else, if they're caught doing something malicious. But with that said, for historically, it's quite possible for software to be written even within the constraints of an operating system that does bad things. And heck, maybe it's even accidental. It has absolutely been the case that sometimes software deletes things that it shouldn't because some human made a mistake. Now, with that said, gradually the world is getting better at designing better and better operating systems that try to sandbox things. And iOS, which runs on iPhones and iPads and the like, is actually particularly good at this, whereby sometimes annoyingly, apps can't do something without your explicit permission. Now, you and I might not give much thought to just saying, OK, 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 because we want the software to do its thing. But more so than operating systems past, you and I are increasingly being allowed to weigh in on whether some piece of software can use the network, can turn on the camera, can turn on the microphone. So thankfully, we're getting more and more building blocks to mitigate some of these concerns. But there are still viruses in the world, and you can be infected by them, whether it is some file you've downloaded and run or some email attachment you've clicked. But more worrisome is another type of malware that we might call a worm. And a worm is very similar in spirit to a virus in that it's just malicious software. It can do anything. But these things can travel from computer to computer even without interaction by humans. Now, how does this work? Well, a worm, theoretically, once it's installed on one computer, having infected it and running, well, it could do that technique called port scanning from earlier. And maybe it can use that infected computer's internet connection and just start scanning the local network or a broader network for IP addresses of other computers and ports of other computers. And if one of those computers' ports happens to be listening, and for unfortunate reasons, that computer is not using encryption, it's not using authentication, and it's vulnerable somehow, theoretically, that worm can travel from computer to computer to computer by making these network connections via these ports at these IP addresses. And that is quite often how they have spread. It's the result of mistakes in software. It's the result of there having been holes in our firewalls, in our systems, by allowing them through via these techniques. So what's the downside, really? Well, beyond just wreaking havoc on your own computer by deleting all of your files, spamming people, Bitcoin mining, and the like, actually what adversaries have increasingly been doing over the years is creating botnets, so to speak. That is, it turns out it's more valuable to an adversary not to completely disable your system, because that doesn't really serve them long term, but maybe to install software on your computer that's just constantly running. And it's not actually doing anything bad to you. None of your files are deleted, no spam is being sent, but you are infected. And there's just some piece of software constantly running on your computer. But maybe this adversary has somehow figured out how to infect not just your computer, but my computer and your computer and your computer and your computer and hundreds, thousands of other computers in the world. Now, if this software is smart and it's constantly listening for commands, an attacker can send some kind of command, not unlike those virtual envelopes, to this entire botnet of computers and say, OK, computers, now everyone at the same moment start attacking some server. Or everyone at this moment start sending emails. Everyone at this moment start mining Bitcoin. And so you can leverage the network of hundreds or thousands of computers all at once and have a much more powerful attack therefore possible. And what form do those attacks take? Well, quite often what we'd call a denial of service attack, or DOS. And this is exactly as the name suggests. Sometimes adversaries' goal in life is just to deny service to everyone else, whether it's for political reasons, financial reasons, or the like. It's one thing for me on my laptop or my phone to maybe visit, maybe I'm a little annoyed at Google today. So I go to google.com, and then I keep hitting reload, 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 or faster, reload, 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 reload. I'm trying to deny service to other people, but realistically, Google has way more resources than me. So a denial of service attack only really works if you have a lot of resources yourself, more resources than the site you're attacking. But with botnets, When you control multiple computers, you can actually wage a distributed denial of service attack, whereby, again, you send a command to this whole network of infected computers, and you say, all right, everyone go visit google.com right now and reload, reload, reload. And when it's hundreds or thousands of computers doing it to Google, or maybe not someone as big as Google, but maybe a small business that they're annoyed at or they're competing with, you can, via distributed network, try to deny service to actual customers or users of that site. Why? Well, a computer, long story short, only has so much memory, only can do so much per unit of time. And if you completely distract a computer or server by all of these requests that are sort of bogus, then the good requests from the real users, the real customers, can't necessarily squeeze in. And so you're denying service to other people. And distributed is particularly malicious. Why? Well, once a company figures out what's happening, like Google, they could just block with their firewall my IP address, for instance, coming from my phone or my laptop or other device. Once they know where the attack is coming from, they can just deny or they can block service there. But if it's distributed, if it's coming from all of us or thousands of people, thousands of IP addresses, then it gets a little harder. Like technically, they could just block all of our IP addresses, thousands of IPs. But very often, you and I share IP addresses. If we're on the same campus, on the same corporate network, even though locally we might have unique addresses, to the outside world, we might all share one public address from our whole company or school. And at some point, it's not going to be in Google's best interest in this story to block all of those IP addresses, because then we might be denying service to actual good people on this campus at this company who just happen to be on the same network as this attacker or as this infected computer. And so that's really the value of attacking computers nowadays. It's not just one thing to get at your computer individually. It's what your computer represents. You are a node, a potential ally on a network of systems. So it's just as well that we try to keep this kind of software out altogether instead. So how? How do you keep it out? Well, for years, you've probably heard about, maybe you've been using antivirus software, and that's exactly what it does. Antivirus software is software you either download for free, maybe pay for, install on your computer, and it's generally constantly running. Or maybe it runs on a schedule to check, are there any known viruses or worms on this computer? And if so, let's delete them, or let's somehow remove them safely. And maybe you have to reboot to get them out of memory, but then maybe you're back in business. To be fair, that might be too late, because the emails, the spam might have been sent, the files might have been deleted, but it at least gets it out of there for the future time at least. But there's a problem with antivirus software alone, in that it has to actually be current for the attacks that you're facing. That is to say, the antivirus software to work has to know about the virus, has to know about the worm. Now, how can you make sure you're always current? Well, you can enable automatic updates with your antivirus software or even your operating system more generally. And in recent years, the world has kind of realized that even though there are downsides of automatic updates, it's generally proving to be, it seems, a net positive for society. Why? Because it ensures that you and I and everyone else are generally running the latest versions of software, which generally means we've fixed security holes, that is, security-related bugs in previous versions, so that at least we're not vulnerable to yesterday's mistakes. You know, we're still vulnerable to today's and tomorrow's mistakes when people continue to write software that's buggy, but at least we're staying current. This also ensures, too, that companies can focus their resources generally on the newest versions of software, and they don't have to worry about being backwards compatible and spending time and effort and distraction on software that might be older and older and older. So enabling automatic updates is generally proving to be a good thing, I dare say. But there are downsides. You know, Google, Microsoft, Apple, and others, they're not perfect. And it has definitely been the case that they or companies have released an update that actually breaks your computer or mine, in the sense that now I can't access it or something went wrong. And so generally, automatic updates are not something you do to all of your customers all at once, but maybe a few, then a few more, and just to make sure that we're not going to break or brick a whole lot of our users' computers. But generally speaking, turning on automatic updates will at least ensure that you're not vulnerable to problems the world has already solved. And this is a good thing, because there's nothing worse than realizing, oh, I've been attacked and there was something you could do about it. You could have updated your software already. But the catch is that there are also these attacks known as zero-day attacks. And the problem with antivirus software in general, and even automatic updates, is that there's still humans involved in this process, whereby they have to realize, ooh, there's a new virus in the world. Ooh, there's a new worm in the world. Ooh, we made a mistake. You have to fix it. You have to update the antivirus software to detect those new threats or those new viruses, those new worms. So a zero-day attack is an example of attack where an adversary maybe writes their own virus, their own worm, gets it out into the wild, maybe on enough computers that they can do something particularly destructive or valuable for them with it, and the world just doesn't have time to catch up. So even if you have antivirus software installed, automatic updates, it might still take a day, a week for the companies who design that software to update those products for you. So even then, you're still vulnerable. And that's why security really is going to be this multi-pronged approach, especially when it comes to our systems. It's not enough to just use antivirus software. It's not enough just to have a good password. It really is a layered defense so that you create this gauntlet of defenses ultimately that adversaries have to get through. And if they get through one, hopefully you're fine. If they get through two, hopefully you're still fine. If they get through three, maybe then you should start worrying. But security really isn't this absolute. Recall from where we began, we really just want to raise the bar, raise the cost, raise the risk to the adversary so that, again, they hopefully lose interest in little old me. So that's it for today's focus on systems. Hereafter, we'll focus on software, specifically on what you can do, whether you use or write software. And thereafter, we'll take a turn to privacy as well. All that next time. All right, this is CS50's Introduction to Cybersecurity. My name is David Malan, and this week let's focus on securing software, whether it's the software you use or whether it's the software you write as a programmer. Consider, for instance, one of our topics from earlier in the class, namely phishing, this attempt by an adversary to phish or obtain information from you. Let's consider today how you might go about implementing this kind of attack, and equivalently how you as the user might go about noticing an attack like this. Well, here again is a language called HTML, Hypertext Markup Language, and it's the language in which web pages are written. This is maybe the simplest example that we could put together that represents the kind of text that a web server would send to a web browser when it wants to display information on your screen, be it the day's news, your email inbox, or anything else that is web-based. ... is where I've put placeholders just to represent where some additional code might actually go, like the content of this actual web page. Well, for instance, suppose that we consider in the abstract just a simple example of these so-called tags. And in fact, recall that everything that you just saw sort of had these open brackets, but also the same words again and again. For instance, if we wanted to have a paragraph in this language called HTML, we would have this thing here called a tag, or an open tag, or a start tag, and then this thing here at the end, a end tag or a close tag. And those are meant typically to be symmetric. This one sort of begins a thought for the browser. Hey, browser, here comes a paragraph. And this one here with the / inside of those angled brackets means, hey, browser, that's it for the paragraph. So anytime you see HTML in a file, it's really telling the browser what to start doing and what to stop doing. So here is how a browser, therefore, might know that it needs to display a paragraph of text, maybe separated by some white space by other paragraphs of text. Here, for instance, is how a browser might know that there's some code inside of the web page, typically written in a language called JavaScript. So this script tag opening here, and this close script tag here would be, hey, browser, here's some code to execute, ... and hey, browser, that's it for the code to execute. So how might there actually be a threat or an opportunity here for an adversary to phish information from you? Well, here, for instance, is how you might, in this language called HTML, create a link, otherwise known as a hyperlink, in a web page. And it, too, uses an open tag and a close tag. This A tag represents an anchor, like anchor some hyperlink, some link in the web page right here. And this tag here means, OK, that's it for the link. And if we want to link, for instance, to Harvard's website, in between that open tag and close tag, would you actually put the text of what the link is meant to be. So if you want the user to see a link on the page that says Harvard, you would put literally Harvard between this open tag and close tag. But that's not actually enough to link to some other page. You have to tell the browser what URL or what file you want clicking on Harvard to actually lead the user to. So for that, we need to introduce one other concept in this language called HTML, namely an attribute. So href stands for hyperreference, and it's a fancy way of saying this is what I want the browser to link the user to when they click on that word Harvard. Now, at the moment, I've just done a ... but that would, for instance, be the URL of Harvard's own website. So consider this very specific example now, whereby we still have our anchor tag opening here. We still have our anchor tag closing here. We now have, though, an href attribute that's telling the browser that when the word Harvard is clicked, I want the user to end up at https://harvard.edu. So that all seems fine and good, and this is the way the web is supposed to work, and this is what links in your own web pages will look like if you poke around underneath the hood. So where's the actual danger? Well, hopefully there is none, and hopefully when you open this kind of HTML in the context of a larger file with even more tags than just this anchor tag, you'd see a browser window that looks a little something like this. You'd see a link, typically underlined, though not necessarily, to Harvard, and then and only then, if you hover over that link, can you see where you will go, even if you don't actually click the link. So suffice it to say, if you just click the link, you're going to end up on Harvard's own website. But if you a little more cautiously, with a bit more paranoia, a bit more consciousness now of cybersecurity, hover over that link and focus in your browser's bottom left-hand corner, typically, at least on a laptop or desktop, you'll actually see the URL to which you will actually be whisked away when you click on that link. So this actually looks OK. The word here is Harvard. The URL it's going to link me to is https://harvard.edu. So I think all is well in the world. And indeed, you can do this on most any web page on your laptop and desktop if you want to proactively, preemptively see where it is you're going to go before you actually click on that link. So where's the danger? Well, let's get a little more specific and a little more malicious, if I may. So here we have the exact same HTML as before, but let's go ahead now and not just say Harvard inside of this open tag and close tag. Suppose that for whatever reason, I want the user to see a little more obviously the URL to which they are going to be linked. So I might change Harvard, capital H, to harvard.edu. So the actual domain name that I want the user to be led to. Here is now what the user would see. So it's a little more obvious that it's harvard.edu and not some other Harvard website. And indeed, if we hover over that, we'll see that it still is going to the same URL. All right, so that seems fine and not all that enlightening. Let's go one step further. Suppose that you really want the user to see a URL in the body of the web page. So now I'm actually going to put in between the open tag and the close tag https://harvard.edu. Now notice this looks a little redundant, and it is in some sense because I literally have the URL in two different places, but that's because those two values serve different purposes. The one in between the open tag and close tag is what the human sees. The one inside of the quote marks, the so-called value of the href attribute, is where the user will actually end up. So if you want them to be equivalent, you have to type the exact same thing twice in this case. So now, of course, if I go back to the web page, the human is now going to see literally this URL, and if they hover before clicking, they'll see confirmation as much. So where are we going with this? Well, here's among the lessons of the course is to think about now how can you take a perfectly reasonable technical solution to a problem, creating a link and a page in this case, and how might an adversary abuse it? How might you as the end user be vulnerable in this case to a so-called phishing attack? Well, there's nothing stopping me from putting anything I want in either this value or in this name of the link. So you know what? Why don't I be a little malicious here, and why don't I tell the user that they're going to harvard.edu, but they're actually going to yale.edu instead, another school down the road. So what does the human see now? If we go back to the browser, they still see what appears to be https://harvard.edu. But if they hover over it, and only if they hover over it, will they see this little clue that, you're actually going to be whisked away to yale.edu. And if they click on the link, they'll actually find themselves at the actual yale.edu website. So what's the big deal? Well, this might just be a silly prank, in which case it's probably inconsequential. And if you do link from one website to a completely different one, it's not necessarily a phishing attack. It might be confusing because the user thinks they're going to Harvard, but they find themselves at Yale. But there's not necessarily any danger in that mislead. But what if the adversary in this case doesn't link to a very common, popular website like yale.edu, but maybe a website like harvard.edu where just one of the characters is slightly misspelled, as we've discussed in the past? Just that you and I, unless we really, really look carefully, we might not even notice that we're not at the real harvard.edu. And what if further the adversary went through the trouble of copying all of the HTML that implements Harvard's website and pastes it into their own fake version of Harvard's website that lives at, again, a URL that is almost the same? Here is now where there's a phishing opportunity, because if you think you're going to harvard.edu and you click the link and it looks like you're at harvard.edu and you don't notice a subtlety like, wait a minute, that's not quite the right URL, you might now be inclined to and comfortable with maybe logging in to the fake harvard.edu website with your username and your password, and voila, now the adversary has that information from you. And it doesn't have to be Harvard. It doesn't have to be Yale. It might be your bank. It might be PayPal.com or something where you could actually lose money, or some other asset you care about. And so that's really the essence of the implementation details of a phishing attack, at least in the context of web pages and or emails. It all boils down to these primitives of HTML being the language in which web pages are written, and adversaries, by knowing HTML, also now logically can misuse HTML by understanding how these basics work. So let me pause here and see if there's any questions about phishing or HTML or this convergence of the two when it comes to this form of social engineering, as we called it before.
Would it be possible to write my IP or some other means to get to their website and not the URLs?
Short answer, yes. If you have access to dedicated IP addresses, which are these unique identifiers you can use for servers on the internet, you can absolutely have a URL that is like http:// and then the IP address. Now, typically it would be HTTP and not HTTPS when using an IP address, in which case that might be a clue to the user that, wait a minute, this is making me nervous, that this isn't legitimate. But honestly, I think we can all think of people in our lives who wouldn't have the instincts to notice, wait a minute, what is this weird numeric address in my browser bar, and stop what they're doing. That's indeed among the goals of the class like this, is to give you those instincts and that training to be a little suspicious when you see something like a raw IP address in the browser. Technically, there's nothing wrong with it, but it's a little bit of a weird branding or marketing decision for a website. And I think a corollary of this then, logically, is that if you are running a website of your own, or if you're running a business with a website of your own, you should really avoid using many different URL formats or many different domains, or having any sort of curiosities or weirdnesses in your domain names, because you're really just teaching users implicitly that your URL format might change from time to time. And certainly you never want to use just an IP address, because you're going to train people to expect that. And so standardizing on one or very few domain names or subdomains is generally best for that. So what are some other attacks that we should be mindful of when it comes to our own software? Well, a class of attacks or category of attacks are generally known as code injection, which is an opportunity for an adversary to somehow inject code into your software and often trick your software into executing that code, even if you yourself didn't write it. Well, let's consider one example of this. A common attack on the web in particular, too, is what's known as cross-site scripting, or XSS for short. Cross-site scripting refers to this potential opportunity for an adversary to trick one website into executing code that they, again, themselves did not write. So what form might this actually take? Well, suppose that you yourself visit google.com, and suppose that Google isn't aware of this particular attack. They certainly are nowadays, but suppose that they weren't yet aware that this attack exists. And so when someone like you or I goes to google.com and searches for something like cats, suppose they do the following. They show you a whole page of search results, and I won't bother showing the actual results, but as of today, there were 6,420,000,000 cats on the internet that Google knows about. And they would show up, of course, down here. Now, notice a few characteristics about google.com as it typically behaves. Well, one, you still see a text box containing what it is you searched for so that you can change it or at least see what it is. And notice, too, that in smaller text here, in this particular version of Google, it tells you not only how many results there are, but specifically how many cats there are. So that is to say, if Google is using your own input, not only to remind you of what you searched for in the search box, but also in the body of the web page, that very simple idea is vulnerable to an attack. Why? Because who wrote the word cats, C-A-T-S? Well, it wasn't Google per se, it was me. Now, fortunately, cats in and of itself is not dangerous, but suppose I knew a little something about HTML and browsers and how the internet works, and suppose that I now, an adversary, did something like this. And knowing that Google is probably inside of their web page rendering HTML that looks like this, a paragraph of text per the open paragraph and close paragraph tag, and an English sentence like this, about 6,420,000,000 cats. If I know they're putting my input, cats, into HTML that looks like this, let me see if I can try to trick Google into outputting something that they might not have anticipated. So instead of cats, let me type something of a little weird that looks like this. Now, what are we looking at? We're looking at now an HTML tag, the script tag, both opened and closed here, and a little bit of code in a language called JavaScript. Now, thankfully, this in and of itself is not actually a compelling attack. It's literally just going to display attack, quote unquote, on the screen. So it's just meant to be representative, I claim, of how I could potentially trick a website like Google into executing code that I wrote, not that they wrote. So what do I mean by that? Notice that I've got this open script tag here and the closed script tag here, which means everything in between there is script. That is JavaScript, this particular language. Well, it turns out this particular language, in the context of browsers, comes with a function, a feature known as alert. And if you want to alert the user with some message, you literally write the word alert, and then an open parenthesis and a closed parenthesis on the left and right. And then inside of single quotes or double quotes, you put whatever word or words that you want to alert the user to. So this is often used for displaying messages to the user. Not actual attacks, but useful messages. And there's more elegant ways to do this as well. But this is the simplest representation of an attack that I could propose here. Now, I haven't yet hit enter on this page because indeed we still see that we're on the page relating to cats as my search result. But as soon as I hit enter, after searching for this string of JavaScript code, or really HTML inside of which is JavaScript code, what might happen? Well, this could potentially happen. Now, again, this is not a bad thing in this specific case. It's just throwing up an alert to the user. And in this sense, too, I'm really only attacking myself. Because if I'm the adversary, and this is my browser, and I've just tricked Google into executing some JavaScript code such that a pop-up appears saying attack, well, I'm just like hacking myself. So this is inconsequential. But again, it's representative of how we could potentially trick a website into executing code that they did not intend. Now, why is this displaying? But notice no more cats and no input here that I typed myself. Last time when I searched for cats, I saw the word cats here. But now I'm seeing nothing at all. Now, why is that? Well, underneath the hood previously, I claimed that Google was probably rendering HTML like this. A paragraph of text, open tag, close tag, and then the sentence about 6,420,000,000 cats. So HTML, and they were just plugging in whatever I, the human, typed in. Well, this time I conjecture that if I typed in what looks like and is HTML with a bit of scary JavaScript code in between, what Google is probably going to try to output in the body of the web page they send to my browser is this: an open paragraph tag and a closed paragraph tag. Still the beginning of a sentence, assuming that there are this many attacks in the world, 6,420,000,000. But notice this. Because I, the user, literally typed in the script tag and the closed script tag, and then that JavaScript code in between, the browser doesn't know that that came from me and not Google. So the browser is just going to read this as, hey, browser, start a paragraph about 6,420,000,000. Hey, browser, here comes a script. That is a program that you should execute. What do I execute? Alert, quote unquote, attack. Hey, browser, that's it for the script. Hey, browser, That's it for the paragraph. So if Google is just blindly copying and pasting what I, the human, am typing in, I might trick Google into rendering HTML that Google did not intend. And the side effect in this case is that I see this alert, but really that's indicative of a potential exploit in Google's website if they were not detecting this on their own. So this is the code that's dangerous. And what then is the fundamental problem? They are just literally outputting what I, the adversary, typed into their page. So how do we go about mitigating something like this to avoid this kind of attack? Well, let's first propose that what we want the effect to be is something a little more like this. Assuming, again, that there are 6,420,000,000 attacks in the world, what I want to see is literally that English sentence here. I don't want any sort of pop-up. So this, I would propose, is the correct behavior, assuming we see more search results down below. I have searched for this. Google is telling me or reminding me what I searched for, but there's no pop-ups in this case. So somehow or other, based on this screenshot alone, there must be a way of ensuring on Google's end that even if the human types in HTML with perhaps some JavaScript code in the middle, that they don't actually treat it as HTML and JavaScript code in the middle. They just display it literally, character by character, whatever I, the user, typed in. So what is our concern with this particular symptom? Well, it turns out that an adversary can wage what we would call a reflected attack, whereby we could leverage this symptom in such a way that maybe we could construct a URL that, if clicked by a user, actually triggers this kind of behavior. But moreover, doesn't just trigger this fairly innocuous behavior like alerting the user with a message like attack just to scare them. But what if we wrote even more malicious JavaScript code that maybe steals their cookies or does something more than that? Well, how do you wage what's called here a reflected attack? Well, let's first consider what a basic link in a web page or an email looks like. It's, again, an anchor tag that starts and ends. It has an href attribute that represents the URL or file to which we're going to link the user, and then some text that the human will actually see in the web page. And now let's notice, when we correctly search for cats as we did before, that not only do we see cats in the text box here, not only do we see cats in the body of the web page, but notice now the URL. It turns out when you search for something on Google, you end up at a URL that looks essentially like this. It might actually be a little longer, but a lot of those parameters, so to speak, in the URL aren't strictly necessary. So this is the shortest possible URL that will work on Google if you want to search for cats. And notice what it is. https://www.google.com/search Q equals cats. So this is to say that the way Google works is that if you want to search for cats, you simply visit a URL that looks like this. If you want to search for dogs, you visit a URL that looks almost like this, but instead has Q equals dogs. Which is to say there's just a very standard format on google.com and a lot of other websites too for searching for things or really sending input to a web server. And this web form or this text box that you typically use to type in cats or dogs or anything else is just generating a URL that looks like this, and then Google knows what to do with it. So how can we leverage now that reality a little more maliciously? Well, let's go back to our HTML, and let's again assume that the adversary is trying to construct some HTML for their own email or for their own website in order to attack some unsuspecting users. Well, instead of the ... let's be more specific. Let's actually, in a good way, in an honest way, say that we're going to let the user click on a word, cats, which is in between my open tag and close tag. And if they click on that, they're going to end up at the legitimate Google website where it's https://www.google.com/search Q equals cats. So this is correct. This is not yet an attack. But what if I am a little malicious, and instead of using the legitimate URL there for searching for cats, suppose I construct something a little more cleverly that says we're going to give them cats, but actually we're going to bring them to this URL. Now this is a bit of a mouthful, and in fact it wraps onto 2 lines this time, but notice the URL starts the same, https://www.google.com/search Q equals, and then some weird text, %3c, script, %3e, alert, wrapping onto the other line, and so forth. So I dare say you're seeing some familiar phrases now, script and alert, but there's also some weird syntax there as well. Now, that weird syntax is just a representation of URL escaping. It turns out that certain characters in URLs, like angled brackets and other syntax, is not good to include in URLs because it might be mistaken by the browser for something else. And so URLs typically escape punctuation symbols and other characters using this % syntax. Now, it looks a little weird to the user, but what's more worrisome is what this is going to be used for on Google's end. If the Q value equals this whole bunch of text, and it's just the browser that's encoding those special characters in this way, what Google's really going to see on its end is the actual script tag with the actual alert and the actual close script tag that you and I constructed earlier. That is to say, what Google's going to receive from that URL is no longer cats, quote unquote, but this, quote unquote, because the server's going to automatically convert the % signs and those weird characters back to the original automatically. That's how URL encoding works. So what the server is going to receive is this. And again, if the server is vulnerable to naively just outputting literally whatever the human typed in, the risk is that they're going to now execute that code. And what if the code isn't just an alert? Maybe it's something like this, which still isn't in and of itself a bad thing because it's just an alert. But this is actually some JavaScript code now, alert, open parenthesis, document.cookie, close parenthesis, that would actually throw up a dialog window that shows the user the value of the cookies they have there on Google's website. Okay, not such a big deal. It's not all that different from just saying quote unquote attack. But what this means is that in JavaScript, you have access to all of the cookies for a website, at least those that are made available to JavaScript. And if an adversary doesn't use the alert function, but maybe uses a little more code to send the value of document.cookie to their own website, or to somehow send other information from the web page, the user's username, or any other personally identifying information, suffice it to say that by being able to write code in JavaScript and by being able to trick a server, like Google in this story, into executing that code, you can effectively, by transitivity, trick a user's browser into executing that code for you. So the adversary is sort of sending the code into Google, and it's being reflected back to some user if they click that same link in an email or a website. And at this point, things like their own cookies might be vulnerable. And again, to be clear, this in and of itself should not hurt you. I'm just using alert as demonstrative of what could be possible, but you could do any number of other things with document.cookie or other values from a web page as soon as you have this ability to write JavaScript that's reflected back into someone else's browser. Any questions then on this particular attack?
I just wanted to ask a question about the JavaScript blockage, because many of the browsers uses to block the JavaScript. How can you use the website and browser which blocks the JavaScript without getting tricked into the JavaScript?
It's a really good question. And the short answer is nowadays that that's not really the best technique to just block JavaScript. The reality is, in this point in time, so many websites, most websites dare say use, if not rely on JavaScript to do any number of features or render their own content. And so it's just, I think, not realistic to just disable JavaScript in order to protect yourself from these kinds of attacks. In a bit, we'll discuss ways to mitigate this kind of attack where you disable some JavaScript, but not all. But in general, I don't think that's a realistic solution, at least on most websites nowadays. So how else might these same principles be misused? Well, it turns out there's another class of attacks known as stored attacks, whereby the adversary's input isn't just immediately reflected back from the server to some unsuspecting user, as it might be when you're using the URL to contain the code. But suppose that a website were vulnerable to actually storing the user's input, even if the user's input includes HTML with some JavaScript inside. Well, that would be a stored attack, and it might work as follows. And at the risk of picking on Google, suppose that when using Gmail, suppose that if you sent someone an email with that exact same code, whereby you're just alerting quote-unquote attack. Again, that in and of itself isn't going to hurt anyone, but it's representative of what you could do with code. Now, presumably, when you send an email in Gmail or Outlook or any other service, that email is going to be stored on a server until it's read and until it's deleted, perhaps, by the user. And if it's never deleted, it's going to stay stored on the server. So this type of attack assumes that the server might actually be saving in a database or a file somewhere the user's input. Now, suppose that here, too, Google didn't know about these kinds of cross-site scripting attacks, and they just allow you and me to input HTML and JavaScript into an email, and they just blindly save it into their database. And then, when the recipient opens this email, they just show the recipient the contents of that email. Well, what could go wrong? Well, if the recipient opens that particular email, and Google is literally rendering the script tag with the JavaScript inside, the recipient of that email, when they open their inbox, may very well suffer some kind of an attack. Again, it just says attack on the screen, but it represents being tricked into running code that someone else wrote. And in this case, someone else sent you. Ideally, what we would want to have happen instead is not have Google show us the attack message here, but rather I would like my inbox to show me the code I was sent, but not execute it. That is, just like I wanted to know that there are 6,420,000,000 cats among the search results, so would I want Gmail to just show me what it is the adversary typed in without actually interpreting it or executing it as HTML with some JavaScript inside. So that could be a stored attack and would be a stored attack if, thankfully, Google weren't actually protecting us against this, which they are. So how do you go about preventing an attack like this in software? Well, the general answer is character escapes. That is, taking any characters in users' input that might potentially be misinterpreted at best, or at worst might be dangerous to the users. Now, what characters might be worrisome? Well, in something like HTML, anything with an angled bracket, a less than sign, would probably potentially be mistaken for the beginning of an HTML tag. So I dare say that a less than sign is a dangerous character. Similarly, might a greater than sign represent the end of a tag, so that too might be something to give us concern. And there's probably a few other characters as well. So what should servers be doing? What should software be doing to avoid this kind of cross-site scripting attacks, whether reflected or stored? Well, ideally, something like this would not just be blindly outputted by Google or by Gmail, but rather it would be escaped in this very weird looking way. But let me highlight just a subset of these characters. Highlighted in yellow now are only the character escapes to which I'm referring. It turns out that this language, HTML, has standardized some special sequences of characters that represent the less than sign, that represent the greater than sign. They're a little more verbose to type. You have to type out like 4 characters in this particular case. But browsers are designed to know that when they see ampersand, LT, semicolon, they should not show on the screen ampersand LT semicolon. They should show a less than sign. And similarly, when browsers see ampersand GT semicolon, they should display not literally that, but a greater than sign. So this is to say, if Google were smart, they would take any user input you and I give them, but they would make sure to escape any potentially dangerous characters with these kinds of escape sequences, so to speak. And Google's got to look it up in a book or on a website or in the specification to know what escape they should use, but these are very well documented and standardized. And indeed, we have one here for the open script tag, and then another here and here for the closed script tag. But notice we don't have to escape all of the punctuation like the slash or the English letters in the tag name or the like. We're only escaping a certain list of these characters. Well, what is that list? Here are the 5 that minimally we should generally be escaping depending on the context. The less than sign should be ampersand LT semicolon. The greater than sign, the ampersand sign, for the very reason that we're now potentially creating a new problem. If we're using ampersand all over the place, what if the user's input has an ampersand? We don't want to confuse the ampersand in the user's input for a character escape. So there actually needs to be a more verbose way, ampersand AMP semicolon, to represent literally an ampersand. Then there's one for a double quote, ampersand QUOT semicolon, and a single quote or apostrophe, ampersand APOS semicolon. And there's more as well, but generally these are the 5 that could otherwise get you in trouble. So all of the examples we've seen thus far where Google is somehow reflecting back or storing potential attack code will not happen if Google is just smart, whereby they're escaping that input from a user before sending it back out as output to google.com search results or to Gmail inboxes. So how else might we actually prevent attacks like these? Well, we can also put in place other measures as well. And recall from past classes, we discussed this notion of HTTP headers. And an HTTP header is a line of text that's stored in those virtual envelopes that get sent from browsers to servers and from servers to browsers. Inside of the envelope, typically, is the actual request for a web page or the actual contents of, the response for a web page. But also in those envelopes are additional information, namely these HTTP headers, which are key value pairs that provide additional instructions, if you will, to the browser or server. So for instance, suppose that we want to ensure that this kind of reflected or stored attack isn't possible, whereby we're accidentally embedding script tags in our own website's HTML. Well, suppose that the website in question now isn't google.com specifically, but more generally example.com. And suppose that example.com's web server is configured to output always in those virtual envelopes an HTTP header that is content-security-policy : so that string of text is the key, and the value of that key is script-source, then the URL that we want to allow scripts from only. So what does this mean? Albeit fairly cryptic, if you configure a web server with this HTTP header, this will ensure that you can only load JavaScript code from actual files, typically ending in .js, that are sent separately from the server to the browser. This line of an HTTP header prevents inline script, so to speak, whereby it allows the browser to execute any old script tag in the web page. This prevents that default behavior. So as such, even if Google, even if example.com messes up and forgets to use character escapes when rendering user input that came from a URL or came from an email or any other source, this header should at least tell the browser, at least newer browsers, even if you accidentally see a script tag with some JavaScript inside of it in my web page, don't execute it. Only allow me to execute JavaScript code that came from a separate file. The only type of JavaScript that will now be allowed is if I have a tag that looks like this in my HTML, which is an alternative version of the script tag. But instead of embedding any code inside of the open tag and the close tag itself, it refers to the source of, abbreviated src, some file, typically, again, ending in .js. So if this ... were the URL of a file that contains JavaScript code, that would be allowed, because the presumption there is that if someone went through the trouble of creating that file on our own server, example.com, presumably that code is safe. But what this line in our header does is it ensures that we can only execute JavaScript code if it comes from example.com in a separate file using an HTML tag like this. It will prohibit that HTTP header any script tags that are inlined in the body of our actual web pages. What else can we do? Well, it turns out, and we haven't talked about it in this class, there's other languages that you can use in the context of web pages, not only HTML, not only JavaScript, but also a language called CSS, or Cascading Style Sheets, which is generally used to style your page. If familiar, or if you take a course on web development, know that there's similarly a mechanism whereby you can specify that only CSS from a specific server like example.com should be allowed either, not inline style tags with which you might be familiar as well. So here, instead of script source, we see style source, which is just another way using this HTTP header mechanism to just ensure that the browser, at least if it's new enough, will not blindly execute script tags in the first case or style tags in the second case when these kinds of headers are present. It's an additional layer of defense against these kinds of reflected or stored attacks. Indeed, that particular HTTP header would only allow us to include CSS in our web page if it uses a tag like this, namely a link tag with an href value, the ... of which, in this case, would be the URL of a .css file on the particular server, example.com, the relationship of which is to the page that of this thing called a style sheet. Questions then on this use of HTTP headers to prevent these kinds of stored or reflected attacks, or anything else thus far?
What do the \T and \A escape sequence do?
\P and O in the HTML. So recall that a lot of our tags have open tags and close tags. And the slash, it's actually a forward slash, not a backslash. The forward slash here just finishes the thought for the browser. So this starts the tag, this ends the tag, and you use the same word, script in this case, or A or P as you described. That is what closes or ends the tag in question, so that you know where the tag ends or where the paragraph ends. Other questions?
Pertaining the React framework, as far as I understand, on the JSX format, you use interchangeably both JavaScript and HTML. How that isn't a security risk for this kind of attacks?
Really good question. Beyond the scope of this class for those who don't have a programming background, however, yes, React and other frameworks use a technique called JSX, which combines JavaScript with HTML with CSS that are rendered by the browser. In that case, though, Matteo, the browser is running JavaScript code that comes from the React library that is reading as input that JSX code and converting it to the resulting code that should be executed within the browser. So long as all of that code comes from .js files or .css files or the like, all is well. But if you just inline it and you're outputting headers like this, it won't execute at all. So the same rules apply. You would have to use an external file. So when it comes to code injection, there are other types of attacks, particularly in the context of what's called SQL, or structured query language, which is a language that's typically used with databases. So again, on a server. So let's consider how you might also trick software into executing SQL code, that is code written in this particular language, when it comes to databases specifically. Well, here, for instance, is some representative code in this language called SQL, whereby you have a line like select star from users, where username equals quote unquote, and then username in curly braces. Now consider this to be pseudocode of sorts, because I'm mixing some SQL syntax with some Python syntax in this case, because it turns out that when you're using this language SQL or SQL, you typically use it in combination with some other language, be it Python or PHP or Java or something else. And you use that other language typically to construct queries dynamically based on values that humans have typed in. So for instance, if you're logging into a website and you type in your username and hit enter, very often if that website is implemented in Python or PHP or Java, it might use one of those languages to construct a SQL query that is then actually sent to the database to look up that specific user who's trying to log in. So what I have here then is mostly SQL syntax, except for, in these curly braces, some Python specific syntax. And what this curly brace with username inside of it represents is, hey server, plug in whatever the human typed in as their username into that part of the string. So the curly braces and the word username should be replaced with literally something like Malan if that is the user who's trying to log in. And that will then the resulting code will be sent to the database to select everything we know from the user's table, so to speak, in that database about that particular username. So what could potentially go wrong here? Well, it all has to do with, again, trusting input from the user. And that should now be emerging as a theme. You should generally always mistrust input that comes from users. You should do something with it, but you should sanitize it or scrub it in such a way that any potentially dangerous characters are somehow escaped. And that's exactly what the solution was to those cross-site scripting attacks, whereby so long as we escaped the user's input and changed the less than sign and the greater than sign and maybe some other symbols as well to the equivalent character escapes, all was well. So here, too, is an example now in the context of databases where a bit of paranoia will go a long way to keeping your software secure. Why? Well, suppose that my username is indeed Malan, but suppose that's not what I type into the website when trying to log in, for instance. So instead of typing just my username, suppose I am suspicious, as the adversary, that this website is probably using a database, and that database is probably using this language SQL. So what could I do to kind of mess with the owners of this website and try to trick their database into executing my code and not just their own? How do I inject code of my own? Well, instead of Malan, let me a little cryptically type this in to the website where I'm prompted for my username. Now, this does look cryptic, and odds are an adversary is not going to know exactly what to type the very first time they try to hack into a server. Rather, it's through trial and error very often that an adversary might eventually realize, this is what I could probably type into that website to inject some code of my own. So to be clear, what have I typed? I've still typed my username, Malan, but then I've typed a single quote and then a semicolon, and then delete from users, and then another semicolon, and then a dash dash. Now, if you don't know SQL and you are not expected to know SQL for this course, this looks weird, probably, but each of these symbols, each of these punctuation symbols in particular, means something specific and serves a particular purpose. Now, what might that be? Well, let me go back to the original query, and now let me assume that in yellow here, the curly braces with username is where my username is supposed to go. And my username is supposed to be Malan, but what if I type in that long sequence of cryptic text? Here's what's going to happen on the server. Because it's using a language like Python or PHP or Java, this yellow value is going to be interpolated. That is, replaced with whatever the human typed in. So let's do that. Let me paste in what I, the adversary, typed in. And notice I've kept yellow the user's input. So everything in white is still the part of the SQL query that the designers of the database came up with in advance. But everything in yellow is what came from like a form on the web, an adversary in my case. And this looks a little cryptic still, but even if you've never seen SQL before, you might have an intuition for what could go wrong. Because I, the adversary, typed not only Malan, but a single quote here, notice that, oh my goodness, that perfectly lines up with the single quote that the database designer used in their query. And so even though this white quote is meant to be closed by this white quote way over here, notice that grammatically in this language, not to mention in English and other human languages, this single quote here, or apostrophe, because it comes first, will be presumed to close this single quote, or this apostrophe here. The semicolon, it turns out, in this language SQL, ends a thought. It's like a period in English. And so anything after a semicolon is like a new command altogether. So notice that delete from users, semicolon, is like a second command that came entirely from me, the adversary. And then dash dash, it turns out, and this is very clever, dash dash in a lot of versions of SQL represents a comment. And a comment in a programming language means ignore everything after this. Because a problem right now is that that single quote, that apostrophe, was meant to surround the user's username. But because I, the adversary, already gave you a single quote to use accidentally as closing this thought, well, we don't need this single quote at the very end anymore. So this is why the adversary, or me in this story, is doing dash dash. That's just going to tell the server, OK, ignore everything after that, including the single quote that we do not need grammatically. So let me reformat this a bit. I'm going to go ahead and add some new lines, some white space, just to make it a little more readable. What you see on the screen here right now is equivalent to this. Notice that I've moved the delete command to its own line, just for readability's sake. I've gotten rid of the final apostrophe, the single quote, because it was after a comment, which means by design it's meant to be ignored. So what I have done as the adversary, because I presumed or inferred or figured out that this website is using single quotes and they're just blindly interpolating, that is, replacing those curly braces and username with literally anything I type in, I can trick the server into finishing this first command by saying select star from users where username equals quote unquote Malan, semicolon. And worse, I can trick this particular database into executing a second SQL command, which even if, again, you've never seen SQL, deleting is probably a bad thing. It's probably a destructive thing that you don't want some random adversary on the internet being able to do on your server. So what's the goal of these lines here? Well, the original intent of the first query, presumably I claimed, was just to search for the user in the database so that they could log in. So when I type in Malan and hit enter, I am somehow able to log in, probably after typing also a password, maybe a two-factor code or the like. But select star from users where username equals Malan, fine. That's probably going to retrieve the information that it was supposed to retrieve. The dangerous part here is that I trick this server into executing a second command, and this one looks destructive. Delete from users, semicolon, means delete all of the users from the system. So it doesn't help the adversary, in this case, get into the system or do anything with the Malan account other than delete it and literally every other account in the system. So this is bad. This is representative of a SQL injection, whereby I, the adversary, wrote code that you, the designer of this database, accidentally, naively treated as part of your own commands. So how else could things go wrong? Well, not only could you do something destructive like deleting data from the database, but suppose that the user is prompted at the same time for a username and a password now in this story. And suppose, therefore, that the query in the software is this. Select star from users where username equals, quote unquote, username in curly braces, but one more phrase, and password equals, quote unquote, password, based on whatever the human typed in as their password. So again, to be clear, in this story, the user is prompted for a username and a password, and the SQL command that's going to use those two values looks like this. But here, too, we're setting the stage for an injection attack. Why? Because based on these placeholders with the curly braces around username and password, it looks like we're just going to blindly plug into this command exactly what it is the human had typed for their username and password, respectively. So what could a more sophisticated adversary now do? Well, maybe instead of typing in Malan and then whatever Malan's actual password is, suppose that they just want to get into someone's account, maybe Malan's, maybe someone else's altogether. What if the adversary doesn't just type Malan, not to mention Malan's password, but what if they type in this specifically for Malan's password? Now this is weird, and I'll tell you now, this is not in fact my password, but what has the adversary typed in? A single quote, the word or, then another single quote with a 1 and a single quote equals a single quote and a 1. So this looks very, very weird, but let's see what happens. And again, most adversaries wouldn't figure this out the first time they try. Odds are they'd be trying a whole bunch of techniques and heuristics to figure out what might actually work for them. So we're fast forwarding to the end of the story where the adversary has figured out that this weird sequence of characters can hack into this server by tricking it into executing code that wasn't intended. So here again in yellow is exactly what the adversary has typed in. Malan, which may very well be a legitimate username, but then for the password in yellow, single quote, or single quote 1, single quote equals single quote 1. And based on our previous example, you can perhaps see what's starting to go on here. We've finished the Malan thought naturally, like we didn't type anything malicious for the username this time, but we did type something seemingly malicious for the password. And the first single quote in yellow quickly finishes the password thought, quote unquote, nothing in between. But then we're saying or, quote unquote, 1 equals quote 1. Why? Well, the adversary in this case kind of figured out or knew or guessed that the SQL command ends with a single quote itself. So the whole point here is, even though this too probably looks very cryptic, is that grammatically what the adversary has typed in not only perfectly aligns with the username field, because it's just Malan, nothing special there, but very cleverly the adversary has finished the thought of this single quote and also finished the thought of this single quote. So we've made everything balanced, just like you would not only in SQL, but in a language like English. So let me go ahead and clean this up a little bit too to make clear why this is dangerous. This command now, once formed by the server based on that adversary's input, is really the same as this. And I'm just going to add, again, a new line and some white space just to help us wrap our minds around what's going on. So I've just moved the or line to the bottom. And just like in math class years ago, let me go ahead and put parentheses around things here that makes clear what the precedence is of things like and or. It turns out that and, like multiplication, binds at a higher precedence. It's more important. You're supposed to do it first. So I'm going to add parentheses now to this first expression. They're not strictly necessary, they're implied. I'm just making them explicit now to show you, just like in math class, the order of operations. Now, what does this mean? This means that the database is going to say select star from users, so select everything from the users table where the username is Malan and the password is quote unquote. Now, that is probably not my password. My password is definitely not nothing. It's not empty, but that doesn't matter now. Why? Because even if this first clause, where username equals Malan and password equals quote unquote, even if that doesn't find anyone in the database with the username of Malan and a password of quote unquote, it doesn't matter because we've tricked the database command into including an or, which is so stupid that it's always true. Or 1 equals 1. Well, 1 always equals 1, which means that now, logically, this query is going to return everything we know about users from the database. And why is this problematic? Well, when you're logging users into a database, logging users into a website or application, you're typically searching for them in the database. And typically, if you get back one or more users, you're going to assume that the very first user is the one that you want. And maybe in this case it's Malan, but it's also very common in servers for the very first user that was created to be you, the person that designed the site. And you probably have administrative privileges, that is, access over everything in the system. And so if a query like this is returning all of the users, including you as the very first one, if there's additional code in the system that we won't put on the screen here or bother hypothesizing about, it means that you could be now letting the adversary log in maybe as Malan, but worse, maybe as you. All because you trusted user input. But you should never trust that your users, if called Malan, are going to type in just Malan. You should always assume that there's someone out there, very annoyingly, very maliciously, that's going to try using some single quotes, some semicolons, or in HTML we saw a less than sign, a greater than sign. You should always expect that someone on the internet will have enough time and interest in hacking your website or application that this might indeed happen to you and your software. So what's the solution then? How do you avoid a query that's equivalent ultimately to this? Because if there's no Malan with no password, it's still the same as asking for where 1 equals 1, which is anything. And to be clear, I didn't have to use 1. I could have used 2 or 3 or 4. I could have used cat or dog or anything else, so long as the thing on the left equals the thing on the right, and I type that into the application, the same thing would certainly equal itself, is the point here. And 1 is just the simplest thing we could think of. So what is the solution here to SQL injection attacks specifically? Well, it's very similar in spirit to the notion of character escapes. But in the world of SQL, there tend to be standard ways of escaping dangerous characters. You don't have to do it yourself. And much like security in general, with encryption specifically, you probably should not be writing code yourself to solve problems like these that hundreds, thousands, millions of people before you have already had to deal with and have probably solved correctly. Do not reinvent wheels when you don't need to in the context of security. So this is to say, in the world of databases, most databases support what are called prepared statements, which is a fancy way of saying that you provide the code for your SQL query, you provide placeholders for wherever you want user input, but let the database itself replace or interpolate those placeholders with the user's actual input, and let the database handle escaping anything dangerous. And we've seen that things are dangerous, like apostrophes thus far. So for instance, instead of writing a single apostrophe, and this is weird admittedly, in the world of SQL, the way you typically escape an apostrophe is not like HTML. You don't do ampersand, APOS semicolon. You don't, like in some languages, put a backslash in front of it typically. The way, weirdly, you escape a single quote or an apostrophe in SQL is very often by putting 2 of them in a row. So why? We'll defer that to another day, but this is just the convention. Now, this means that you could write code that changes any single quote to 2 single quotes, but again, don't bother doing that. Use functionality that comes with the database or whatever library you're using. So for instance, if we go back to that very first query that was vulnerable to being injected with something like delete from users, what if we now do this? Let's change our Python-based placeholder using curly braces in yellow here. And let's change that and get rid of the quotes and just put a question mark. This is one of the common conventions in prepared statements where you put a question mark, not because you don't know what to put there, but because you want the database to replace that question mark with a user's own input. Then what happens? Well, if the user types in that dangerous command with the delete inside of it, notice what happens. Here's the single quote. Here's the closed single quote, and the database has given that to you automatically. The prepared statement adds those single quotes for you. Notice that even though I, the adversary, only typed in Malan single quote, semicolon, the prepared statement has gone ahead and escaped a single quote or apostrophe with two of them instead. And nothing else here thereafter is actually too worrisome. That alone is sufficient to solve the problem. Now, this looks a little weird, right? Because it kind of looks like logically, well, you still have this quote and this quote which line up, and you still have this quote and this quote which line up. So it looks like we haven't really fundamentally solved the problem, but we have. It turns out in SQL databases, anytime they see two single quotes back to back, they don't try to pair them with something to the left or something to the right. They just treat it as one special escape sequence, so to speak. So that would then fix this query. And if we go back to the second query, which had two placeholders, username and password using this Python syntax, let me go ahead and change that to prepared statement syntax using, in this case, question marks without quotes, and trust that the database itself will add any necessary quotes and escape any potentially dangerous characters. Now, what did the adversary type in that second scenario? Well, it was just innocuously Malan. And so that comes back from the prepared statement as being prepared with quote unquote on the outside. No problem there. But this other input from the user, from the adversary's password, which was very cryptic with lots of single quotes, notice that every single quote in the adversary's so-called password has been escaped. So that the single quote here becomes 2. 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 And the prepared statement automatically adds a final single quote at the very end. But I've kept highlighted in yellow everything that represents the user's input now that it's been properly escaped, because again, even though you might try mentally to pair this quote with this one with this one, this one with this one, and so forth, that's not what the database does. Whenever it sees, in this case, two apostrophes back to back, they are treated as special escape sequences. And so the only quotes that ultimately are treated as lining up are the two around the username and the two around the entire password here. So the characters are still in there, but they've been escaped, sanitized, or scrubbed, so to speak, in such a way that now the database is smart enough not to mistake those for quotes that should be matched with ones that we might have otherwise written previously. Now, there is another class of attacks that similarly involve injection into your software, particularly command injection. Those of you familiar with a command line interface in the context of a terminal window or the like might be familiar with how on a system you type commands as opposed to always using your mouse to point and click on menus and buttons. The problem with command injection is that it's all too easy in a lot of today's programming languages to write code that invokes commands on systems, whether it's to copy files, delete files, move files, execute other commands altogether. And that's because a lot of programming languages come with functions. That is a feature called system, which is literally a feature of some programming languages that allow you in your program to execute a command on the underlying system, a command on the underlying operating system. And that might be useful for you because in addition to writing your own code in some higher level language, you can occasionally run a command on the system itself. But the problem is that if you, the programmer, somehow take user input and you just blindly pass that user's input to the command line, so to speak, to the terminal window, to the underlying operating system, that is yet another context in which potentially dangerous characters like semicolons or the like could accidentally finish your thought, but then start a completely new one from the adversary so that they too on your system can not only delete things like data from your database, but even files from your file system. They could perhaps send email or spam or do anything in a command line environment that you yourself could do on the same. In other programming languages, the same idea exists in the context of another function called eval, which evaluates whatever you pass to it. So there too, if you're in the habit of using system or eval, taking user input and passing that user input as part of the input to system or eval without having sanitized it or scrubbed it or more generally escaped potentially dangerous characters, you're putting your entire system at risk and any and all software that's installed on or running on the same. So what's the solution here? In any of those programming languages to which I'm alluding that have functions like system or eval, they almost always come with another function or built into these functions, a way of escaping the user's input. So I would always take care to read the documentation if you yourself are or want to become a programmer, that whenever you take user input, you always figure out and think to yourself, wait a minute, how can I escape this properly so that I can't be tricked into executing some command, some SQL, or some HTML and JavaScript within my own software? All right, that's been a lot. Let's go ahead here and take a 5-minute break. And when we resume, we'll look at a whole other category of potential attacks on software. All right, we're back. Let's go ahead and return to this world of HTML and the web, if only because so much of today's software is actually web-based. And indeed, even on your Macs or PCs or phones, what looks like a native application, so to speak, might actually still be implemented in HTML with that other language, JavaScript and CSS. Well, it turns out in the context of a browser, there's very often a feature called developer tools. And indeed, if you've done any web development of your own, you might have played with this feature. And these developer tools, which might be called something slightly different across different browsers, allow you to poke around the HTML, the CSS, and the JavaScript that compose some web page, either that you yourself have made or that someone else has made and you have downloaded or accessed via your own browser. Let's consider now, though, what you can do if you have access to these developer tools. So for instance, here is some HTML using a tag called input, which would create a checkbox on a website. We haven't seen this one yet, but it's similar in spirit to the paragraph tag and the anchor tag, in which case it is interpreted as the browser as meaning, hey browser, here comes a checkbox. The only thing different that's worth noting here is that some HTML tags don't actually need a close tag. Because whereas a paragraph starts somewhere and then ends somewhere else after some number of words, a checkbox is either there or it isn't there. So there's really no conceptual notion of it starting and stopping. So some HTML tags don't even need end tags or close tags. This, then, is one of them. This, then, is an input tag that gives us a type of input, namely a checkbox. And another curiosity about this is that some HTML attributes don't need values. We saw the href attribute for the anchor tag earlier, and that, of course, had a value. In quotes was the URL that you want to link to. Here we see that same paradigm, type equals quote-unquote checkbox, to give us specifically a checkbox type of input. But you'll also notice here another attribute, specifically for this input tag, that's literally called disabled. And strictly speaking, you don't need to give it a value because it's either there or it isn't. And if it is there, that just means that this checkbox is exactly that, disabled, which means you can see it, but it's not checked and you can't actually check it. It's disabled and lightly grayed out typically on a browser. So why might this be? Well, maybe there's some feature in the browser that you don't want to give some users access to. Maybe based on who has logged in, they should or should not have access to some feature. The problem, though, with HTML and CSS and JavaScript, or really anything that is web-based or using those languages, is that you're sending this HTML to the user's own device, to their browser on their phone or laptop or desktop, which means they can not only see this HTML code, but theoretically they can edit it. They can't edit it on the server because that's your own copy, assuming they can't hack into the server, but they can edit their own copy thereof. Now, usually that's not such a big deal because what's the worst that can happen? They can hack themselves by changing HTML on their own computer or phone. But it is problematic if you are using HTML or even JavaScript to try to prevent certain user interactions with your server. So for instance, if you simply don't want a user to be able to check this box so that when they submit a form, they're not agreeing to something or they're adding something to their shopping cart by using this checkbox, Well, you might rely, therefore, on this HTML attribute disable. Just prevent them on the client in the browser from checking this box. But it turns out with developer tools, which are accessible usually via a menu at the top of the screen, or by right-clicking or control-clicking on a web page and then selecting an option, a user with access to HTML can change any and all of that HTML on their own computer, which means they could just remove this disabled attribute in their own copy of your HTML on their computer and effectively enable that checkbox by getting rid of it. Now, what does this mean? Well, there's no problem yet, but if they do now check that checkbox, and you didn't want them to be able to, and they submit the checkbox to the server, as by clicking a submit button in a web form, you on the server, if you're not paranoid enough, might just trust that if I see a checked box being submitted via form, they must have been allowed to do it, so I will trust them. But no. Here, too, is an example of where you should never trust users' input, because if you're trying to disable them from doing something on the client, they don't have to respect that. They can override the HTML in their own browser, remove any such defenses, and then send the checkbox to you anyway. The takeaway here, then, is that you really should never rely on client-side validation alone. And this disabled attribute is just one minor incarnation of that, where you're relying on the client to ensure that the button is that the checkbox is disabled and its value can't be sent to the server. But client-side validation is really on the honor system only, because if someone knows how to use these developer tools and removes the disabled attribute, or if they know how to use developer tools and maybe disable JavaScript altogether for your website on their computer, any form of client-side validation in HTML or JavaScript that you wrote on the server, but that your server sent to their browser and that's therefore executed by their browser, is vulnerable to simply being turned off. So the catch is that even though client-side validation tends to be nice in terms of user experience, the button is obviously disabled, so I should not be able to click on it. Or my email address is improperly formatted, so I should not be allowed to submit the form. Any forms of client-side validation tend to give the user immediate and often very useful visual feedback. But if it's not accompanied, this client-side validation, by server-side validation, your server software is still vulnerable to attack in some way. So what other form might this take? Well, here's another example of an HTML input. This time it's of type text, which means it's a text box on the field. Suppose that you really want them to provide that value. Maybe this text box represents the user's name or their email address or their password or something like that. And so if you know a little bit of HTML, you know that there's not only a disabled attribute available to you, but also a required attribute. And it doesn't have an equal sign or a quote mark. You don't need that. It suffices just to say this input is required. But the catch here is, too, if a user doesn't want to give you a name, doesn't want to give you an email address, doesn't want to give you a password or some other value, well, they can use these so-called developer tools, click a button on their browser, remove the required attribute, and voila, now they do not need to submit that value. Now, that in and of itself is not a problem, because again, they're only hacking themselves. But if they're then allowed to submit this form to your server, and your server just trusts or assumes that every user will send you a username, an email address, a password, or the like, that's where things can break. If you're trusting client-side validation alone to ensure that the user's input is as expected. So if they're allowed to get rid of something as simple as this required attribute, effectively making the input like this, you might be missing some value. And so you must, therefore, use server-side validation again. And we won't get into the particulars of how you do this, because it will completely depend on the type of server software you're using, the programming language that you're using. And so it's really the principle today that's important, that client-side validation, whereby the browser or the user's own copy of your software tries to preempt mistakes and require or disable certain inputs, that's fine. That tends to give good, immediate, useful user feedback. But it must still be always accompanied by server-side validation, so that you have the final say over what the user input looks like and if and how it's actually stored into your system. Again, the particulars of how you do one or the other is a topic for an actual programming class or a class on web development specifically. But for now, it's this principle. Just because you have client-side validation doesn't mean you shouldn't also have server-side validation. And in fact, if you've got to choose one or the other, always choose server-side validation. Client-side validation is really just icing on the cake. It adds to the experience, but it's not the prerequisite one. Questions then on these so-called developer tools or these kinds of threats when it comes to validating the user's input?
Yeah, so my question is more related to SQL and command injections for a second. Isn't it really easy to just not run the user's commands with admin or root privileges to delete certain records from a database or something?
Yes, another defense would be to make sure that whatever username you're using to execute these SQL commands does not have the ability to delete anything at all. However, some threats only need select access. So the second example I showed you, whereby we trick the database into just selecting star from users where 1 equals 1, that was an example of one where permission-wise it probably would work, and it might allow the adversary still to log in. But your suggestion is a good one as an additional defense, not an alternative. Let's consider another class of attack to which your code might be vulnerable if it's on a server using the same language, HTML, namely cross-site request forgeries, or CSRFs. So this one's more of a mouthful, but it too relates to a mistake you might otherwise make when writing software on a server if you're not already familiar with this kind of threat. So first, HTTP, recall, is this protocol, this convention via which web browsers and servers communicate. Well, it turns out there's different ways that browsers can get information to a server, and one of those ways is literally called GET by convention. In other words, inside of that virtual envelope is typically literally this word, GET, followed by the file name that the browser wants to get from a server. But more importantly for our purposes is that whenever using this GET method to send information to a server, all of the information that you want to get is embedded in the URL itself. So what does that mean? Well, consider, for instance, this sample link in HTML. Here's my anchor tag beginning. Here's my anchor tag ending. Notice here is the text buy now. Well, let's suppose that you're in the US here, and on Amazon.com in the US, there's actually this feature where you can buy now. That is to say, when you visit the page of a product on Amazon's website in the US, if not beyond, you can skip the steps of having to add an item to your shopping cart and check out and choose your payment method, and then some number of clicks later actually buy the product. Rather, if you configure your account in advance, you can go to any product's page, literally click a link or a button that says buy now, and that's it. In a single click, for better or for worse, that product will be shipped to your home. So how might Amazon be implementing this? Well, they might indeed be using a link like this, the href value of which is a URL, like https://www.amazon.com/dp/b07xlq2fsk. In other words, that seems to be enough information in the URL alone via which to buy the product whose unique identifier is apparently that string of text at the end. Now that's all fine and good, and that actually seems very user-friendly, because with a single click on buy now, I can indeed buy that product. But the danger here is that if this link is not just on Amazon.com, but is in some adversary's website, or maybe in an email that is sent to you, if it's that easy to buy something now, you could trick someone potentially into buying things that they didn't actually intend in this case, or doing anything else on a web server into which they're already logged in if GET is the method being used to get something from that server. Well, why is this exactly, that this URL is problematic? Well, consider, for instance, the following HTML instead. Suppose that you visit an adversary site who just likes to create havoc in the world, and that adversary site doesn't even have an anchor tag or a link that they want you to trick, so it's not even as deliberate as a phishing attack that they want you to click some link. Suppose they're using something like an image tag, which it turns out in HTML, IMG for short, is how you embed an image on a web page. And how do you specify what image? You specify the source thereof, src for short, the value of which can be the URL of or the name of the image you want to display. But strictly speaking, that URL doesn't have to actually lead to an image. It could actually lead to an Amazon product page. But the way images work on web pages, recall, is that typically when you visit a web page, the images automatically load. You don't have to click or do anything typically for the images to appear on a web page. Maybe in emails, and that's an anti-phishing mechanism, but in web pages, you typically don't have to click on anything to see the images. That is to say, the value of these source attributes are just automatically downloaded and displayed to the user. Now, this, in fairness, is not an image, but the browser doesn't necessarily know that from the get-go. And so if this HTML is in some adversary's website that you've somehow been tricked into visiting, and you don't even click a link, you just visit that web page, that means this image tag is going to try to download this source, and even though it's not going to get an image, it is going to buy that product for you. Why? Because if you're logged into your Amazon account, even though this is in another tab, it's as though your browser requested that URL via that GET method, because all of the relevant information for buying that product is in the URL alone. So it turns out that using GET is actually not a good thing when it comes to changing state on the server. To get technical, the GET method is meant to be safe. Safe whereby it does not change any state or values on the server. So it would actually be incorrect, or definitely bad practice by Amazon, if they were implementing their buy now button simply with a simple URL and a simple GET request. It should not be that easy to buy things on the internet, let alone change state on the server in other ways. So there are thankfully other methods, but even these are potentially vulnerable to this kind of attack. There's a post method, which is typically used by browsers when you want to post your credit card information or your password to a server. You don't want your credit card, you don't want your password typically ending up in the URL of your browser for privacy's sake. So rather, post will kind of hide it more deeply in that virtual envelope to which we keep alluding. Post might also be used if you want to upload images or video files to a server, because those don't really fit in URLs, it would seem. And so post is an alternative that is meant to change state on the server. For instance, buy products for you. But even this can perhaps be abused. Well, let's take a look how. Here is now some HTML, and it's more HTML than we've seen thus far, but we'll wrap our minds around each piece of it, that represents an alternative implementation of the Buy Now button on Amazon that's no longer a simple anchor tag with everything that's needed in the URL. This is more of a traditional web form. And it's fine if the form is super short and only has a single button. It doesn't need text fields or anything like that, but there's a lot going on here. So let's see. So here's the form tag, the opening tag. Here's the close tag. So everything in between must be implementing this form. The action of this form, I claim, is going to be to submit the information to this Amazon.com URL here. But the method that we're going to use is explicitly post. So it turns out in an HTML form, if you don't specify a method, it will use get by default. So explicitly, I'm at least using post because I don't want everything to be in the URL alone. Well, I've got two inputs here, one of which is of type hidden. Well, what's going on here? Well, it turns out that in HTML forms, you can create like key value pairs to send input to a server. So if you recall previously, I used the DP part of the URL as separating Amazon.com from the product ID. And here, and now I'm making this up for the sake of discussion, I'm supposing that Amazon supports a web form name called DP whose type is hidden, because it can be, the user doesn't need to see this, but the value is that same product ID. So this is an alternative to embedding that product ID in the URL. Instead, I'm saying there's an HTTP parameter called DP, the value of which will be this. But it's hidden, so the user doesn't even see it, which is fine, because the whole point is a nice, simple buy now button. How do we get that button? We use a button tag in HTML, the type of which is to submit, because its purpose in life is to submit this form. And the text that the user sees for this button is indeed buy now. So what am I doing? This will make more sense, admittedly, to those of you who've already studied a bit of web development, who have written HTML yourself. But I'm essentially making it harder for an adversary to automate an attack on a user's Amazon account. Why? Because I am not just using a link anymore that the user might click, or a URL that could be subtly hidden in an image tag. Now I have an actual web form. And at least based on my naive understanding of HTML at the moment in this story, this would seem to require that a human click an actual button. Like, I cannot use this as the source of an image. It's not a URL. It's all of this complexity. So if you're familiar with get versus post, you might be inclined to think that, OK, post surely solves the problem by using this web form, because you make sure in this way that someone clicks the button before they can buy anything. Now, why is that indeed naive? Well, it turns out using not just HTML, but this language we've seen a little bit of today, namely JavaScript, can be used to automate the process of submitting a form. So if an adversary now has this HTML in their website, they don't have to wait and hope that someone like you or me is going to come along and click the button explicitly, because that would be a little weird to click a button thinking you're going to buy something now, but it's not on the actual Amazon.com. That alone doesn't matter. If the adversary can just trick you into visiting their website, and their website contains this HTML and this additional JavaScript, they can immediately submit this form for you to Amazon without you clicking a thing. Why? Well, inside of this script tag that I've added down below, I've simply said document.forms bracket 0. So this means get me the first form on the page, and I'm presuming there's only one in this story, and then submit it. So this is to say, in JavaScript, not only can you do things like trigger alerts on the screen, those dialog windows, you can similarly, through code, automatically submit forms. So it doesn't matter that you're using post. It doesn't matter that you have an actual button that must be clicked. It doesn't have to be a human that clicks that button. It can be their browser automatically executing this JavaScript code in the adversary's website that just submits that form for them. So this is the essence now of a cross-site request forgery. If HTML like this exists in the adversary's website, some other website, you can nonetheless trick users into executing operations across websites, on Amazon.com in this case, even though the users themselves are not on Amazon.com. So that's the cross-site aspect of these attacks. And it's a request forgery in the sense that it's sending all of the right information, but it's forged by the adversary. It's not coming from the Amazon.com developers themselves. But it is this simple, because if Amazon does not defend against this attack, there is nothing stopping you or me or any adversary from including code like this on our websites, somehow tricking users into visiting our websites, and boom, having products sent to them automatically, assuming they have an Amazon.com account and they're also already logged into it in another tab, or at least earlier in the day, for instance. All right. Any questions now on this particular attack, these cross-site request forgeries, whether implemented using get with simple URLs or even implemented with post using actual forms?
How can AI model and quantum computing change the way that we look at cybersecurity?
Quantum computing? Let me address that another time, because I dare say that's a bit far from today's goals. But quantum computing is bad if the bad guys have it and you and I don't. I'll put it that way. All right, so how can we defend against this threat even when there's JavaScript code automatically inducing submission of these forms which have enough information in them in order to buy something on our behalf? Well, it turns out that we could include something like a special token. And it turns out a common way to address this problem is by having the server not just output a simple HTML form, but to output an HTML form that additionally has another value, often hidden as well. And by convention, in some worlds, it's called the CSRF token, which is just a fancy way of saying an extra value. But its value is typically meant to be random. And I've chosen something fairly pronounceable here, 1, 2, 3, 4, A, B, C, D. But assume that that value is randomly generated by the server. And it might have a bunch of numbers, a bunch of letters in it. But the point is that it's randomly generated by the server. Now, why is this important? The implication of this mechanism, by having a web server output not only the product ID and also the button inside of a form that they might be using to implement this buy now feature, the point is that the server should also be generating some secret randomly generated piece of information in that server as well, in that HTML as well. And the server should remember that value. as by using its own database or some other mechanism. The point here, though, is that only the server, Amazon.com in this case, knows what that value should be for you, a specific user. And so an adversary, even if they trick you into visiting their website where they have HTML that looks quite like this, the adversary, unless they've hacked Amazon.com, which is not part of this story, they would have no idea what this random value is that Amazon.com is using for your buy now buttons. Because again, if it's just an adversary on the internet, they haven't taken over Amazon.com, they haven't taken over your computer itself. They are just trying to trick you into visiting a web page of their own that has HTML like this. They won't know what value to put there. Now they can try to guess, and maybe they could guess 1, 2, 3, 1, 2, 3, 4, A, B, C, D. But assuming it's more random than that, the odds that that adversary guesses your CSRF token value is just so small and low probability that it's just not going to happen realistically. So now, even if you visit a web page that contains this HTML, even if it has some JavaScript that automatically submits the form, because the adversary doesn't know the value of this CSRF token, Amazon.com can just ignore the request to buy that product now. And they can throw up an error message or say something went wrong or the like. But the point is that only the real Amazon.com should be able to generate and remember this CSRF token value. And so therefore, they can validate server side that it's indeed you who intends to buy something now. The adversary, if they put a blank value there or any other value, it's not going to be validated server side because the server realizes, that's not the value I'm using for David. That's not the value I'm using for you. So this is a very common technique. It does require a bit more complexity on the server. Very often, programming languages like Python will come with libraries, third-party libraries or code that other people have written that allow you to add this functionality to your own software. But you have to know that the threat exists, and you have to look for a solution there too, or implement it yourself if need be. But almost always is a library the answer to this problem. There's another way you can solve this same problem, which doesn't involve outputting any HTML at all. It is also possible to send these kinds of tokens as HTTP headers as well, as might commonly be the case when a website is very heavily using JavaScript and is using JavaScript to talk directly to a server without even any HTML. Well, the same values can be sent via this other mechanism as well. So if you're interested in these kinds of web-centric attacks especially, you might find it interesting to explore the Open Worldwide Application Security Project, which has documentation of, discussion of, recommendations for all of these kinds of web-centric attacks and more. For now, though, let's go ahead and take a short break. And when we come back, we'll look at problems that go beyond the world of the web, specifically the software that you might have running on your own Macs, PCs, or phones. All right, we're back. Let's now consider a class of attacks that is particularly common when it comes to software that's running on your own Mac or your PC or your phone. So not web-based, but local instead. And the first of those is generally called arbitrary code execution. The potential for an adversary to somehow trick your own computer into executing code that you, the adversary, have written and that's not embedded in the actual software that's meant to execute it. This is an example more generally of what might be called remote code execution, whereby the same attack can happen even if the adversary is somewhere else in the world, perhaps connected to you somehow via the internet. And how might these attacks be possible? Very, very common mechanism for waging these kinds of attacks, whereby an adversary tricks your own system into executing code that the adversary wrote, is through something generally known as a buffer overflow. Now, to be fair, this is a topic you would explore in more detail in a class on programming specifically, computer science more generally, but we'll give you a high-level sense of what the threat is as it relates to software that might very well be running on your own computer. So what is a buffer overflow? Well, for this, we need a mental model for what's going on inside of your computer when running a program. And when you double-click a program on your Mac or PC or your phone, and it opens up and loads into the computer's memory, the memory you can think of as this big rectangular region that represents all of the bytes or megabytes or gigabytes that are in your Mac, your PC, or your phone. And the computer, or device more generally, uses different parts of this memory for different purposes. And this is just because humans came up with conventions years ago to lay out the computer's memory in this way, using some of it up here for one purpose, using some of the memory down here for another purpose instead. So for instance, if this big rectangle represents your phone or your computer's memory, let me just propose that at the top of it, so to speak, although memory doesn't have a top, bottom, left, or right, because it totally depends on how you're holding it, but assume conceptually that at the top of your computer's memory is the machine code for the program you're running. So long story short, when you write software, at the end of the day, zeros and ones are involved. And the zeros and ones represent the instructions or commands that that software wants to execute on your computer. When you click an icon or double click an icon and load a program into memory, the actual program's machine code, the zeros and ones, if you will, are stored up here in your computer's memory. Meanwhile, while a program is running, it might need more or less additional memory as it executes instructions therein. So what does this mean? Well, if the program is prompting you for input, or if it needs to load a new level from a game, it might need more and more memory, but eventually it might not need that memory anymore. So the memory requirements of a program tend to go up and down all the time based on what you, the human, are doing with the software and based on what the software is designed to do. So computers typically use this bottom area of the computer's memory for a so-called stack. Very similar in spirit to any physical thing that you might stack one on top of the other, like clothes in a closet or trays in a cafeteria. Stacking means literally from bottom on up. But the weird thing is about a computer's memory is that by convention, when the computer needs memory, it first uses some memory from the very bottom. And then if it needs more, it uses more above that. When it needs more, it uses more above that. So instead of just going top to bottom, it actually deliberately by design goes bottom up for reasons we won't get into in this course, but just take on faith that indeed this stack of memory grows upward. The catch, though, is that sometimes software doesn't necessarily know in advance or predict correctly in advance how much input you, the human, might give it. So for instance, a computer program might decide to take up this much memory at the bottom, but then not realize that, oh, wait a minute, what if the human types in a really long name or a really long essay or just gives me more keystrokes as input than I, the programmer who wrote this software, anticipated. That might mean that even as you allocate what are called frames of memory on this stack, the user's input might not stay confined to that particular frame. If they type in too many characters at their keyboard, what's supposed to go here might end up going down here. So overflowing these frames of memory. So the computer or the programmer makes hopefully an educated guess as to how much input the user might have. But if they're wrong, that input might be too tall and therefore overlap other parts of the computer's memory. Now, there are ways to defend against this. So the scenario we're worried about here is often when programmers don't know how to anticipate this, or when you are using software written by programmers who didn't anticipate or implement the solution properly. So what might go wrong? Well, for instance, when a program first starts running, one of the first things it does, if it's calling another routine or another function, when you click on a button, when you start typing keystrokes, the computer might start using some of this memory, and it might be moving around among these zeros and ones, executing different instructions. If you click this menu option, it'll use this code. If you click on this menu option, it'll use this code. So in other words, the computer logically is kind of moving around among all those zeros and ones and executing them accordingly. So one of the first things your computer does when a program is running is it just jots down at the bottom of the computer's memory, what is the address to which I should return after doing this? So it's kind of like in the real world, if you go off and do something over there, eventually you want to remember to come back over here to pick up where you left off. And that's what we mean by return address. It's a little reminder to yourself that no matter what you go off and do right now, you got to come back and resume where you left off. And what this return address then does is it refers to some specific location in the machine code, some specific pattern of zeros and ones that eventually the software should come back to pick up when the user leaves off. So for instance, if you open the file menu and go to print, and you go through the steps of printing a document, the return address might be to go back to whatever you were doing in that document before you initiated the print command. So the software is constantly jumping around in this sense. Suppose now that the user just clicks some button within the software to search for something. Maybe it's like cats. Well, because this is a new function that's being called, the search function, what the computer might do inside of its memory is this. It might put a little note to self to say, go back to this location in the machine code once the user is done searching, just like the user might be done printing. printing. And then suppose the user types in cats. Well, cats is stored in the computer's memory just above this frame on the stack because, again, I said by convention, whenever the software uses memory, it starts at the bottom, then goes up, then goes up, then goes up. So after now this software is done searching itself for cats, then that frame on the stack is sort of removed because we don't need to know about cats anymore. We're done searching for them. So the last thing in memory is this reminder, go to machine code. And this is how the software knows to go back to a particular location in code, where maybe it's just sitting there waiting for me to click some other menu option instead. But what if an adversary is the one at the keyboard, so to speak, and it's not a good user just typing in short phrases like cats, but maybe it's an adversary who's typing something more. So suppose that an adversary actually pulls up the search feature, and in general, therefore, the software is going to remember to put the return address there. So specifically something like go to this location in the machine code. But suppose that the adversary doesn't type in cats, doesn't type in dogs, but types in, for the sake of discussion, some pattern of zeros and ones that represents actual code. Maybe it's the pattern of zeros and ones that represents delete everything from a server or start sending emails or the like. Or maybe, more cleverly, maybe it means skip whatever menu keeps prompting me to register or activate my software. In other words, the adversary wants to trick the software into running zeros and ones that didn't come with the software. Now, in practice, you can't just type zeros and ones at the keyboard. It would be a different way that the adversary inputs this data. But for the sake of discussion, assume that the adversary is not typing in cats, but is typing in these zeros and ones. And they know enough about binary, zeros and ones, that they know what patterns to choose. Now, suppose that this code, this so-called attack code, is way longer than CATS, and it's many more characters or bytes long. It is possible, by definition of how memory is used, that this attack code might be so big that it takes up not only this space that's been allocated for it, but it overflows other things in memory. You can now think of this frame, this rectangular region on the stack to which I keep referring, is like a buffer, a room for some amount of information. But if the adversary provides so much information, so much attack code, zeros and ones, that it overflows that buffer, it might actually overwrite that note to self with ... something else. And what's clever here, though, is that if the adversary is smart enough, and this is often through lots and lots of trial and error, they don't often just get it the first time. If the adversary is ultimately clever enough, they can actually put not just some random zeros and ones there, but they can put the equivalent of a note to self that says, go to attack code. In other words, instead of typing in cats, they type in two things that are pretty long. One are the zeros and ones that represent some form of attack, like circumvent the registration or the activation for the software so I can use it for free, or do something else that's malicious. And if the second thing they provide in just so happens to be cleverly the address of their own attack code, which they can figure out mathematically, perhaps through trial and error, the adversary can trick the computer into not going back up here and running the machine code that came with the software. The adversary can trick the software into executing code that the adversary themselves injected. Now, what does that mean? If you are running the software under your username, whatever you can do on the software and the system, be it your Mac or PC or phone, so now can the adversary. And maybe they'll now delete all of your files. Maybe they will now all register the software. Maybe they will now start sending spam. Anything at all is possible based on what the adversary has passed in here. So if you've ever heard of a website called stackoverflow.com, which is a popular website for programmers to ask questions and get answers of a community, that specifically is the allusion to exactly this kind of bug or mistake, whereby, if not programmed properly, the stack can overflow. And if the software or programmer does not anticipate or detect it, bad things can happen. You can have arbitrary code executed, or you can have remote code executed if the adversary isn't even at that keyboard, but is somehow sending this code into your software via some network connection. What then might this mean? So if you've ever heard of the term cracking, which typically refers to figuring out someone's password, or in this case, breaking into software, cracking might refer to eliminating the need for a serial number or an activation code or the like, because if you can inject any software, any code that you want into someone's software, you could tell that software to just skip the lines of code, the zeros and ones that represent asking you for that activation code, or they can do something much more malicious. So this is an example in some sense of what we might also call reverse engineering. Reverse engineering refers to the ability for someone to figure out how something was engineered, how it was built. Now, at the end of the day, most of the software that you and I install on our Macs or PCs or phones is pretty much just zeros and ones. So it's very non-obvious to an adversary even what is actually going on. But with certain techniques, with certain trial and error, they can actually figure out what those zeros and ones represent. And depending on the language that was used to generate that software, they might be able to glean even more information than that. Now, there's a good side of reverse engineering, whereby if you and I are in the business of figuring out how malware was implemented so that you and I can contribute solutions to antivirus software and the like, well, malware analysis uses these same kinds of techniques, trying to figure out what's going on underneath the hood of software as by reverse engineering it. So using trial and error, maybe injecting some code of our own to figure out exactly what instructions are embedded among all of those zeros and ones. Now, how might you hedge against these kinds of threats of remote code execution, arbitrary code execution with software of your own? Well, you could start using open source software, for instance. Open source software just means that the code that implements that software, be it in Python or PHP or Java or C# or C++ or any number of other languages, is itself open source. That is, you and I and anyone on the internet typically can read the source code and see exactly what instructions will be executed on your computer or phone. Now, that doesn't necessarily mean that the version of the software that you are running is exactly the same as the open source version. There's still a threat whereby the code might be open source, but maybe you were tricked via some phishing email or some malicious website into installing a fake version of some software that actually has malicious code in it. So malware might still be a problem. But a lot of folks think that open source tends to be a good thing because you can audit. Smart people on the internet can audit the code and make sure that there are no backdoors or malicious instructions that might do things that you wouldn't expect the software to do. Now, again, that's not necessarily the case that the version you're running doesn't still have some form of infection, but this might give you at least a bit more reassurance. Now, the flip side, though, is that if code is open source, even if it's devoid of anything malicious, it might still have bugs, mistakes that human programmers accidentally made, which might very well make open source software or any software vulnerable to attack. I mean, you're literally giving the adversaries the plans to your software. It's like the plans to the Death Star in Star Wars, such that they can probably figure out what the weaknesses are in your software because you're giving them the blueprint therefore. So an alternative to open source software is perhaps the default, which is closed source software. So any software that you might download or buy from companies that it's not open source is typically closed source, which means only their employees have access to it. Now, the downside is that you, the user, do not have access to closed source software. Only the authors, therefore, do. But the upside, arguably, is that now so do adversaries on the internet not have access to it. So maybe the probability that that software not only has mistakes, but those mistakes are exploited is perhaps lower. And so this is perhaps more of a debate, and you yourselves, as you consider this, might require your own opinions on open source versus closed source. But another argument in favor of open source is often that with so many people around the world having eyes on software, perhaps that actually increases the probability that we will detect bugs or detect potential exploits because so many more smart people are looking at it and therefore weighing in. The downside, of course, if one of those smart people is an adversary, they find it and don't tell anyone, then we're back to a problem from a previous class wherein we discussed those zero-day attacks. But this is one way, one mental model you might have for evaluating just how secure your own software might be that you're either using as a user or developing as a company. What's another way that you might gain some assurance that the software you're installing and using is not infected with some form of vulnerability or malicious intent? Well, you could download all of the software that you use only from an approved app store, be it in the world of iPhones or Android devices, Mac OS, Windows, or the like, whereby you have some other entity, like a Google, an Apple, or a Microsoft, a big company, that is at least analyzing the applications that are being uploaded to these app stores before they're allowed to be distributed to people like you and me. Now, that's not to say that Apple and Microsoft and Google's or others are perfect. There have absolutely been many cases where even applications in these app stores has some malicious feature that they only realize after the fact. But again, it's probably increasing the probability that some smart people or automated software is going to detect those things first before it even reaches your device. And therefore, it makes it harder for the adversary, raises the bar, raises the cost, raises the risk to them to even get something like that distributed. So what does this mean? Well, when you install software on your computer, perhaps you should get it only from Microsoft or Google or Apple and not from some random website, and certainly not from some random email that someone sent you with a link to download some piece of software. Now, that's not always going to be the case, and particularly if you yourself are an aspiring programmer, a software developer, you might need to be in the habit of installing sort of unauthorized software for which you might have to jump through some hoops and change some settings in your phone or your Mac or PC to even allow you to install unauthorized software if you know what you're doing. But these kinds of mechanisms, even though they create dissatisfaction with this idea of a walled garden, whereby you need some corporate entity's permission just to distribute your software, they do serve a good purpose as well. So there, too, you might fall on one side or the other of that sort of argument, too. Now, how do those app stores enforce the fact that you can only install the software if it is in the App Store itself? Well, it turns out we can revisit some of our primitives from past classes whereby we talked about encryption and also hashing and also digital signatures. The latter of two are particularly germane here. It turns out that cryptography really is the solution to a lot of the world's current problems when it comes to cybersecurity if we use these primitives, hashing, encryption, and digital signing, as building blocks to solutions. So for instance, when you develop a piece of software, or some company does this for you, and they upload their software to Apple or Google or Microsoft for distribution, what are those companies doing? Well, first, you as the author of the software are first using your own public and private key, which you came up with in advance, and you are running your software through some special function or algorithm and getting back a hash thereof. Again, a hash is this fixed length representation of your software. So even if you wrote a really big program, you have this unique identifier or highly probably unique identifier called a hash. And what you can then do with that hash is use your private key and sign that hash, giving you a digital signature. That signature can be verified by Google or Microsoft or Apple as being, OK, I know that David Malan wrote this software because I know that only he has that private key. And so long as I, David Malan, registered my public key with Apple or Google or Microsoft in advance, they can assume that, OK, this new version of the software or this new program came from David Malan and not from some random person on the internet pretending to be David Malan. Conversely, what Google and Microsoft and Apple and others can do is the same thing. Once you have uploaded your software to their app store, they can ensure that they run the software through the same function, getting back a hash thereof, a unique representation thereof. They can use their own private key from their own app store to take that hash as input and produce a digital signature, this time signed by Apple or Microsoft or Google or whoever else is running the app store. And then when you or I install that software on our Mac and our PC or on our phones and devices can ensure that any software you and I are installing on our device was digitally signed by that app store, by Google or Microsoft or Apple or the like. So again, just by using this basic building block of digital signatures and hashing in this case, you can both attest in one direction that I am David Malan, trust my software is written from me. Conversely, when people install my software, they can trust, if Apple or Google or Microsoft or others trust that software, that they should indeed be allowed to double click it. And it's only when you download some unauthorized software from the internet typically that you get often nowadays on your screen an alert saying this has not been signed, or this is from an unauthorized third-party developer or the like, if they're not playing nicely in this same ecosystem. But again, digital signatures take us a long way there. So another mechanism you can consider, which is similar in spirit, but typically terminology that's used in the world of Linux computers or similar, are package managers. And different programming languages also come with an ecosystem of libraries, third-party code that people write and they make freely available, often as open source, but there's standard ways via which these package managers can let you and me install the software on our own Macs, PCs, phones, or the like. And it's using tools like pip for Python, gem for Ruby, npm for Node.js, and there's others as well, apt for Linux. These package managers, though, typically adopt a very similar mechanism whereby they are digitally signing these packages so that you and I can have our computers verify those signatures before they're actually allowed to be installed. And in general, this involves operating systems as well. The operating systems that you and I are running nowadays, at least if you stayed current and are in the habit of automatic updates or frequent manual updates, odds are today's more modern operating systems are increasingly building in native support for these kinds of checks. Downside is it's getting a little more difficult, a little more annoying to install third-party software on our devices. But the upside is that if you trust these app stores, these package managers, then by transitivity, you can, with higher probability, trust the software being distributed there too. Now this too, though, is not fail-safe. And it has often happened that even once software has been uploaded to these app stores or package managers and made available to folks, and version 1 might be perfectly safe, version 2 might be perfectly safe, version 3 might be malicious for some reason. Maybe the developer finally decided to do what their intention was all along. Maybe the developer, and this has happened too, sold their software to someone else and the third party now is adding ads or something malicious to it. Or someone has hacked their computer or account and gained access to their private key and not just their public key, and therefore are masquerading as them. So even now, you can't necessarily trust the software you're running on your computer. But again, that brings us back to some of our earliest lessons in the class where what we're really trying to do is raise the bar to the adversary, increase the cost, increase the risk to them, and conversely decrease the probability to us that any one of these pieces of software might actually be malicious. Now, there are models that the world has been experimenting with over time to try to figure out how best to reduce these probabilities further. And there's this notion of bug bounties, whereby some companies will actually steer in to the reality that there are people out there with the skills not only to do malicious things with their software, but also good things as well. For instance, people who might very well want to try to find bugs in software, particularly ones that relate to security, if they know that the company in whose software they're discovering these bugs is willing to pay for it. And not in a ransom sense, not in a malicious ransom sense, but in a bounty sense, whereby there tends to be this marketplace for some companies and some products, whereby if you do discover a bug in their software and you disclose it only to the designers of the software, at least during some window of time before you tell the world about it, they will pay you. So that once they can therefore fix the bug, then pay out because it's a net positive for everyone. Win-win. You have benefited, they have benefited, and hopefully no adversaries have found it first. And depending on the severity of these bugs, you might get paid more or less based on the same. And so the idea here of these bug bounty programs is to try to leverage the collective intelligence and technical skill of people who, frankly, without these programs, maybe would be using their skills for evil and trying to hack these systems and monetize them through ransomware. But perhaps we could channel those funds instead toward paying people to do this kind of work. So this too is something to consider, not so much as a user using software, but perhaps a company developing software. So where can you learn more, and what has the world come up with to keep track of like all of these possible threats? And what we focused on today really are representative attacks using some languages and technologies that are quite omnipresent and fairly accessible, at least at the level we've explained them. But it turns out that there is a whole inventory of vulnerabilities that have been detected over the years, common vulnerabilities and exposures, or CVE, such that a lot of the kinds of attacks we've been talking about today, and more specifically bugs and flaws in specific software and versions thereof, are often assigned a unique identifier, a CVE number that system administrators, companies, and even end users can keep track of to make sure they are always current with the latest threats out there. There is also a common vulnerability scoring system, or CVSS, which is a standardized way of assigning a score to the severity of a vulnerability. Is it a big deal, or is it not so much a big deal? It might still be a vulnerability, a bug, but is it that problematic? And so there's this scale so that you can prioritize things, for instance, given limited resources or time, which of the bugs you should be fixing, which of the software you should be updating, or maybe which of the software you should not be using, at least while it's vulnerable to something that's highly severe. There's an exploit prediction scoring system out there, EPSS, which refers to what do people in the real world think the probability is that this particular bug or mistake in software will be exploited is. And this then might give you a sense of just how problematic it is. Even if there's something very severe, is it more of a hypothetical threat or an actual threat? Something that IT people might indeed take into account when designing how to respond to some system. And then there's a known exploited vulnerability catalog, KEV, which refers to all of these kinds of bugs that are known to have been exploited. So suffice it to say, here we're now seeing evidence of just how big of a world, how big of a space cybersecurity is, that we have all of these lists and taxonomies for keeping track of things. Because if you're feeling a little overwhelmed with just some of the concepts, imagine just how many hundreds, thousands of actual threats and vulnerabilities there are in the actual wild. All right, so that's a whole lot of threats to the security of your software, whether you're using it as a user or writing it as a developer. But hopefully by way of today's examples of how software works, how adversaries can take advantage of it, and how you can defend against it, you have a much better sense of how to manage those threats. Up ahead is how we might now preserve our own privacy. More on that next time. All right, this is CS50's Introduction to Cybersecurity. My name is David Malan, and this week let's focus on preserving privacy. Indeed, over the past several weeks, we've focused on securing your accounts, your data, your systems, your software, and all of that is really about keeping communications between points A and B, for instance, secure so that no one in between can actually access the information you're trying to share. But what if you, A, don't even want B to have some of that information? So indeed, today, let's focus on some of the technologies that you and I use every day, and some of the technologies that underlie the software and applications and more that you and I are going to use tomorrow and beyond, and consider exactly what information we're sharing now, perhaps even without our knowledge, and also empower you with certain mechanisms via which you can perhaps restrict all the more of this information if you indeed do not want to share it beyond yourself. So let's consider first some of the obvious features that you and I probably use every day, like your web browsing history. Whether you're on a laptop or desktop or mobile device, odds are you know by now that your browser tends to keep track of pretty much everywhere you go on the World Wide Web. That is to say, if you click on your URL bar, you can sometimes browse through the past few URLs that you visited. If you go up to your browser's history via some menu, you can probably see everything you've done earlier today, yesterday, last week, last year, or perhaps even the entirety of your history, particularly if you're logging into your Google account, Microsoft account, or something else. So the web browsing history is sort of both a concern when it comes to your privacy, but also a feature. Well, let's first consider the feature. Well, why is that useful? Well, one, I mean, even I occasionally go back through my history trying to find some web page that I know I was looking at earlier in the day, or yesterday, or some previous time in the past, because it just helps me find information more quickly. So in that sense, it might solve a problem for me. me. Moreover, you probably have noticed that your web browsing history is often used for features like autocomplete. So when you start typing a URL or maybe even a keyword that was in the name of a page, your browser might remember much more quickly what it is you're looking for, so you can just hit enter or click and voila, you're at that same page. But of course, this is a concern potentially for your privacy, whereby you might not want someone else who has physical access to your device to start poking through where it is you've gone. You might not want someone else to have access if you just so happen to visit that website or those websites on maybe a computer in a lab environment or an internet cafe or the like. So you could imagine quite a few scenarios in which this is, yes, a feature, but quite a few other scenarios in which this is not really a desirable feature because it invades your privacy in some sense, or at least puts it at risk for being invaded by someone else. So we'll consider how we might at least sanitize this history or remove it altogether in ways that you might already know about. For instance, you're probably already familiar with some option in your browser whereby you can clear your browser history. And that forgets, therefore, all of the places that you've been, all of the cookies that you might have accumulated, all of the usernames and passwords that might have been remembered by your browser. Although that tends to be a fairly heavy-handed solution, because when you clear your browser history, assuming you check all of those boxes, like all of it is gone. And that might mean negatively that you're now logged out of Google, you're now logged out of Outlook, or some other account that you actually still want to use, even if you just wanted to clear your history from something else altogether. So we'll consider then what else might be a concern when it comes to your privacy beyond your own browser. And in fact, it doesn't even matter if you sanitize your own web browsing history and delete the entirety of it, because it turns out that typically any website you visit is itself on the server side also keeping track of a lot of that same information. That is to say that servers typically have logs, and these are not only for diagnostic purposes in case anything goes wrong. The IT staff can use those logs to sort of reconstruct history and figure out who was doing what and when and how that might explain some problem. It might be used for auditing purposes if they want to keep track of exactly what was accessed on a system. It might be used for advertising purposes or analytical purposes more generally to kind of mine or analyze that data to figure out how we might monetize it or do something else with that same information. But what do we mean concretely when we say that information is logged on a server? Well, it's very similar to your own web browsing history, but it's even more detailed. So here, for instance, is a representative piece of configuration that captures what it's a very common convention for information that servers log, web servers specifically, when you visit them with a browser. And I'll highlight just a subset thereof. This log format, the so-called combined format, indicates to me that it's very common for a server, when you visit some web page on it, that the server will log, that is, remember your remote address, otherwise known as your IP address. It will remember the day and time at which you access that page. It will remember exactly what you requested, so the name of the file or folder on the server specifically that you sought to download or look at. It'll remember the referrer, that is the URL from which you came, and it will even remember the user agent that you use, that is to say, your browser. So perhaps unbeknownst to you, every time you use your browser to visit some website, inside of that virtual envelope is quite a bit more than just the request that you're making of the browser, of the server rather. It includes, yes, your IP address, and on the outside of the envelope as we've described it in the past. It includes some number of HTTP headers as we've discussed in the past, but in particular, it includes information that you might not want being stored on servers in perpetuity, and you have no control over deleting necessarily, unless there is some regulatory requirement or law that requires that the server delete it for you on some schedule. You have much, much less control over this information. So let's consider in a bit more technical detail what some of this information is and how you might at least exert some control over just how much of that information is being shared. So let's revisit first this building block of HTTP headers that we keep coming back to, if only because in the world of systems and software nowadays, things on the web are just so common. Using HTML, CSS, JavaScript, using web browsers and web servers, that's driving a lot of today's interactions with technology, whether it's in native applications or whether it's with mobile websites or desktop websites or the like. So HTTP headers, recall, are just like key value pairs that are inside of those virtual envelopes that indicate some kind of setting or some kind of piece of information that the browser is sending to the server, or that the server is sending to the browser. So for instance, if I go on google.com and I search, as I often do, for cats, well, what might be going on underneath the hood? Well, in that web page that Google gives me with like 10 or 20 or 30 or 6,240,000,000 cats, there might be HTML that looks like this. And recall that this HTML, which I'm proposing exists somewhere in Google search results, is an anchor tag for a link. There's the end tag over there. The hyperreference for this link, or href attribute, has a value of https://example.com, for instance. And the word that the human will see is cats, literally in this case. Now, I'm assuming for the sake of discussion that today, example.com is a website full of cats. And that's why it might be appearing among Google search results when I search for cats as my keyword. But when a user, like you or me, clicks on that link on google.com, because that is literally where you're looking at the search results in this story, it turns out that your browser not only goes and requests that web page, your browser includes an HTTP header like this in that virtual envelope that's specifically called referrer. That's the key in this case, the value of which is the URL from which you came. So for instance, if I have just gone to google.com and I've searched for cats and I've hit enter, recall as in past classes, I proposed that the shortest version of the URL that you might see in your browser upon searching for cats is this: https://www.google.com/search ? Q=cats. Now that is what you'd see in your URL bar. Below that, you'd see the 10 or the 20 or the 30 or the 6,240,000,000 cats, each of which has a link that when clicked leads you to a search result. But the implication of this HTTP header is that by default, perhaps unbeknownst to you indeed, your browser is telling the whole world from which web page you came when you visited some other web page via a link. Now, why in the world is this compelling? Well, it's actually useful for the website at which you end, because it might be useful for their analytics. They might want to know, well, how are people finding my website? How are people finding my business on the internet? Oh, it looks like I'm getting a lot of users, a lot of customers perhaps, from google.com specifically when someone searches for cats. Not dogs, not something else, but cats. So you can imagine, especially in the world of commerce, that just being useful information to know how people are finding you, or conversely, how people are not apparently finding you. But this is very invasive, because now this website, even though it's arguably none of their business, they know I use Google instead of Bing or some other search engine perhaps. And you can imagine that there could be links on CS50's own website, on any number of other websites in the world. And just because you happen to visit them and you clicked a link, now they're broadcasting your business to whatever website you're ending up on by revealing where you came from where you were referred, so to speak. But this has long been a feature of HTTP, and this has long been a feature that's enabled by default unless the website, or perhaps you as the user, turn this off or somehow moderate its response. Now, some of you might be noticing that there's a bit of a typo on the screen, and I promise this isn't actually mine. In English, at least, this is not typically how you spell the word refer. And this is actually a fun fact. In referrer, there should be 4 R's in total. It should be R-E-F-E-R-R-E-R. However, fun fact, years ago, when the specification for this standard was being written, the poor individual who wrote the specification made a typo that has been immortalized in history for years to come. And so this is what browsers and servers have been using and expecting for years. There are other variants of this header that the typographical error has been fixed in, but it's sort of a fun fact from our internet history. But this is indeed what you might see going from your browser to your server. So ideally, we'd send less information, at least, right? I'd be a little more comfortable if example.com, which is this website for cats, told them, OK, fine, I came from Google. That's not a big deal. But I'd rather you not know what I was looking for, if only because that seems unnecessary. It seems invasive. And who knows what kinds of cats I was looking for. Maybe I don't want you to know exactly what my preferences are in cats or dogs or whatever types of breeds there might be in this case of searching for animals. So just feels like it's unnecessary information to share. But better still, I dare say, would not be to even tell example.com where I'm coming from and essentially just get rid of this altogether. So how might a website go about moderating just how much output comes from the browsers at the server's request? Or maybe how might you, with special software, suppress some of this information to preserve all the more of your privacy and what it is you're doing online? Well, for instance, this is a common tag that web pages can put in their own HTML code that indicates to the browser that, yes, you may send the referring address, but only send the origin. That is https://www.google.com/. And that's it. No search path, no question mark q equals cats. Tell them the website you came from, but not the specific page or not the specific search query or search results. Notice here in the world of HTML, the typographical error has been fixed. There's two R's in the middle there. But otherwise, this is an HTML solution to the problem. The browser, assuming it respects this HTML, will therefore send and refer HTTP header, but with less information. Not the whole URL, but just the origin. So really the domain name itself and a bit more like the protocol. If you don't want any of that to be sent for your users, for your customers, you could do this instead. Now, Google does not do this. Google currently actually sends origin, so part of the URL. But if you want to be an even better citizen and not make it easy for browsers to send more information than they need to, you can include this HTML in your page instead, informing the browser that you can don't send a referrer at all because the value of this meta tag, so to speak, is actually none instead of origin. And there are other values as well that allow you a bit of range of opportunities when it comes to these settings, but these are perhaps the most common or ones to consider. There's an alternative too. If you happen to be a little more technical and you have control over the web server and not just the HTML on the server, you can actually configure a referrer policy HTTP header that goes from the server to the browser. So in this case, the referrer policy can indicate that you only want the origin to be sent, for instance, the shorter form of the URL, or you can actually indicate that no referrer should actually be sent in this particular case. So a second mechanism for actually controlling the same. Let me pause here and see if there's not only some concerns perhaps now that you understand better, hopefully, how the web works, at least by default, or how we might mitigate this concern with your privacy.
Is there a way that is like easy enough for us to delete those traces as a client, like in case that we don't want to be tracked or something like that?
A really good question. We'll refer you to some URLs outside of the context of class itself. But yes, there is actually client-side software that you can install on your own Mac or PC typically that will scrub some of this information so that when your HTTP requests go from your browser to servers, you can ensure that this third-party software removes a lot of that information automatically for you. Because in that way, you don't have to trust that the website, like the Googles of the world, will actually reduce the amount of information for you. You can instead do that for yourself through client-side software, and we'll provide a few links online. Other questions on the same?
By using a private browser such as Tor, for example, or using a temporary operating system like Tails, does this remove all of our traces on the internet, or does it leave some on the client side or the server side?
A good question. Short answer is that it does leave some evidence on both the server side and the client side, but we'll come back to Tor in just a little bit as well. All right, how about one final question?
You said previously about the third-party software that's supposed to be used in order to scrub the information from being submitted to the server side. What if that program itself is used to eavesdrop on what we do in the computer?
That is a very valid concern. It is absolutely possible. In general, what is working in your favor is either open source software, where if you're using software that other people can see the source code of, presumably it's less likely that it's doing something malicious. Capitalism often helps you here too, whereby it is often not in a company's own interest to be violating the privacy of their users, because presumably that would create some form of backlash, which would not be good for business. But beyond that, there is a lot of trust on your part and my part whenever it comes to installing software. So that is indeed very much a risk. Now, it turns out there's other information that your browser might be sharing without your realizing that it's making it available, and that information is enough via which servers can even fingerprint you, so to speak. That is to say, there's this technique, generally called fingerprinting, that in the context of the web means to take as input a whole bunch of characteristics of the request from the internet that's coming in, and see if you can use those characteristics to create a profile of sorts for the user via which you can uniquely identify that user. Now, that doesn't mean you'll know specifically that that user is David Malan, but you will know, according to this system, if it's the same user today as you see tomorrow, as you see the next day, because you can use this information to infer with high probability that, okay, we saw that exact same browser configuration again and again and again. Odds are it's the same person and not some twin on the internet who just happens to have precisely those settings. Now, how might this be implemented or achieved technologically? Well, the simplest mechanism, perhaps, is just to rely on something like your IP address. Recall that anytime you're doing something on the internet, those virtual envelopes we keep talking about have your IP address on the outside, so to speak, as well as the IP address of the destination to which you're trying to send information. Your IP in that case is the return address, which means you're literally telling the remote server, when using certain protocols, where you are in the world, or at least what your IP address is. Now, that IP address might not alone uniquely identify you, because it turns out on campuses, in homes, in corporate networks, you might actually share one IP address with many other people, but it at least narrows the scope of whose IP it might be, even if it's shared among a few people. But your browser, inside of that virtual envelope, is sharing other information as well. Another HTTP header that is typically sent by browsers to servers is called user agent. And this is just a unique string of text that uniquely identifies typically the browser that you're using and the version thereof, and the operating system that you're using and the version thereof. So for instance, a standard format might look a little something like this. It's deliberately overwhelming, and it's just meant to capture how much detail might be leaked in this header's value. But within this big string of text that doesn't even fit onto one line, it's wrapping here onto 3 lines, is some indication of what browser you're using, be it Chrome or something else, and what operating system you're using, be it Android or something else, on a phone, a laptop, or a desktop. Now, of course, a lot of people in the world presumably have the same browser installed, so that too, even with IP address, might not be enough information to uniquely identify you, at least with high probability. So what else can servers do? Well, if the server has the ability to send some code to your computer, for instance, some HTML, some CSS, and some JavaScript, servers can effectively interrogate the browser and ask it certain questions. For instance, a server could figure out what the resolution is of your screen. Now, this might be practically useful, so they know how to render information on the screen, but that alone might be enough, especially if you're in the habit of full screening your browser and you always use the same resolution on your monitor. That might be another ingredient with which to identify or fingerprint you. The server might be able to figure out what fonts you have installed on your system. The server might be able to figure out what time zone you are in, because that's also a value available within the context of a browser. And there's yet other values still that collectively, with high probability, can be used to fingerprint you and me. So even if you're not even logged in, even if you're using various privacy-enhancing software products to try to remove some of these HTTP headers and the like, you're still leaking other information, including the extensions or plugins sometimes that your browser might have installed. So if you're in the habit of using the same computer again and again, and you're in the habit of not changing a lot of these settings, that alone might be enough for a website to effectively track you. Now, it might be innocuous. They might just use this for statistical purposes to get a sense of how many users or customers they have. But it could be for more invasive purposes, like serving you targeted advertising based on your behavior of these websites, or really just tracking you specifically. And the catch is that if you ever log into this server just once, if the server's been logging all of your traffic based on that fingerprint for days, for months, for years, at that point, retroactively with high probability, they can infer, oh, wait a minute, if the user on this day was David, and we think it was the same user on all of these previous days, now by transitivity, they know a lot more about your browser history as well. So even unbeknownst to you, and even without explicit header values being sent that identify you, the collection of attributes or characteristics that our browsers have and our browsing behavior has can still be enough to uniquely identify most of us quite a bit of the time. Let me pause here and see if there's any questions on fingerprinting or these implications for privacy.
Would using like a VPN prevent browser fingerprinting?
A good question, and we'll talk about VPNs a bit more soon. Short answer, no. So VPNs will typically mask your IP address, but that's about it. If you still use your browser as usual, with your user account as usual, all of that same information is going to be leaked. It's just going to change one piece of it. A good question. Other questions on fingerprinting and privacy?
Is it possible that a hacker can steal a fingerprint and use it for their own purposes, and everything will look like it was my computer that performed certain actions? So it's like stealing an identity.
A short answer, yes, if the hacker has access to the same information. If we rewind to our focus on encryption a couple of classes ago, if you are accessing websites only via HTTPS and nothing is unencrypted, then it's going to be a lot harder for a hacker in between you and that server to glean any of the same information, because almost all of it is encrypted. IP address is not, but anything inside of the envelope is, including these headers, the HTML, the JavaScript, and the CSS. If, though, the hacker has somehow infiltrated your own laptop or desktop or phone or the server, then all bets are off. And they could absolutely identify you according to these same pieces of information. Other questions?
I was just curious to understand the difference perhaps when you are on mobile. My understanding is that they can even get much more information when you are on mobile.
That's a fair question. I don't think I would answer yes to that. I'm hard-pressed to imagine what more your phone is doing than the browser is doing, except that there are, I suppose I could argue that your phone tends to have additional features nowadays, like GPS, like accelerometers, gyroscope perhaps, so other hardware features that theoretically can be interrogated by JavaScript code, typically on an opt-in basis, so you, the user, could deny access to these pieces of information. But those characteristics, I suspect, could be used to identify you a bit more uniquely, because laptops, at least today, have less of that functionality. Other questions?
When storing and retrieving data on the front end, is it more secure to use cookies, local storage, or another alternative?
A really good question, and we will come to this subject literally in like one slide, cookies. In general, local storage, because cookies by design are meant to be sent back and forth between browser and server. Theoretically, that should not be a concern if everything is encrypted, but we've talked in the past already how mistakes can be made. You might start on HTTP, be redirected to HTTPS. So in general, storing things in local storage at least prevent things from accidentally leaking out over the browser connection. That said, if you're storing things in local storage, they are literally available locally. So if you have a colleague, a friend, a sibling who gains physical access to the device, let alone an adversary, then they could see all of the information in not only your cookies, but also local storage. So at that point, physical access, generally all bets are off when it comes to your privacy. All right, how about one other question?
There were calls being made from people's local phone numbers on cell phones to other local numbers. Obviously, the people weren't making the calls. And it happened to me too, and I was wondering how that kind of works, or if it's related to this at all.
It is. We weren't planning to talk about it today, but in a nutshell, it is very easy to spoof telephone numbers. And this is how a lot of spam calls are sent, particularly internationally or abroad, where they might not be regulated in the same way as someone's home country. It's very common, too, for if your number starts, your own phone number starts with 555, for instance, very often you'll get fake calls from other numbers that also start with 555, because the presumption by the adversary is that, oh, Sabrina's probably more likely to pick this up if she thinks it's a neighbor with a similar looking phone number. But unfortunately, with the phone system, it's all too easy to fake phone numbers. And this is yet another reason why using phones, using SMS, is not a recommended approach for our earlier topic about multi-factor authentication. It's just not a secure network. That's not how Edison and others designed it 100+ years ago. This is why systems that use cryptography in some form are much safer when it comes to that information. All right, so beyond this user agent header, there's other headers that your browser is often sending back and forth with the server. And one of these we've talked about, and one of these you probably came into the course knowing about, namely cookies. But there are different types of cookies. But recall that in general, a cookie is a piece of information that a server puts on your computer to help remember who you are. So in the absence of these fingerprints, in the absence of specific headers like these, it can just put a small random value with numbers and letters or the like on your computer, or maybe even a bigger value if it has lots of users, and it uses that value to uniquely identify you if you return again and again to the website. It doesn't necessarily know that I am David unless I log in at some point, at which point then it can realize, oh, wait a minute, David's cookie is this value. Now I know who this user is. But in general, there are different types of cookies and different settings for cookies that are worth knowing a little something about. So we talked previously about what we'd more properly call session cookies. So session cookies are used by servers to maintain state, so to speak, between the server and the browser. That is to say, without getting too technical, HTTP is typically stateless, whereby when you visit a page, the browser icon might spin for a bit and then it stops because the transaction between the browser and the server is complete. But if you want to remember who the user is, therefore the second, the third, the fourth time the browser contacts the browser had better remind the server who it is. And this is why we use the metaphor of the virtual hand stamp, whereby that hand stamp is like the browser's way of reminding the server, you've seen me before, don't make me log in again. I am David. I am David, even though it's just relying on this virtual hand stamp or really some unique identifier that's going in the cookie header from browser to server. So a session cookie allows browsers and servers to maintain sessions, this kind of state. A little more concretely, it allows them to maintain things like shopping carts. So if you're shopping on an Amazon.com or the like, the session cookie is what remembers who you are, or at least that you're the same person, so that every time you poke around on the website, Amazon shows you the same contents of your shopping cart again and again, so that they don't lose your business by accidentally deleting it when you simply change the page. So how do session cookies work? Well, when you first visit a website that wants to plant a cookie on your computer, the response might look a little something like this. HTTP 200 is the status code, which recall means OK. All is well. It's not something like 404, which would mean file not found. So 200 is OK. But the server might also respond with this key value pair, this HTTP header, set-cookie, : so that's the key, the value of which is session equals 1234 ABCD. And that's the same value we used previously when we talked about cookies in this context. And the point here is that the name of this cookie is session, and its value equals, in this case, 1234 ABCD. Now, if you visit the same website, and you, and you, and you, we would all have different, seemingly random values for those cookies. And so this number, this sequence of letters and numbers would be different for each of us. That is to say, we have different hand stamps that we're presenting each time. Now, this is a session cookie, and it's a session cookie in the sense that it is supposed to expire when you close the browser, when you quit for the night, when you reboot, or anything else. Now, with that said, that's a bit of an overstatement because browsers nowadays will frequently preserve your tabs for you. They might go to sleep. You might have to wake them back up. But increasingly, sessions are living longer than they once did. But the idea is that this is not meant to last for like a year or forever. It has a much shorter lifetime by design. When your browser has received that cookie and you click on some other page, you visit some other product on Amazon.com, your browser might say something like this, get / and then cookie : that exact same value. So recall from our previous class, this is how the browser just reminds the server what its hand stamp is or what its cookie value is. But again, the idea is that when the browser is closed, you reboot for the night, then you should not have the same session cookie tomorrow, at least in this model. That's not true for all websites, but according to cookies as we are currently using them. Now, that's pretty good for your privacy, because if the cookie is by design meant to be a session cookie, and it sort of expires pretty soon when you're done with that browser tab or done using the browser for the day, then that's pretty good, because it means if you go back to the same website tomorrow, that cookie might not exist anymore, so you might as well look like or be a brand new user. So they can't correlate, perhaps by default, as much information about you. But these are the cookies that you read about being bad for you and bad for your privacy. Tracking cookies, which are the exact same idea, key value pairs that are sent from server to browser to remember who you are, or at least that you're the same person, even if we don't know that you're David Malan specifically just yet. But as per the name, tracking cookies are really designed to track you and me. Why? Well, maybe analytical purposes, maybe debugging purposes so that they know where users were in case something breaks, maybe advertising purposes so that you get served different ads from me so that they can maximize their revenue by serving up ads that you and I are each more individually likely to click on. So tracking cookies are the ones that get a bad rap, and rightfully so. So let's consider an example of a cookie that's designed to track your behavior on a particular website. Here, for instance, is a set cookie header that Google specifically might send to your browser. In fact, they use a cookie that by convention is called _GA for Google Analytics, which they use for analytical purposes, and its value looks a little something like this. And the point of this value is that it's generated on a per website basis if that website is using Google Analytics. And Google Analytics is a tool that allows website designers to track who is clicking on what browsers they're using, what operating systems they're using, and generally giving them a sense of the demographics of their user base. But unlike session cookies, which are meant to expire after a day, after the browser closes or the like, Google's analytical cookie here has a maximum age of this many seconds, which if you do out the math is by default 2 years. Which is to say, if you visit some website that is using Google Analytics by embedding a bit of Google's JavaScript code in their website, whenever that Google code is pulled from Google's website, Google has an opportunity to plant this cookie on your computer. And you'll get a unique ID based on you visiting for the first time, based on the specific website that is embedding Google Analytics. And that cookie is going to live in your computer, according to this HTTP header, for as long as 2 years. Now, that's useful for Google. It's perhaps useful for the website. It's perhaps a little more invasive for me and you. Now, Google has many other cookies that they use too, but this is perhaps one that you should keep an eye out for. And indeed, in the coming weeks or months, if you poke around some of your own browser settings, you might very well see values like this. But what else might servers use to keep track of us, especially if you and I are in the habit of deleting our cookies or clearing your history, which would be counterproductive for Google or websites that are trying to track you in this way, but a plus for you and for my privacy if you're behaving in this way. But it turns out there's other ways servers can track us, including through HTTP parameters, tracking parameters. So parameters are the key value pairs that often appear in URLs that are sent via GET requests typically. So we've seen one of these. If you recall when we've searched for cats on Google before, you might recall that the URL was something like https://www.google.com/search Q equals cats. Anything after a question mark in a URL is indeed an HTTP parameter, but it could be used not for innocuous, helpful purposes like searching for cats, but also to track you. And in fact, if you see ampersands in URLs, that might mean that you have a second or a third or more parameter up there. And sometimes the purpose of these parameters is simply to track you as some person. So for instance, here is a representative URL. It's a long one. And this is taken from example.com, having a path of add_engagement, ? And then I'll highlight here, click ID equals, and then this long, seemingly random string. But there's a second HTTP parameter in this particular URL, &campaign ID equals 23. So the campaign ID, certainly with such a small number, is not meant to track you. That's meant to be sufficient input to the website to know what types of ads should be served to you, what ad campaign should be served up. But this click ID, which is sort of a euphemism for tracking cookie or tracking parameter in this case, is what's actually keeping track of you specifically, because different users are going to find that whatever link they click on has a slightly different value for click ID. So recall that a tracking cookie is something that's sent via an HTTP header, and so it's harder for you and me to see it unless we're more comfortable with our browsers and can poke around some underlying settings. But these tracking parameters are right there in front of you, at least if you click on the URL in your browser and take a look at its entirety. Now, wonderfully, at least for us end users who are concerned about privacy, browsers and even third-party software are increasingly removing values like this for us. As soon as the browser manufacturer or as soon as the third-party software developer knows that, wait a minute, Click ID has no good purpose other than tracking our users, they can simply automatically remove it for you. After all, when you visit a web page and you get the HTML that represents that web page, the browser could certainly poke around there before you even have a chance to click on anything, and it could scrub or sanitize these kinds of tracking parameters. Now, to be fair, if the browser manufacturer doesn't necessarily know what the tracking parameter is called, or if maybe the website is constantly changing the name or trying to mix things up, this might not work so well, but it's at least an attempt to try to put downward pressure on this very commonplace technique of keeping track of you and me. Now, why is this parameter able to track us? Well, this too can end up in those server logs, because this would be, for instance, the web page that I am requesting, /add engagement click ID equals ... That could very well be logged by the server, stored in a database even, and they could use that information to know exactly which pages I have clicked on, because I visited those links, and even what ads I have seen. And maybe that's a good thing commercially, because now they know what types of ads I'm clicking on. Now they can serve even more of them to me, and that might be great for them, but probably not so great, if not annoying or invasive for me and you. So something else to keep an eye out for, and something else that might guide your decision making in the days and the years to come when it comes to picking your browser. You don't necessarily have to nowadays use the one that comes with your phone, comes with your laptop or desktop. You can, if more comfortable, install something else, and increasingly you and I are having more and more options. Questions now on these tracking parameters or anything prior with respect to our privacy?
Are the cookies the ones that track, or are the ones that have been tracked?
The cookies are values that are being used to track you. So recall that a metaphor for the cookies is like that virtual hand stamp. And so if all of these web servers are putting ink on your hand and on my hand, and because of HTTP, you and I, our browsers, are in the habit of presenting these cookies, these hand stamps to every website we visit, that value is being used to track us. So cookies in and of themselves are just a technology. It's a very simple idea, storing a big random value on your computer and mine just to uniquely identify us. They are necessary to give us features like logging into websites, maintaining shopping carts, but very quickly, especially since the internet from the get-go has been largely free to use, or rather a lot of the internet has been free to use once you have a connection at least, they've been used, or in some views abused, by the advertisers, the Facebooks, and the others of the world. So another way to think about tracking cookies is to consider them to be third-party cookies, because indeed, even in the Google example, that's how they're being used. If a website like example.com is embedding Google Analytics, and therefore some kind of HTML tag that mentions google.com, well then example.com is the first party in that story, so to speak, and google.com is the third party in that story. What that means is that your browser might get cookies from both example.com and google.com, but the most important ones, presumably, are the first-party ones from example.com, because that is the website you chose to go to and whose functionality you want to use. The third-party functionality, like tracking your clicks and your internet behavior on that site via Google, that's third-party, and so very commonly do browsers nowadays certainly offer options via which you can disable third-party cookies. And that tends to be good for privacy's sake, because it means that you're blocking third parties like Google from keeping track of you via cookies, but that doesn't necessarily mean the website isn't still using tracking parameters in some way, and you would only know that by actually looking more closely at the URLs you're clicking on or that are embedded in the web page itself. And that's where now browsers and third-party software are additionally helping by helping us remove not only those cookies, but even those parameters. But let's consider a more concrete scenario of what third-party cookies are and why they allow companies not only like Google to track your behavior on one website, but even companies like Google or other advertisers to track your behavior on multiple websites. And in this sense, third parties have increasingly been more powerful, more omniscient, for instance, than the first-party websites that you and I are actually visiting. Why? Well, if there's a lot of popular third parties out there, Google being one of them for advertisements and for analytics, well, if lots of different websites are using them, maybe Harvard's using them, Yale's using them, Stanford's using them, then that third party very quickly becomes more powerful than even any of those individual parties alone. Why? Because that third party, if it is being embedded in at Harvard, Yale, and Stanford, that third party, Google for instance, kind of has eyes into all three websites. And if it sends the same cookie to you on all three websites, Google might actually know that you're poking around Harvard's and Yale's and Stanford's website when Harvard might have no idea you're checking out Yale and Stanford. And Stanford might have no idea you're checking out Yale and Harvard. So what does this mean concretely? Well, consider some HTML here, such as we've seen before, and I've highlighted a couple of salient characteristics in this particular example. Notice that I've given in this web page not only a body, which contains the body, the bulk of the web page, I've also included a head for the web page, inside of which is another tag called title. And I'm doing this just to, one, demonstrate there are more tags than we have seen in this language thus far, and specifically this, I claim, is meant to represent harvard.edu's own website, the title of which would be Harvard, like in the tab along the top of the screen. And inside of the body of this page, for simplicity, let's assume that for now there's just one big advertisement. There's no content for the sake of discussion. There's just one advertisement. Well, where is that advertisement coming from? It's coming from, in this case, example.com, or our friends at Google, specifically a file called ad.gif. And this particular URL is being used as the value of the source attribute of an image tag. So what do I mean by this? Well, if you visit harvard.edu in the story, what you are seeing is a big advertisement, a big GIF, a graphic that is coming from example.com. Now, what is the implication of that? Well, suppose that Yale is doing the same thing. So here now, for the sake of discussion, is the exact same HTML, except it lives at yale.edu. So the title of the page has now changed to Yale. And moreover, just to make things really interesting, let's add Stanford to the mix. Same exact page. So the point of this story is that Harvard and Yale and Stanford are all using the same third party, example.com in this case, or maybe someone like Google in the real world. And they're requesting, moreover, the same GIF. And so the same file is being accessed, but that even alone isn't a strict requirement. The same website is being accessed by all three of these first parties. So what does that mean? Suppose that you open up your browser and you first visit harvard.edu. Your browser is going to download the HTML for Harvard's website. It's going to see that, oh, there's an image tag in there, and that image tag wants to show this ad.gif from example.com. So your browser is automatically, by nature of how browsers work, going to send a second HTTP request, this time requesting ad.gif from the host, example.com. And just to tie today's stories together, it's going to include probably a referrer HTTP header that specifies where I'm coming from. And that's useful for our purposes because it puts these requests into context. Now, that server, example.com, or Google in the case of the real world, is going to probably respond with 200 OK, like, OK, here is the advertisement. And it's going to include not only the image, but also an HTTP header of its own. And this is our old friend setCookie, where in this case, for the sake of discussion, I'm going to propose that it's setting a cookie on my computer called ID, because this is going to be my unique identifier for example.com. Its value is going to be the one I keep using for discussion's sake, 1, 2, 3, 4, ABCD, but that would be some big random value for each of us. And my gosh, this thing's going to last a year. That's the number of seconds in 365 days. So this cookie is being planted on my computer by example.com because I visited harvard.edu. So Harvard is the first party, example.com is the third party in this case. But here now is the concern. When I visit yale.edu with that same browser, my hand has been stamped by example.com already. And so what happens is that my browser now presents that hand stamp to example.com, sending the same ID and the same value. That is the same hand stamp. The host is, as before, example.com, but this time the referrer happens to be Yale. So in other words, after I visited Harvard and my hand has been stamped with this tracking cookie, this third-party cookie from example.com, my browser, when I visit yale.edu, is going to present that same hand stamp again, this time to example.com with this referrer. The next time I use my browser to visit stanford.edu, the same message is going to be sent from my browser to example.com to request that same ad, this time now from stanford.edu's website. Now, what's the implication? Via these 3 HTTP requests, example.com knows that I'm visiting Stanford, and before that Yale, and before that Harvard. And none of Harvard or Yale or Stanford necessarily know that I'm visiting any of those other websites. The third party is the more powerful. It's the more all-seeing, simply because example.com, or in the real world Google, is just so darn popular that it's embedded in so many darn websites. Google and others know almost everything, dare say, about what you and I are doing on the web, because these ads are all over the place in this way. So we've seen a very simple example, but it's simple because cookies and HTTP really are relatively. It's once you realize how they work that you can use them not only to solve compelling problems for all of us, sessions and shopping carts and the like, but also can be used to monetize the internet, and has been used historically to monetize the internet, or even worse perhaps for us, to track our individual clicks and behavior. So let me pause here and see if there's any questions now on third-party cookies, and why, therefore, it's perhaps so compelling for you or me to opt into disabling them, or better yet, to use browsers that are starting to block them for us.
What browser are more secure among other considering tracking parameters?
Sure, a quick tweak. I wouldn't say that some browsers are more secure than others in this context. I would say that you want browsers that are more privacy conscious or privacy preserving, because that's what we're talking about today. Hopefully all of them are just as secure when it comes to HTTPS and the encryption that's just keeping our data protected between points A and B. So generally, Safari has been pretty good when it comes to privacy, and they are the ones that very recently, that you're using now, announced that they're going to start giving people the feature of removing tracking parameters from URLs. In fact, the sample URL I gave was actually from Apple's recent announcement about exactly that. DuckDuckGo is probably the most popular third-party browser that is very privacy conscious and tries to disable a lot of these tracking behaviors. Another one is Brave. Perhaps the worst offender is probably Chrome, even though I myself am guilty of using it myself because it's so integrated into Google's ecosystem. But Google, of course, has made their business on monetizing your behavior and mine. So that is perhaps one to put toward the bottom of the list if you're concerned about this. So that's kind of how I would rank things. And there's yet others, but I think those are some of the most popular. And then, of course, in the Microsoft ecosystem, there is Edge. And Firefox, too, has actually, I should have put them higher on the list. They are more privacy conscious, I do believe, than Google. So with all of these mechanisms for tracking in mind, what can we do to protect all the more of our privacy? Well, you might already know of this feature, private browsing. So you don't necessarily have to delete all of your browser history and delete all of your cookies. You can instead, on occasion, open up a special type of window, which most of today's browsers support, that puts you into private mode or incognito mode. And you can think of this as giving you just a different chunk of memory in the computer that doesn't know any of your past browser history, that doesn't have any of your past cookies, that doesn't remember any of your past usernames and passwords. You're starting fresh so that everything you do in that window is brand new. The catch, though, is that everything you do in that window still works exactly as the web works as we have been describing. So you still might have tracking parameters. You still might have tracking cookies. You still might have server logs. But when you close that private window or you close that incognito mode, at least the information is discarded from your computer. So that if tomorrow you do the exact same thing and open up an incognito window again, then it's as though you're starting fresh with that server. Except for the reality, as per our past discussion, that fingerprinting is still a possibility. Your IP address can still be factored in, as can be other information that your browser might still be leaking. But what you're not doing is contaminating, so to speak, your general browsing history with specifically what you're using that window for. What you should realize, too, that private browsing or incognito mode is entirely client-side. So particularly those logs that we have mentioned are still being stored by the server. They might be storing perhaps a different tracking cookie or parameter for for you because it doesn't necessarily recognize you when you're in private or incognito mode, but it doesn't mean that your tracks are completely absent from the internet. Rather, it's really just scrubbing them from your local computer and decreasing the probability, but not eliminating the probability that a server still knows that it's you. So I would use with care, but with that said, if you take a course in web development or you already design your own websites, using private browsing or incognito mode can also be useful for development purposes because it's a way of opening a brand new window that has no recollection of maybe past bugs that you had or past web pages that you clicked on, and it's very commonly used as part of development tools to actually facilitate and mimic the idea of starting fresh with some site. Super cookies, though. These sound delicious, but these two are kind of the worst of cookies that we've discussed already. We saw session cookies for maintaining state. We saw tracking cookies for tracking you. Super cookies are not so super really. These are cookies that are typically injected by a third party, like your company, your university, or your internet service provider into your HTTP requests. Which is to say, if you, from your browser, visit some website, that traffic, of course, goes from your laptop or phone through some internet service provider, whether it's on campus or home or wirelessly in the real world. And if whoever is providing you with that internet service can see the contents of that virtual envelope, there's technically nothing stopping them from opening up the envelope, so to speak, and adding one or more HTTP headers of their own. And so mobile phone carriers, for instance, in the past have been known to do this, whereby if you are just requesting a website like example.com from your phone, they might, halfway between you and that server, they might inject a cookie of their own. For the sake of discussion, I'm going to use the same name and value as before, ID equals 1234 ABCD. But what's noteworthy here is that that value is not coming from your phone. It is not coming from your browser. You can clear all of your cookies. You can clear all of your history. You can use incognito or private mode on your phone. You're not going to see any trace of that client side because the darn thing is being injected into your traffic between you, point A, and the server, point B. So this is sort of a canonical example of a machine in the middle attack, but your internet service provider in this telling of the story is doing it because they want to track you, or they want, because of advertising relationships they might have with some websites, they want to make sure that you can be tracked by that website, even if you have opted out or have been clearing proactively your very own cookies. So suffice it to say, these have been particularly controversial, and thankfully you and I do have a pretty good defense here. Just never use HTTP without encryption. If your URLs are always https:// and then something, theoretically this attack or this feature of your mobile phone carrier should not be possible. Why? Because if the contents of the envelope are encrypted, not only can't they see what's actually inside, they can't add anything to the mix because they don't have the key that's being used to encrypt that information. So simply using always HTTPS is one solution to this problem. And also, at least in the US, some of the mobile phone carriers got a lot of backlash for this. But so you can occasionally log into your cell phone provider's website, go through a bunch of menus, find an option to opt out of this feature. But I will say from experience that they typically bury these options too, and so it's not necessarily even the easiest thing to find. But again, this is just a natural result of the underlying technology that we're using being used, or if you prefer, abused, for alternative purposes. All right, let me pause here and see if there's any questions now on these super cookies, which indeed are not so super, or anything prior.
Given that cookies store passwords and emails, can the adversary impersonate another person by copying that cookie and pasting it into his own computer and visiting that website?
A good question. So cookies can be used to store usernames, email addresses, even passwords, though I would generally not recommend doing this. But they theoretically should be secure, even if you're storing those values in cookies, because they're going back and forth between the browser and the server using encryption, if HTTPS is indeed in use. A danger, though, is that if someone has physical access to your computer, it's very easy to poke around your own browser's cookies, at which point they're going to see your password, which is probably not a good thing. So an alternative would be, for instance, for a browser to encrypt the cookie or minimally digitally sign it so that it can be identified as belonging to that same server. But even better, I dare say, would be for servers to only plant big random values as cookies on your computer, like this virtual hand stamp, and then store recollection of your username, email, and/or password on the server. So stamp my hand to remember who I am and that I'm logged in, but don't bother expecting my browser to send my username, my email address, my password again and again. It should suffice to send that just once. Other questions here?
I've heard that it's possible, for example, if I'm writing a text to someone, it's possible to intercept, alter my text, and send it on my behalf. So it's going to be a different message. So it's possible to ask maybe for a sensitive information. So I was wondering, don't those messengers use something like cookies? How can this be possible?
A good question. So SMS, or traditional texting, is generally insecure. It is very easy for someone to forge your phone number. And in fact, if you've gotten a lot of spam via text, that might be exactly what is happening. Or worse, it's also possible, recall, to steal your SIM card, essentially, or port it to another carrier so that someone can intercept all of your actual text. So in general, nowadays, you should be reducing, if not eliminating, your usage of SMS, at least for anything important or anything you want to keep private. When it comes to other messaging tools like iMessage, like WhatsApp, Signal, Telegram, there's a lot of products nowadays, third party or otherwise, that use end-to-end encryption, which, recall, we discussed a couple of classes ago. And in that case, even though the data is going through a company like Facebook, theoretically, assuming they're behaving honorably and have implemented end-to-end encryption properly, then even they cannot see the message going between their servers. And that is independent of cookies. Cookies have no part of that solution. That solution is entirely thanks to cryptography and encryption with digital signatures. All right, let's consider one other threat to your privacy that you might not necessarily have thought about, that doesn't relate just to the web, but really your use of the internet more generally, namely DNS, the domain name system. Thankfully, even though computers on the internet all have IP addresses, these unique numeric addresses that we've discussed, you and I don't have to remember what servers' IP addresses are, because servers typically have domain names, something like harvard.edu, yale.edu, stanford.edu, google.com, amazon.com, and others. But how then, when you type in any of those domain names into your browser or into any piece of software on the internet, how does your browser or your computer know what IP address to contact? Well, it turns out that there's a domain name system in the world. And this is a system deployed throughout the world on the internet whose purpose in life is to translate domain names to IP addresses, so that on the outside of those envelopes can indeed go the IP addresses of source and destination, but you and I as humans don't need to know or remember exactly what those IP addresses are. You can think about this back in the day of when we were in the habit of typing in phone numbers to actual analog landline telephones. It was actually pretty hard to remember lots of people's numbers, and you might even have had an address book that you looked up people's numbers in, or there were certain mnemonics. For instance, in the United States, there was a number 1-800-COLLECT, C-O-L-L-E-C-T, which was just much easier to remember than the actual numbers for making a collect call. The equivalent on the internet is DNS, which just automates this process for us so that every website, every service can have its own unique name, but it's translated automatically for us via DNS servers throughout the world to the corresponding IP address. But why is this problematic? Well, it turns out that DNS servers are typically in a few different places. One, you probably have one in your home or your company or your university. And it probably is built into, if in your home, the router, the device that you're using just to connect to the internet. But your internet service provider also tends to have a DNS server. And that DNS server probably knows about way more IP addresses than your own home does, because why would your own home network know about all of the IP addresses in the world? But with that said, why would your internet service provider know about all of the possible IP addresses and domain names in the world, well, suffice it to say for our purposes, there's a hierarchical system. So even if your home router doesn't know, even if your internet service provider doesn't know, there's some other server on the internet that can eventually give you the answer to a question like, what is harvard.edu's IP address? What is yale.edu's IP address? And so forth. And for efficiency, once that answer has been figured out somewhere, then your internet service provider might remember or cache the answer, and even your home router, and heck, even your device or your browser might remember the same answer for efficiency so that we don't have to keep asking this same question. And it turns out by convention, DNS uses port 53, if you recall our discussion of also using unique numbers to identify things like HTTP or 80 or HTTPS or 443 or 22 for SSH. DNS tends to use 53. But the catch is that the traffic used for DNS is typically unencrypted, which means that when your phone or your laptop or your desktop is asking your home device or maybe your internet service provider or someone else, what is the IP address for harvard.edu or yale.edu or the like, you're actually announcing to the world what website you are about to visit. Why? Because you're waiting for a response from the DNS server to actually tell you the corresponding IP address. So this isn't great, and moreover, your internet service provider, therefore, knows all of this information about you, because every time you ask for a new website that you've never been to before, your home network probably doesn't know the IP address, so you have to ask your internet service provider. And again, they might ask someone else, but the internet service provider is going to know now that you asked. So your internet service provider, be it for your home network or for your cellular phone, pretty much knows every website you've ever been to, assuming they're logging this information, which they probably are, unless there are regulatory or legal requirements that say they can't or they can't for very long. Now, why is this the case? Well, the domain name system essentially requires that we ask these very questions. And if the internet service providers remember these answers, well, they can keep track of everywhere we've been, at least at a high level. DNS only gives them back a translation from the domain name to the IP address. What it does not include is the specific page that you're looking at, the specific URL, the folder, the file that you're looking at. So your internet service provider might know you're visiting somewhere on harvard.edu because you asked, of course, for its IP address, but they don't know what department you were looking for or what course you were looking at or the like. But there's still a decent amount of invasion, therefore, of your privacy if you'd rather that ISP or someone else just not know that information. So increasingly, there are alternatives to the standard DNS functionality, one of which is called DNS over HTTPS, or DOH for short. This means exactly that. Instead of just sending out DNS requests unencrypted on port 53 to the local DNS server, now they're sent, potentially, if you enable this, over HTTPS. And what this means is that they will be sent using the HTTP protocol, which we've talked about endlessly in these virtual envelopes, but securely, using TLS, which is the encryption protocol that ensures that no one else can see what's going on inside of that envelope, including your internet service provider. Now, someone is going to still know what domain name you're looking up, because after all, to whom are you sending this request? Maybe you're sending it to Google, maybe you're sending it to some third party, but you are sending it to someone. But at least, goes the thinking, it's not your internet service provider who really doesn't need to know this information. So that's one way of thinking about it. And there's alternatives to this. There's actually something called DNS over TLS, DOT, which is very similar in spirit, but it doesn't even bother using HTTP, but it is still using encryption. So this is something that's increasingly common. It's not necessarily the default on a lot of systems, but it's yet another feature of today's technology that you can increasingly look for, seek out, enable proactively, if this too is a concern, that you don't necessarily want a third party like your ISP to know what it is you're accessing. And it might not even be your own ISP if you're on the road and in a coffee shop that gives Wi-Fi or an airport that gives Wi-Fi. At that point, your internet service provider is effectively that coffee shop or that airport. And do you really want them knowing everywhere you're going? You might be, depending on your comfort level, you might be preferring that at least all of your DNS requests go to some other central party that you do trust for whatever reason, so you're not just informing every different Wi-Fi hotspot that you might be using around the world. Let me pause here and see if there's any questions now about DNS and this concern with respect to your privacy or these solutions there too.
Can DNS spoofing used to deceive users and steal like information which is sensitive?
Absolutely. So DNS itself can also be used for evil purposes. If you control the DNS server, you don't have to give an honest answer. If someone asks you for the IP address of harvard.edu, you could give them the IP address of some completely malicious server that you control. However, if the user, like Ryan in this case, is using HTTPS, the whole point of HTTPS is to encrypt the data between browser and server, and presumably the browser is going to try to request the TLS certificate of harvard.edu in this case. But if the IP address returns the wrong certificate that wasn't signed by the right website, then the connection might fail. And you'll be given a warning that you can typically ignore in your browser, but this should be preventable because you should at least be warned that that is not working correctly. And ISPs actually do this quite often. If you make a typographical error sometimes on home networks or coffee shops or airports, you might actually still see a website of like search results or worse, advertisements. And that's because even if you made a typo in the domain name, the coffee shops or the airport's DNS server is still going to return to you an IP address of their server so they can at least push some content at you. So let's consider some of the mechanisms via which we can push back on some of these more invasive privacy practices. And one is something we've talked about before, namely a virtual private network or VPN, which is a increasingly familiar technology, but it's worth knowing exactly what problems it is solving for you and exactly which problems it is not, particularly if you're using such a service to protect your own privacy. Well, what is a VPN? It allows us, recall, to connect from point A to another point B using a completely encrypted tunnel. So it doesn't matter if there are machines in the middle, as indeed there will be on the internet, all of the traffic between A and B on a VPN is encrypted or scrambled. So what does this do? This allows you to access sometimes a corporate network or a university network that might have servers or services that are only accessible if you are on physically or if you are on virtually that particular network. This ensures that even if you're at home or in a cafe or an airport, at least you have an encrypted, more secure connection to the campus or the corporate network, at which point the campus or company might be more comfortable with you accessing those services. Now, this does not prevent you still from being hacked, because if you're running malware on your own computer accidentally, it doesn't matter if you have an encrypted connection to the company or campus, you might very well have an infected connection now to the company or campus if you yourselves are infected. VPNs can also be used to create the illusion that you're actually in one country and not another. Why? Well, if point A is where you are and point B is somewhere abroad, well, to the rest of the world, if you start using this VPN, this virtual private network, you will appear to have an IP address that is in that foreign country, because all of your internet traffic for chatting, video conferencing, the web will be sent through that VPN by design. That's what a VPN is for. And it will come out the other end in that foreign country and then continue on its way to the chat service, the email service, the web service, or the like. So each of those services will think that you live or are physically in that foreign country, even if you are not actually. So what's the implication of this? A virtual private network only guarantees that the connection between you and that point B is encrypted. It doesn't necessarily mean that once you're out of that VPN, it's going to stay encrypted, especially if you're using still HTTP and not HTTPS, but it does at least encrypt everything between points A and B. It also does change what your IP address appears to be, so that you will indeed appear to have an IP address that's from that foreign country and not your domestic IP address, which might have some value in covering your tracks or decreasing the probability that you'll be identified. But again, we've seen so many other mechanisms today whereby your browser can be fingerprinted in the context of the web that someone might still be able to realize that, okay, your IP is different today, but this still looks like you, even if they don't necessarily know that you are David Malan or you yourself. But it at least does solve at least one problem, which is encrypting end-to-end all of your traffic. Well, there's another piece of software that's been popular for some time called Tor, the onion router. So this is a piece of software that you can install on your own Mac or PC or other device. And this uses encryption to solve the problem a different way, using additional encryption to try to give you a higher probability of privacy. And here's a picture that Tor themselves puts on their website. And it has depicting here you on a very old school PC connecting to a whole bunch of nodes inside of this Tor network connected to ultimately maybe the websites that you're visiting. And what happens here is that when your computer is running the Tor software first figures out, OK, who else in the world is using the Tor software? Because it's going to use those other computers to route your traffic up, down, left, and right. And kind of like the movies or TV where you see a map of the world and the traffic is bouncing back and forth and back and forth, that's kind of the spirit of Tor. And what happens is if your computer here wants to send a request to a website that's maybe over here, and it decides, for instance, to route it through 1, 2, 3 computers, what the Tor software will do is encrypt the request at least 3 different times. Whatever web request you are sending, whatever email you are sending, whatever chat message you're sending, whatever service you are using between point A on the left and point B on the right is going to be encrypted with this node's public key, with this node's public key, with this node's public key. And so here's the onion in Tor, the onion router. You are encrypting layer upon layer upon layer of data so that mathematically, recall per our discussion of public key cryptography, only this node can peel off one layer, only this node can peel off one layer, only this node can peel off one layer using their own respective private keys, which undoes the effect of your having encrypted your traffic. So what you're really doing here by choosing perhaps a different path every request, a different path every day, is you are with Tor effectively covering your tracks in some sense. And by design, the Tor software doesn't remember much information at all, so it doesn't have the sorts of logs that I propose can be worrisome, at least in the context of web servers. By design, Tor is meant to preserve your privacy with higher probability, and so by design, it just doesn't keep nearly as much information around. Now, this isn't to say that if you're doing this for malicious purposes, trying to evade the authorities, this isn't to say that this computer, this computer, this computer couldn't be subpoenaed, so to speak, by some government entity, and they could reconstruct the path that your data took. But the point is that it's generally quite laborious. By this time, all of that data has disappeared from those interior nodes, and so they don't have much information to share. And so increasingly, it does provide you with some higher probability of privacy by layering your requests with encryption, 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 and sort of trusting that these interior nodes are going to relay it to the final endpoint. So something to consider if of interest, but realize too that because of how the internet works with IP addresses, because of how the internet works with port numbers, it's still possible on a network to know who is using Tor, for instance. So if you happen to be the only person at home, the only person on a company or on a university network who's using Tor at the moment, it's being used for malicious purposes, odds are you could be targeted as the source of that attack. And so realize in particular that this just raises the bar to detection. It raises the bar to your privacy being invaded, but it does not, as do none of the technologies we've discussed, give you an absolute protection of these same properties. So there's one final mechanism when it comes to preserving one's privacy that's thankfully increasingly available to us on devices, on desktops and laptops, and especially on phones. And that's this notion of permissions, which isn't anything new, but as iOS and Android and other operating systems have evolved, increasingly you and I are being asked by our operating systems, do you want to allow this? Not only do you want to allow this program to run, but do you want to allow this program to access your camera, for instance? Do you want this program to access your microphone, for instance? Do you want this application to access your contacts, for instance? So on the one hand, we're being given much more fine-grained control, which is a good thing, presumably. At the same time, it's also just pushing the decision onto you and me. And very often with these applications, as you've probably found, well, if you don't enable the camera and give access to the app, it just might not work because they have some code in their application that says if camera is not on, then do not do anything useful. So there's this tension between usability and privacy in this case, but thankfully there's finer grained controls too. On iOS, for instance, you might be prompted, do you want to give this app access to this feature always, or only while using the application, or never? And that's certainly a good thing for something like the camera or the microphone, where it would be nice to trust that when you close the app and put your phone in your pocket, that it's not still listening to or trying to watch you from this built-in hardware. Now, there is some feature that might need to run all of the time, which includes location-based services, which is to say that our phones, especially nowadays, can pretty effectively track our location using GPS or Wi-Fi or some other technology. Now, that's, of course, useful, if not necessary, for using mapping applications like Maps or Google Maps or the like that help us get physically from point A to point B. But very commonly, these applications, at least by default, ask for access to your geographic location always, which means just by walking down the street, even if you're not following a map on your phone, means that the app can still be tracking where you're going. And certainly among the Googles and the Apples of the world nowadays, or other manufacturers, they certainly know pretty much everywhere you and I are going if we leave these location-based services on by default. So this is an example of something of which you should be mindful, if only because here is yet another example of information that logically, when you think about it, okay, obviously that makes sense. They must be keeping track of my location. Otherwise, how could they provide me with mapping services? But pause and think now, perhaps, exactly what the implications are for you, for your privacy, and just walking around 24/7 with these radios now in our pockets. So even though there are quite a few threats to our privacy online especially, at least there are these mechanisms that you and I can enable to at least preserve some of the same. Well, what have we done over the past few weeks? We began with a look at how we can secure our accounts, then our data, then our systems, then our software, and today, of course, focusing on preserving our privacy. And by way of the various technologies we've looked at, the stories we've told, the principles that we've introduced, we hope that in the days, the weeks, and the years to come, you can use all of these first principles and these ideas and these building blocks to extrapolate to how new technologies work, to how new threats might affect you, and to what questions you should be asking of either the software you use or the software you develop to ensure that not only your communications are secure, but also that it has these privacy-preserving properties that you and your users and your customers might want. This then was CS50's Introduction to Cybersecurity, and this was CS50.